Okay, so we are going to talk about binary search trees. So binary search trees are a data structure that you should properly learn in your 2270 data structures class. Okay, but they are so important and so useful, and they appear all over the place, that it's worth talking about binary search trees in an algorithms class, because many algorithms will be built on top of binary search trees. So therefore it is very, very important. So I'm going to mostly focus on algorithms, on complexity. I am not going to focus so much on how do you implement a binary search tree, how do you use pointers, how do you do it in Python using references and classes and so on. Okay, I'm not going to focus so much on that. I'm going to focus more on the algorithms so that it can serve either as a review if you have already done this in data structures, or it can serve as a preview if you are yet to do this in data structures. All right, what's a binary search tree? Well, a binary search tree is a data type. It's an abstract data type that supports the following operations. Okay, so it's going to support the ability to insert an element. It's going to support the ability to delete an element. Okay, and it's going to support the ability to find if an element exists. Okay, and it's going to support various kinds of traversals. Okay, that can be used to support operations like map, iter, and so on. Okay, now what kind of a data type is it for? It's a data type for collections. I should have mentioned that. So it's going to store a collection or a set of objects and so on. So one assumption I will make is elements cannot repeat in this collection. So it's going to be a set-based collection. So elements cannot repeat. There can only be one copy of 1, 2, even though that can be relaxed. You can have binary search trees that have multiple copies of the same element. Right now I'm going to have one copy. All right. Now each element has an important member called the key of the element. Okay, and the key is always going to be a number. Okay, so I'm going to pretend that all the elements are numbers, even though they may be different from numbers, but let's assume they have a key, and the key is going to tell us a number corresponding to that element so that we can compare elements. So it provides a way of comparing elements. Okay, now using binary search trees, I can build other data structures. So I can build a data structure for a set. I can build a data structure for a dictionary, or a map. Okay, and these can be built using binary search trees. Okay, so let us investigate what's the structure of a binary search tree. Well, a binary search tree has a bunch of nodes. So this is what a tree looks like. Okay, and it has some leaves. I'm going to use a special character for leaves, and they are all called nil. Okay, every leaf is called a nil. I'm going to soon stop writing these leaves. Okay, every node except for leaves, so every node has 2 children, and these are called internal nodes. So internal nodes, which are shown in circles, has 2 children. Every leaf, which are shown as nil, has no children. Okay, so this is exactly how we would write down a binary search tree. Now what's the property? So every node has an element, right? So every node has an element. Let's call this E1, E2, E3, E4, E5. The leaves don't have elements. All right, the leaves don't have elements. Now the main property, the important property, binary search tree property, the important property is that if I have an element E1, then E1 dot key must be greater than or equal to E2 dot key. So the key of the left child must be less than or equal to the key of the parent. So in other words, I can say E2 dot key must be less than or equal to E1 dot key. So the left child key must be less than or equal to parent, and the parent must be less than or equal to E3 dot key. So the right child must be greater than or equal to parent. So if I move to the left child, the key reduces. If I move to the right child, the key increases. All right. So this is the right child. All right. What else? Note that leaves do not have any key, so I have to modify the statement a little bit. Likewise, E4's key is less than or equal to E2 dot key, and E5's key is greater than or equal to E2 dot key. Okay, and more importantly, every node in the left subtree of E1, the key must be less than or equal to. Every node in the right subtree, the key must be greater than or equal to. Okay. All right. So to summarize, let us draw examples of binary search trees that are valid and non-examples. So here is an example. So let me just draw the key. Let's say the root has 25, excuse me. The left subtree all has to have keys less than or equal to 25. Okay, this is important. Less than or equal to 25. Not just the node immediately to the immediate left child, but everything in the left subtree has to be less than or equal to 25. So 20. Now everything on the left subtree of 20 has to be less than or equal to 20. Let's say 18. Let's say 15. Now it has to be greater than 18 but less than 20. So let's say 19. 19. Okay, this is 19. Let's say here it has to be greater than 20, less than 25. Let's say 23, 21, 24, greater than 20 but less than 25, less than equal to 25. All right. Let's say 29, 31, and then let's say nil, 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 nil. Okay, so those are going to be the leaves. I will soon stop writing these leaves, but for now I will write these leaves. Okay, so notice that if I have the right subtree of a node, and the key of the node is 25, the right subtree has all nodes greater than or equal to 25. And since I say that the keys must be unique, it has to be strictly greater. I'm not allowing keys to be equal. If I allowed keys to be equal, I would say greater than or equal to. But right now I'm saying greater than. All right. Likewise, everything to the left has to be less than 20. All right, for 25. Now let's say take this node with key 20. Okay, the node which I'm pointing to in green. So for the left subtree has to be less than 20. Okay, I've already said that. In the right subtree, it has to be greater than 20. But since it's also the left subtree of 25, it has to be everything in the right subtree of 20 has to still be less than or equal to 25. All right, so hopefully you get an idea of binary search trees and the structure. And by the way, this is a 31. 31. All right, hopefully you are getting an idea of what binary search trees are looking like. Let me give you some non-examples. So what would be some non-examples of binary search trees, some bad binary search trees, which are going to fail this property? So take an example. What about this example? So in this example, 20 is the root node. So this, by the way, this is called the root node. Okay, and its left child is 19, which is fine. 19's left child is 17, which is fine. The right child is 21, okay, which is fine with regard to 19. But if I think of 20, I note that everything in the left subtree of 20 needed to be less than 20 or less than equal to 20, but I am not allowing duplicates. Let me remind you of that. So in this case, this node is illegal because it cannot be here. It cannot be where it is because it cannot be to the left of 20 because it's greater than 20. Okay. If it were legal, then it should have been to the right of 20. So it should have been in the right subtree of 20. All right. So this is super important. All right. So I've given you an example of a binary search tree. I've given you an example of something that's not a binary search tree. All right. So what are the important properties of each node? So for each node in a binary search tree, if the node is not nil, okay, if n is not nil, then n dot left is the left child. N dot right is the right child. N dot parent is its parent. Okay, and just for completeness, I will keep the parent of root to be nil. Following the book convention, the parent of root will be kept to be nil, and that's how you would know if a tree is, if a node is a root. Okay, so n dot parent is its parent, n dot key is the key. Okay, and this is all following CLRS convention. Okay, CLRS convention. All right, so now that we have binary search trees, I want to define a few things for binary search trees. Okay, so next step is let me define the height of a binary search tree. So what's the height of a binary search tree? Well, if you start with a binary search tree, let's say an example like that. I'm not going to show all the nils. I will just try to show some of the nils. All right. Okay, so suppose this is a binary search tree. All right. We define the height of a node as the length of the path. Okay, the length of the path or the length of the longest path from that node to a leaf. So in this case, if you start from the root, the longest path is going to go all the way right to a leaf, or you could go all the way right and then left, same thing. All right, and the length of the longest path is going to be 1, 2, 3, 4, 5. Okay, so many books will differ on whether to count the node itself or not to count the node itself. All right, so in the case of CLRS, I believe the height is simply defined as 1, 2, 3, 4, and you do not take the very last node into account. Okay, you do not take the leaf into account. So that allows us to define the leaf as having height 0. So the leaf has height 0. Okay, this node, let's call it N1, has height 1. Okay, so the longest path can go either way. It has height 1. Okay, for example, let's take node N7. Okay, N7 has height 1, 2, 3, 4. Okay, so how do you define the height of a node? So height of a leaf is defined as 0. Okay, now some books will define it as 1, so be careful there. Okay, be careful. But whatever answers I get you will be off by 1, so we are not going to really worry too much about 1 or 0. Let's just define the height of a leaf to be 0 and start. Height of a node is recursively defined as height, take the height of n dot left, take the height of n dot right, okay, and take the max of these and add 1. Okay, so take the max of the height of n dot left or n dot right, whichever one is larger. So take the max of this and add 1 to the result, and that gives you the height of a node. So for example, the height is 0 at these two leaves, the height is going to be 1 at the node here, the height is going to be 0 at the leaf, at the node here, let's call this N3, the height is going to be max of the height of its right child, which is 1, height of its left child, which is 0. So max of 1, 0 is 1, okay, plus 1. So the height of this node becomes 2. Likewise, the height of this node becomes 3. The height of the root becomes 4. Okay. So the height of a tree is defined recursively by defining the height of each node, starting with the height of the leaf being 0. All right. So if a binary search tree has n nodes, okay, how high can the root be? How high can the root be? Okay, and that is defined as the height of the tree. So the height of the tree is simply the height of the root node. So what's the height of a binary search tree? All right, there are two cases. So in the worst case, the tree can be completely unbalanced. What is a completely unbalanced tree? Well, every node just has a single child, okay, which is not nil. So the tree is simply almost like a linked list. So it's almost like a linked list. Every node just has one child, which is an internal node. Another child is nil, except for this node, which has nil and nil. So 1, 2, all the way to n. Okay. So in this case, the height of this tree is going to be 1, 2, 3, 4, all the way to n. So height of the tree is going to be n, which is the number of nodes. All right. This is the worst case. What's the best case? The best case is a completely balanced tree where every node has 2 internal nodes, except for the nodes at the very end, which are going to have 2 leaves, okay, nil, nil. Okay, so this is going to be all the leaves. So if there are n nodes, what is the height of this tree? Okay, so if there are n internal nodes, n circles, how high can this tree be? Well, we can talk about this. So if there are n internal nodes, okay, so there is one root, 2 nodes at this level, 3 nodes at this level, and let's say the height is h. So there are going to be 4 nodes, so 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power h minus 1, okay, where h is the total height of the tree. So what is the equation? Equation is 2 to the power 0 plus 2 to the power 1 all the way to the 2 to the power h minus 1 equals the number of nodes in the tree, number of internal nodes, n, or 2 to the power h minus 1. This is the geometric summation, geometric series. And this sums up to 2 to the power h minus 1 is n, or h is going to be log to the base 2 of n plus 1. Okay, so the height of a tree with n nodes is going to be roughly log to the base 2 of n. Okay, if you want to be precise, it could be ceiling log to the base 2 n, and this is the best case. Okay, so this is the best case, and this kind of a tree is called perfectly balanced. And here this tree is highly imbalanced, so much so that it becomes a linked list, right? The tree becomes a linked list. What about the trees in the middle? Trees in the middle are going to be somewhere between the worst case, which has to have a height equal to the number of internal nodes, and the best case, which has to have a height equal to log n. Okay, remember there's going to be a plus minus 1 here depending on how I define the base case. All right, I'm not going to be super accurate in this class. So what about other trees? Generally, trees are going to be somewhere in the middle. Okay, so they are going to have some imbalance. Okay, so they are going to have some imbalance. Okay, so they are going to have some imbalance. I'm not going to write the remaining nil. So you can see the tree is imbalanced For example, the longest path from the root to leaf that defines the height of the tree is going to be something like this. All right. Whereas you can see there's another path which is much shorter. All right. So this is going to be imbalanced, not perfectly balanced, not highly imbalanced, but somewhere in the middle. So there is a sliding scale where the height of the tree in the worst case can be n, in the best case can be something like log n, all right, which is a big range to be, all right. So for example, if you insert, for example, n equals 2 to the power 18, which is roughly 1 million, okay. So if you insert about 1 million nodes, the height can range from about 18 in the best case to about 1 million in the worst case, all right. This is amazing range of heights, all right. And the worst case is when the tree is just a single path, okay. And in this case I'm just showing everything going to the left. It could go to the left or to the right, but the point being that every internal node here has exactly one internal node children, and then there's one leaf, one internal node which has two leaves, okay. So and it looks like a straight line tree, okay. It looks like a straight line tree, or almost like a linked list, okay. Whereas in the perfect case, the tree can be perfectly balanced. Every internal node has two internal node children, except at the very end where it has two leaves. All right. So the height of a tree is going to be very important, because the algorithms we are going to talk about for insertion, deletion, and so on are all going to depend on the height. Okay, so we are going to talk about that in a second. Talk about the simplest operation on a binary search tree, which is the find operation. Okay, so what is the find operation? So I'm going to give you a key, okay, a number, a key, and ask you in a binary search tree to find an element that has the same key, or tell me that you cannot find an element. All right, how do we do that? All right, let's take an example to motivate how find works in a binary search tree. So suppose I have a binary search tree. I'm going to fill in numbers later. Let me just draw a nice big tree. All right. Okay, here is my nice big tree. Let me not make it perfect. Okay, let me make it a little bit unbalanced right there. Okay. Now, one of the things I would highly suggest you do as practice is take examples and write down some examples of binary search tree. When you do so, the concepts become clearer for yourself. Okay, so let's put in some numbers here. So let's put in 50, 25, 12. Can't be 12, can it? Let's do 32. See, now I'm learning a lot by writing an example out myself. 22, 18, 14, let's say 60, 70, 68. All right, so here is my binary search tree, and I would like to find 45. Okay, so I would like to find 45 in the binary search tree. So initially, I start at the root. All right. So 45, at the root, the key is 50, and 45 is less than 50. So that immediately tells me that if I find 45, I'm going to find it in the left subtree. So I'm going to go left, and if I go left. Okay. Now you see why it's called a binary search tree, because it's going to behave very much like binary search algorithm, right? If I go left, I encounter 25 as the immediate left child. Okay, let me compare 45 and 25. Well, 45 is greater than 25. Okay, so what I'm searching for is greater than the key, so I have to go right. All right, I go right. Now I'm going to search in the right subtree. So I'm here at this node 32. So go right. Now I'm at the node 32. 32 is less than what I'm searching for, 45. So I'm going to go right again, right? I'm going to go right again. So go right. All right. Now what happens? I go right and I end up with nil. So I'm going to return a pointer to this node, nil. All right. Why am I going to return a pointer to nil? You will see later. You will see later. So I'm going to declare not found, and as a investment for later, coming right up, I'm going to say return a pointer to this node or return a pointer here. Okay, so return a pointer here so that I may do something to it. All right, good so far. How about I find something that's actually in the tree? Let me find 68 in the tree. I know secretly it exists. How about I find it? Well, I start at the root again. If I start at the root is a 50 and I'm interested in finding a 68. So I go right because what I am searching for is larger than the key at the root. Now I encounter a 60. Well, if I encounter a 60 and I'm searching for a 68, still larger, go right. Now I encounter a 70. Well, now it's smaller, go left. Well, now I encounter a 68, bingo, find it, return a pointer to the node where I found it. All right, so this is how it's going to work. So what is the idea? So I'm going to write find node key. Okay, so this is going to be the algorithm. What's the algorithm? If node is nil, return node. Okay, so if the node is nil, just return it. I've failed, so it's going to return a nil. It's going to return a nil. Else, if node.key equals, let's call this the search key. So I'm going to call this S key, the search key. Then bingo, return node. Okay, so if I found it, return. If I didn't find it, else, if node.key is greater than S key, if what I'm searching for has a key which is greater, which is less than the key of the node, then I search in the left subtree. So search left, go left, right? So this is the key that I'm interested in. This is the key for the node. Obviously, if I'm going to find it, I'm going to find it in the left subtree. Am I right? Yes. Okay, so what I'm searching for is smaller than the key of the node. Okay, this always trips me up a little bit. So return, what should I return? Well, this is recursive. So I'm going to find node.left S key. So find the key in node.left, all right? Else, go right, return find node.right the key that I am searching for. That's it. So it's exactly the algorithm that I sketched out. It looks very similar to a binary search algorithm, and that's it. That's really it. Okay. So what is the complexity of find? What is the worst case complexity of find on a tree? Well, in the worst case, I might be made to take the longest path from the root all the way to a leaf which is nil. So the complexity of find is theta of h, where h is the height of the tree. That's it. Okay, so the complexity of find is the height of the tree. So if the tree is very high, if the tree has large height, find is going to take a lot of time. If the tree is well balanced, find is going to be log n, right? So if the tree is imperfectly balanced or imbalanced, it's going to be theta n, number of nodes in the tree. If imbalanced, theta log n, if balanced. Okay, so what you will see here is being balanced will seem to be a very, very, very important aspect of all operations in a tree. So I talked about find. Okay, so find. So what about if I can do find? In fact, there is a very cheap addition to it where I can insert a new node. Okay, and the new node has a key which is new node dot key. All right, so how do I do insert? If I do find, I can modify find very slightly by doing an insert, right? So insert is just a small modification of find. So let us say instead of finding 45, I'm interested in inserting 45. So insert, when I say insert 45, I mean insert a node with other data whose key happens to be 45. All right, so insert a node whose key happens to be 45. Well, I already did a find of 45, right? And when I did a find of 45, I went searching starting at 50, then 25, then 32, and then I ended up here at nil. All right. Interestingly enough, if I wanted to insert, this is exactly where I insert the new node. So just a second. Okay, let me get an eraser here. So if I needed to insert, this is exactly where I would insert. So since find returns a pointer to this place, if I needed to insert, I would create a new node here, 45, set its parent to 32, nil, nil. How I implement that, how I data structure that in Python or C++ is something you would learn in your data structures class. But remember, the simple idea behind insert is first do a find. If you do a find, you will end up not finding the node you want to insert. If it's already there, you should not be inserting it, let's say. All right. If it is not there, then where you will end up in a find operation is you will end up going right to a nil node. Okay, you will end up going right to a nil node. So at that nil node, create a new internal node, make two leaves out of it and insert right there. So insert is just a little bit extra on top of find. So little bit extra on top of find. That's it. Okay, so if you know how to do find, doing insert is very, very simple. Okay, so inserting a new node is really simple. All right, deletion. Okay, and I have retained the example from the previous example on which we looked at insert and find, and we are going to talk about delete. All right. So what is the idea behind delete? So in delete, I have a tree. Okay, I have a tree, and I would like to delete a node with a key from the tree. So I give you the key, and that's enough. I don't need to give you the node. If I'll just give you the key, and I ask you to delete it from the tree. So for example, I could say delete, and since the tree here is just one tree, I'm just not going to put the tree here. So let me say delete. I don't know. Let's do an easy delete first. Okay. So let's do a delete of 45. Okay. So if I wanted to delete the node 45. First, I have to find out if there is a node with key 45 in the tree. All right. So let me find out if there is a node key 45. So I'm going to go 50, 25, 32, 45, and I found it. So this is the node to delete. Okay. Now, what are the easy cases for delete? Case 1. So there are going to be many cases. Case 1, node has a nil left or right child, which is node dot left equals nil, or it could be node dot right equals nil. Okay. So if, for example, both the children are nil, deletion is really simple. Just replace the entire node and the two children, just take them away and replace the whole thing by a nil. And that's it. Okay, so if I replace the whole node by a nil, that ends up deleting the node. So if the left child and right child are both nil, life is easy. Okay. So what happens if I wanted to delete, for example, 22? So in this case, I first find the node with the key 22. So this is the node to delete. Now the right child is nil, but the left child is not nil. Okay, so the left child is not nil. So if the left child is not nil and I want to delete it, simply replace it with the left child. That's it. So you can simply delete it and link it back to the parent. So how do we do it? So let me just handle one case where the node's left child is not nil. Okay. So the node's left child is nil. Okay, and right child is not nil. So and node dot right is not equal to nil. So the right child is not nil, but the left child is nil. All right. So first thing is I'm going to say node dot right dot parent. Okay, so here is the node. All right, left child is nil, right child is not nil. Okay, node dot right, and then it has a whole subtree hanging maybe, and then this is node here. Okay, and there is a node dot parent. Okay, so what is the first step? So node dot right's parent, I will make it to point to node dot parent. Okay, so now what I did is I bypassed the node. All right. The other thing I have to do is I have to find out if the node was the left child of its parent or the right child of its parent. Okay, so if node equals node dot parent dot left, if the node is the left child of its parent, then well, node dot parent dot left equals node dot right. Else node is the right child of its parent, node dot parent dot right equals node dot right. What did I do? I took this link from the node's parent to the node and I made it point to the node. So now node is free and it can be deleted. Okay, so the memory of the node can be recycled. Okay, so this is the deletion case when one of the children is nil. Okay, so when one of the children is nil. All right, otherwise what do we do? Otherwise here is what we do. So if, for example, let me say I want to delete the root 50. So in this case I want to delete 50. Okay, so in this case the problem is the node has two internal children. Okay, so both the children are not nil. So if I wanted to delete the very root of the tree, then both the children are not nil. Okay, so in this case, what do I do? All right, so we will take a trick that we learned from heaps, and what we are going to do is instead of deleting 50, we are going to go ahead and delete something else. Okay, what does that mean? So what we are going to do is we are going to figure out who is going to replace 50. Since 50 has both children, I need to find the successor of 50. What is successor of 50? Successor of 50 is the node that's going to be next biggest node to 50. All right. So what's the next biggest node that comes after 50? Well, here's the idea. What I do is I go, if in a tree, whenever I want to find the successor of a node and the node has both children, both internal nodes, what I do is I go one step to the right and then I go all the way to the left until I am about to reach a leaf. And this node is called the successor. Okay, this is a very important concept. Okay, so if I wanted to find the very next node in terms of the ordering of the keys, what I do is I go one step to the right and then I take all the way to the left until I'm about to get to a nil, and before I get to a nil, I just stop. Okay, and this is called the successor, all right? So in this case of 50, what is the successor? Well, the successor is going to be 50, go right, one step, 60, and keep going left until I'm about to get to a nil. So 60 is the successor of 50. So successor of 50 is this node with label 60. Okay, let's do one more example of successor. How about the successor of 60? Well, if the successor of 60 is I go right and then all the way to the left, it's 68. Okay, so go right all the way to the left until I'm about to hit a nil. That's the formula for finding successor. Well, I'm about to delete 50. So the deletion candidate is going to be 60. All right, so what do? I take this 60 and I transplant it here. Okay, now this node became transplanted here, and I simply delete the node here. And remember, this node always has one child which is going to be nil, so the deletion is already covered. Okay, the way I have calculated successor, one of the children has to be nil for the successor, and therefore deletion is covered. All right, so what is the steps for deletion? So case 2. So let me walk you through the different cases. Case 1, left child is nil, right child is non-nil, case 0, let's do a case 0, both children are nil. Okay, so case 0, case 1, one of the children is nil. Case 2, just the other way around, right child is nil, left is non-nil. Okay, and these two cases we've already covered. Okay, so we already covered. Case 0 is trivial. Case 3 is both children non-nil. Okay, this case is slightly more complicated, but what we do is find successor, which is go one step to the right and go all the way to the left. Okay, you find the successor, replace with successor, and delete the successor. And remember, the successor is always going to have one child which is nil, so you head back to one of these three cases here. All right, that's it. Okay. Now, what's the complexity of deletion? Complexity of deletion is, first I have to find the node to delete. In the worst case, I have to find its successor. Convince yourself that the sum of these two is theta of the height of the tree. So if I reach a node and I reach a successor, then I'm reaching a leaf. So this is theta of h, and from there I have to do some pointer operations to delete, but those aren't very big pointer operations, so do pointer operations. And you will learn about these pointer operations in 2270 class. Okay, and this is theta 1. So overall, it's still theta of the height of the tree. So we've looked at algorithms to insert, algorithms to delete, algorithms to find, and all their complexity is theta of h, which is the height of the tree. All right, so the height of the tree is becoming a very important factor, and I would like to know how can we make sure that the height of the tree is going to be small. All right, we will talk about this as soon as we cover traversals and then talk about height of the trees. Tree traversals. There are many reasons why we would like to do tree traversals. Okay, so if we are implementing a higher level data structure like a map or a set or a dictionary, then we would like to do operations like iterators. We would like to support iterators. We would like to support map operations. Okay, let's call this map a dictionary. So if you're going to implement a dictionary or a set using tree data structures, then we need to do iterations, map operations, filters. You might have learned a little bit in the functional programming module, okay, sometimes. Okay, so we need these operations. Okay, so these are operations that need to be supported. Another important operation is that called, it's kind of a generalization called a visitor pattern. Okay, where if I have a tree, I would like to visit every node in some order and do something, do some operation at each node. What could this operation be? I could just print the contents of the node. I could, for example, take the node and send it across the network. I could take the node and dump it on the disk. Okay, so there are things I would like to do. Let me say my default operation is print. But this doesn't have to be print. It could be anything that you want to do. You may not want to change the key at the node that invalidates the tree. But in general, you want to visit every node and do something. Okay, and that's called a traversal. Traversal simply means visit every node in the tree and maybe do something like print or something. There are three types of traversals. Okay, the types of traversals are called in order traversal, okay, pre-order, and post-order. Okay, so let us talk about in-order traversal. So in in-order traversal, okay, so which is the first one, I'll talk about in-order traversal. What I do is for each node, I first visit the left, first go left, then visit the node itself and then go right. Okay, so what does this mean? In an in-order traversal, so let me do in-order traversal of a node. It's going to be a recursive procedure, okay? So the first step of this recursive procedure is do an in-order traversal of node.left if it's not nil. Okay, so if it's not nil, node not equal to nil. If node not equal to nil, then do all of this. Okay, in-order traversal of node.left, then print. Let's say print is the operation I'm doing at each node. Print node.key, and then do in-order node.right. That's it. Now let's see what happens if I did an in-order of this tree. So if I did an in-order of this tree, I start from the root, I do in-order of root. Well, first it's going to ask me to do in-order of node.left, which is going to be this node 29, which is in turn going to do in-order of 18, which is going to do in-order of 12, and now I'm going to print 12. Okay, so in-order of 12 is going to do nil, so then print 12, okay, and then I go back up, I print 18, and then once I'm at 18, I do in-order of right, which is 20, okay, and then I go back, and then I print 29, and then I go to 32, 31, 30, okay, and then I print 31, and then nil, go back up, 32, okay, and then I visit 34, not 34, but then I go to 33, and then back to 34. Okay, so this is a recursive call where the rule is first my left child, then me, then the right child. Okay, that's the rule for everyone. First left, then me, then right. So if I'm applying that rule for 35, it says, oh, 29, you first. Well, 29 says 18, you first. 18 says 12, you first. 12 doesn't have left child is nil, so let's say then says 12, print itself, right child is nil, returns back to 18, then does the right child, so you get 12, 18, 20, 29, print itself, then attends to its right child, 32, but 32 says, wait, first my left child, 31, 31 says first my left child, 30, then back to 31, nil, 32, 32 prints itself, 34 goes to 33, 33 prints, 34. It seems complicated, but it's a traversal that follows the rule at every node. First left, then me, then right. Okay, if you understand that rule, then it's very easy to print the in-order traversal. And something very magical happens when you do in-order traversal. The nodes are printed out in the sorted order. In a binary search tree, if you do in-order traversal, the nodes are printed out in a sorted order. Okay, very good. Now what is pre-order traversal? This is the next kind of traversal. In this traversal, it says first me, node itself, then left, then right. Okay, so pre-order means first me, then left, then right. So in a pre-order traversal, what will happen is if I start at 35, 35 gets printed, and then it says go left child, print yourself. So 29 will get printed, then its left child 18 will get printed, 12 will get printed, I go back to 18, then the right child 20 gets printed, go back, then 32 gets printed, 31 gets printed, 30 gets printed, go back, 34 gets printed, 33 gets printed, go back all the way up, 60 gets printed, 45 gets printed, okay, and then 90 gets printed, 70 gets printed, 30 gets printed, 120 gets printed. All right, so pre-order, everyone follows the following rule. First attend to myself, then go to my left child, then go to my right child. It's a recursive procedure, okay, and it will stop when you get to nil. First myself, then left, then right. So following that rule, you see 35, 29, 18, 12, that's the order in which things start getting printed, and then 20, and then 32, 31, 30, and then 34, 33, like that. Okay, so it's a different kind of traversal. The last kind is called a post-order traversal. What is a post-order traversal? Well, post-order traversal says first my left child, then my right child, and finally me. First left, then right, finally me. So that's called a post-order traversal. I come last, pre-order, I come first, in order, first left, then me, then right. All right. Now these are three kinds of traversals of a tree. How much work does it take to traverse a tree? Well, if I put, let's say, $1, or let's say I put $3 at each node. Okay, so when I first visit a node, I collect $1. Okay, and when I visit its left child, I collect $1. When I visit its right child, I collect $1. Okay, so I pay $3 at each node. So what you can convince yourself is that the total number of operations that I do is roughly 3n or theta of n. So these traversals work in linear linear time in the size of the number of internal nodes of the tree. So if your tree has n internal nodes, these work in time that is proportional, directly proportional to n. Okay, so traversals are very important, very useful. You will get to do traversals of tree-like data structures a lot. So it's worth exploring traversals by implementing them, trying out examples and seeing what kind of trees do you get, what kind of order do things get traversed in when you do in order, pre-order, and post-order.
Hello, and welcome to this lecture on self-balancing binary search trees. So far, we've looked at binary search trees, and in a binary search tree, recall that the key property is that the key at a node and the key at its left child and the key at its right child satisfy a certain property. That is, the key of the left child is less than or equal to the key of the node, which is less than or equal to the key of the right child. So things that are larger than the node's key go to the right. Things that are smaller go to the left. Okay, so you remember this, all right? So this is very key. Now, one of the main problems with a binary search tree is the performance of most algorithms, to do operations like find, insert, delete. All of this depends on the height of the tree, also the depth, same thing, all right? Some books will call it height, some books will call it depth. And it depends on the order in which the keys were inserted. So that means that because if the keys were inserted in a bad order, for example, if you insert the keys, let's say 1, then 2, then 3, up to n, the tree that you end up with is going to look like this. So 1 is going to be here, 2, 3, up to n. So, and I'm not going to show the nil. There's going to be a bunch of nil. So the tree is going to look like this, and the height of this tree is going to be n. All right, and that's bad. So this is the worst case. So in the worst case, the complexity of find, insert, and delete become theta of n worst case, because in the worst case we assume that the worst possible enemy comes up with the way things are inserted or deleted or the find operations, and therefore everything is going to be theta n. That's too bad. On the other hand, if only I could get the tree balanced, if I could get the tree nicely balanced, okay, if I could get the tree nicely balanced, then the depth of the tree or the height of the tree could be as good as log n, right? Theta log n, let me, but it's literally log to the base 2 of n, and that's really, really good. So this is what I would really like, and this is what I do not like. All right, so the question is, how do I make sure that the trees can be balanced, where the height can be more like 2 log n or 3 log n as opposed to 2n or 3n? And one thing I always urge you to look at is consider some real numbers. So if n equals, for example, 10 to the power 7, which is, let's say, 10 million keys, okay, something like big data, okay, I'm looking at log theta log n is a few hundred operations. So a few hundred operations to find if an element exists, a few hundred operations to do search, insert, delete, and so on. Whereas theta of n is roughly a few million operations. Okay, and between these two there is the huge difference. Okay, this is efficient, this is quite inefficient. All right, so something that I'm really interested in is how can I ensure that the binary trees are balanced. All right, and one thing to make sure is that even if the user inserts things in this order 1, 2, 3 up to n, I want to somehow end up coming up with a tree that's balanced. All right, so a big deal is to implement so-called self S-E-L-F, self, all right, self balancing trees. So these are of course going to be more complicated than your binary search trees, than, let's call it, vanilla BST, which is what we looked at previously. So of course it's going to be more complicated, but you know, the question is, can the complication be worth it if you have large numbers of data elements that you're inserting in a tree and you want to do efficient search, you want to do efficient maintenance, then the complication is worth it. Okay, so there are many different types of data structures. Okay, so for example, there is what we are going to study today. It's called red-black trees. Okay, there's something called 2-3 trees. There's something called splay trees. There's something called AVL trees. Okay, treeps. All right, skip lists. Okay, so by the way, I won't be covering skip lists, but if you want to look up something, look this up. Really cool data structure. Okay, and in fact there are some data structures that are specific to access patterns like B trees. So this is useful for storing data in a disk, in a computer disk. Okay, so there is some very interesting kinds of data structures. All right, the ones that are really commonly used are red-black trees, AVL trees, and trees, because trees are really easy to implement. Okay, so for that reason, I'm going to cover red-black trees, and I'm also going to look at trees just for fun. All right, so the rest of this lecture we will study red-black trees. So I'm going to talk about what are the properties of a red-black tree, and why is a red-black tree balanced. Okay, so we are going to talk about this. So once we talk about the properties and why it's balanced, we can then talk about how do you do insert, delete, and on a red-black tree while maintaining these properties. All right, on to red-black trees. Okay, so let's talk about red-black trees. So what is a red-black tree? Very simple. It's a binary search tree plus extra stuff. What is this extra stuff? Well, the extra stuff is really simple. So suppose you have a binary search tree. Okay, binary search tree. All right, and for now I will show you the nil, the leaves which are going to be nil. All right. And these are going to be nodes. These are the leaf nodes. Okay, they are considered first class nodes, and the other ones are called internal nodes. We saw this last time, and this is mostly the book convention to do things this way. Other books do things slightly differently, no problem. All right, so this is a binary search tree. So what is this extra stuff? Right, so what is this extra stuff? Well, every node has a color, and the color can be one of either red or black. Okay, so it's like a single bit of information that you associate with every node in the tree in addition to the key. So the key can be something like 35, 23, 46, 40, 38, I don't know. So you can have keys, all right, as usual, all right, 42. All right, so you can figure out what the remaining key should be, for 54, something like that. So you can have the keys, and you still have the BST property, the binary search tree property. Recall, the key of the left child has to be less than the key of the root, has to be greater, and we still will not allow duplicate keys. So every key has to occur once. So I can simply say everything to the left is less, everything to the right is greater. All right, you know all of this. This is things that we are familiar. But then what we do is we also end up coloring every node with a color. And the color could be red or black. So some of these nodes have the red color, and some of these nodes have the black color. Since my background is black, I'm not going to bother coloring it black. All right, so let us say that. Okay, sounds good. All right, so what are the rules of a binary search tree? So what are the rules of a binary search tree? So remember, there is going to be some rules, and these rules are going to be super important. Rule number one, the root and the leaves, which are the nil nodes, are black. Okay, the roots and the leaves are black. Okay, that's number one. Number two, every red node must have, all right, every red node must have black children. Very, very important. So every red node must have black children. Number 2. Number 3, so I'm going to define this. The number of black nodes on any path from any node to its leaf, to a leaf, must be the same. Okay, so this is the most mysterious property and requires explanation. Requires explanation. Okay, let's leave this for a second. Forget about this for a second. Okay, so forget about property 3. Let's deal with properties 1 and 2. So property 1 says the root and the leaves are going to be black. That's great. So that's fine, easy to understand. If you have a red node, then the 2 children of the red node must be black, and they can be the nil, the leaves, the sentinel can be the 2 children, right? So every red node must have 2 black children. So these properties are easy to understand, and let me illustrate them on this tree example up here, right? So for example, you have node 35, which is black, and for black there is no requirement, right? So the root is black, the leaves are all black, that's automatic. And then if you have a red node, let's say 40 here is red, then it has 2 black children, right? Here you have 54, which is red, has 2 black children. So this is good. Okay, so this is good. Now the third property is very important. It says if you start from any node in the red-black tree, so let's start from some node in red-black tree. Okay, so let's call this node N, all right? And then let me look at all the paths from this node to a leaf. So here is an example of a path, and let's say along this path there are some red nodes. Let's say there are some red nodes and there are some black nodes. Then you count the number of black nodes. So let's say here I have 1, 2, 3, 4, and you don't need to count the starting node. Okay, let's just count the number, but don't count the node itself. Okay, and let's associate this with a concept called the black height. And let's call this 4. So which means that if I chose any other path, let's say there is another path that goes from this node to a leaf, then that path must also have 4 black nodes. And if I chose any other path, like for example, here is a red node, so its child has to be, let's say, black, nil. Now the number of nodes here must be 2, 3, 4. So the point is that even though you can have red nodes, if I start from a node and I count the number of black nodes from that node to a leaf, okay, counting the leaf but not counting the node itself, that number must be the same on every path. Okay, and when this number is the same, you define this number to be the black height of a node. Okay, so that means that every path, so for example, if I had a 2, that must have a black child here. Okay, so now you can, this looks complicated, but it's not as complicated as it looks. All right, so let's see some examples and see how this is going to work. So let me make sure everything. So for example, all right, so here is an example. And now you can see if I start from node N, make sure that every path has 4 black nodes. All right, so if this property holds, and this is very important, and this needs to hold for every node of the binary search tree. So for example, if I start from the node 2 here, if I start from the node which has around which I have labeled 2, its black height is 2. So black height . Okay, so let me take an example. Let me take an example and show you an example of a binary search tree, and let's talk about its black height. Okay, so here is an example of a binary search tree. All right, so here is an example. I am not going to draw the keys. All right, so I'm not going to draw the keys, but every node for which I have shaded it red is going to be red, and the nodes which I have left open is going to be black because the background of the slide is black. All right, let me make sure of the rules. Number one, root plus leaves are black. Is that the case? And you can see indeed that is the case. Roots and the leaves are black. All right. Number two, every red node has two black children. Can you check that? Okay, so let's look at every red node. So here is a red node, and you can see its children are black. Here is two red nodes, and you can see their children are black because remember nil is black. Here is a red node, its children are black. Very good. Now the third property is that, let me simply call this third property because it's too lengthy. Black height is defined for each node. And when I say black height is defined, the only way black height can be defined if the number of nodes, black nodes on each path is the same. That's the only way you can have black height be well defined. Let's call it well defined. All right, let's write down the black height. Okay, so for the nil nodes, the black height is 0. For node n, let me call this n1, the black height of this node is 1 because there is, if you go from this node to any leaf, there is exactly one black node. Okay, what about the black height of these nodes here? So I'm going to write it in blue. So they are going to be 1. The black height of this node is also 1. Okay, and the black height of this node here is also 1. No, actually it's not 1. It's 1 plus 1, which is 2. Because if you go along any path, you get 1, 2, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2. So check that for this node n, let's call this n5, every path has 2 black nodes. Okay, likewise, what's the black height of this node? 1. Okay, because there's just one. Black height of this node is 1, right? And what is the black height of the root? Which is 2. So if you go from any path from the root to the leaves, recall the black height has to be 2. You will encounter, without counting the root, you would encounter 2 other black nodes. Okay, so in blue I have written down the black height of every node, and therefore for any node and for any path from that node to a leaf, the number of black nodes you encounter along that path is constant, and that constant is called the black height of a node. Okay, so it's a very important concept, and this is what is going to make things work. All right, so very good. So binary search tree with red or black information along each node, and this 3 rules: root and leaves must be black, every red node has 2 black children, and black height is well defined for each node. So let me give you some examples of non-red black trees. Okay, so let's take a look at this example. So I claim this is not a red black tree. Can you see why it's not? So let's look at the 3 rules. Number 1, root and leaves are black. Can you see whether that rule holds? Number 2, every red node must have 2 black children. What do you think? That works. Number 3, black height of each node is well defined. Now this is where I think things will go wrong. Okay, let's look at the black height. I'm going to write them out in blue. 1, 1, 1. Okay, black height of this is also 1. Now the problem with is the black height of this node. Let me call it n. What's the black height of n? So I claim black height of n is not well defined. Why is that? So let's take a look. So if you look at n, what happens to its black height? Okay, so if you look at n, the problem with n is that if you go, let's take one path. Okay, let's take a path in green. Okay, if I take the green path, how many black nodes are there along the green path? Exactly one black node, which is the nil. That's the only black node. Let's take another path. Okay, going all to the right. How many black nodes are there? 1, 2. So there are, if I go this way, there are 2 black nodes. If I go this way, there is 1 black node. So you look at it, it clearly does not satisfy the third property, which is the number of black nodes on any path from a node to the leaf is not constant. And now that it's not constant for n, you can see that it's not constant for the root either, because from the root, if I go this way or if I go this way, you see there is a problem. All right. So even though I say the property must hold at every node, it's the same as saying the property must hold at the leaf, but don't worry about that. You can see that n here is the problem. And the property that's violated is property number 3, which does not hold. Okay, so now that you have seen how the 3 rules of a binary search tree, let us prove the following fact. Any red-black tree with n nodes, okay, so think of a red-black tree with n nodes. The height of the tree okay, let's call it h, must satisfy the following inequality. H can only be between log n and twice log n. Okay, so interestingly, the height of a red-black tree cannot be more than twice log n. So you will never get a red-black tree like that. You will never get a completely unbalanced red-black tree. So let us take an example, right? So let us take 4, 1, 2, 3, okay? And let's put nil, 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 nil. I challenge you, come up with colors for the nodes. To make the red-black tree property hold. And what you will find is it is not possible. Okay, so it is not possible to make the red-black tree property hold. All right, so now let's try and understand why this is the case. Okay, so we saw empirically, so you can never have an unbalanced red-black tree. Even with 3 nodes, there is no way to color things red and black to make the red-black property hold, because you will see that the black height of the tree will never work out. All right. Okay, so let us see the proof of this theorem. All right, proof. Okay, now let me provide you the argument for why a red-black tree cannot get too imbalanced. All right, let's take a red-black tree, okay, with n nodes. N is the number of nodes, and h is the height of the tree. So what is the height of a tree? Remember, height of the tree is the longest path from the root to some leaf. So there are h nodes on this path. All right. So if you have a tree of height h, okay, and there are h nodes along this path, and let's say this is the longest path. All right. Let's look at any other path in the tree. Let's look at any random path other than this. Okay, so here is an example. Let's take any other path. Okay, now what can the length of this path be? All right, So since h is the longest path, let's call the length of this path L. Okay. Now I can know that L is less than equal to h. Why is that? Because h is the longest path. Okay, so this is the longest. So if you took any other path, it better be less than equal to h. Now it cannot be more than h by 2. Why is that? Because in the worst case, if I looked at the red nodes in the longest path, okay, so the idea here is if I had the longest path, then at least half the nodes on this path, so at least half the nodes on this path okay, so at least half of them are going to be black. So at least half of them are going to be black. So if I looked at the longest path and any other path L, okay, from the root to the leaf, L cannot be more than h because h is the longest path, but L cannot be less than h by 2. Okay, so if you look at the imbalance between the shortest possible path in the tree and the longest possible path, they cannot be more than a factor of 2 out of each other. So if the shortest possible path was, like, let's say this was all black, and let's say this had 20 nodes, then this path here can have at most 40 nodes. Okay, and by the way, what's the black height then? The black height would be simply half of h, okay, the number of black nodes, and that has to be the same, and that's why you cannot have more than 40 here, because here half the nodes can be red, half the nodes can be red, but the other half you have to have 20 black nodes. All right, I hope this part of the argument is clear. All right, now the second thing is, suppose I had a node whose black height was bh. So suppose I had a node whose black height was bh. Then if I looked at the subtree under this node, then the subtree has to have greater than or equal to 2 to the black height minus 1 nodes. Okay, and this is easy to prove. This is because if you just look at the black nodes, you find that it's almost perfectly balanced. Okay, if you delete the red nodes and just look at the black nodes, you find it's almost perfectly balanced. So you can prove this. So you can prove this by induction. So if you take any tree and if you look at the root, if you look at everything under the root, then the total number of nodes in the tree, n, must be greater than 2 to the power the black height of the root minus 1. So if the root has black height bh, then that's 2 to the power black height minus 1. If you look at the height of the tree, the longest path, the height must be at least, so the black height and the height must be related like this. So the black height must be more than height divided by 2. Okay, so therefore n must be more than 2 to the power height divided by 2 minus 1. And therefore the height must be less than equal to log to the base 2 of n plus 1, twice of that. Okay, so this is just taking this relation, taking log on both sides and rearranging. Okay, so we have proved that if you have a red-black tree, the number of nodes n and the height of the tree must satisfy this relation that the height cannot be more than twice log n. And in the worst case, every node in the tree is black. Sorry, in the best case, every node in the tree is black, in which case the tree is perfectly balanced and you get this. It cannot, the height has to be at least log n, and it can be at most twice log n plus 1. All right, so therefore height of a red-black tree is theta log n. So perfectly balanced tree, the height is log n. Red-black tree, it's about somewhere between log n and twice log n. So red-black tree is, its balance is about factor of 2 more than perfectly balanced. So therefore if n is about 10 to the 7, log to the base 2 n is about 22. 2 log to the base 2 n is about 44. So even if you say the height of the tree is 44, that's not too bad. 44 operations versus 22 operations. Whereas in the worst case, a binary search tree could be 10 to the power 7. So red-black trees aren't going to be absolutely perfect in terms of balance, but they come in within a factor of 2 of log n, which is excellent balance. Okay, so therefore, what do we learn? So we learn that if you can satisfy 3 rules, root and leaves are black, every red node has 2 black children, and because of that you get this relation between black height and height. You get that black height must be greater than or equal to height divided by 2. Okay, and then black height is well defined everywhere. That is important. Because of these 3 properties, because of these 3 properties imply that the height of the tree must be less than twice log n plus 1. We simply say equals theta log n, and that's why you get balance. All right, so this is I will conclude this part of the red-black tree here. In the next part, we'll look at basically how operations like insert and delete can be done while the 3 important properties are maintained. Okay, see you then. Bye. Okay, so now we'll talk about operations on red-black trees. So what are the operations on red-black trees? Operations are going to be the usual operations: find, insert a key, find if a key exists, and delete a key. Okay, so what is the main idea behind find? It's going to be the same as binary search tree, exactly the same as binary search tree. Why is that? Because red-black trees also are binary search trees. Because red-black trees are binary search trees, find is going to be the same as binary search trees, except that unlike binary search trees, I can guarantee that finding an element will take theta log n worst case. And you should know the reason why this is the case, because remember, for any binary search tree, find takes theta of the height of the tree, and for a red-black tree, height itself is theta log n. So combining the two, you get this complexity of a find is theta log n. So this is the reason why we are interested in balance in the first place. So in a self-balancing tree, you can do operations like find rather fast. Now let's talk about the insert operation. All right. So what's the insert operation? So in a tree, okay, so suppose you have a red-black tree like the one shown here. All right. By the way, make sure that this satisfies the 3 important properties of a red-black tree. The root is black, the leaves are black, every red node has black children, and finally the black height is the same, is well defined for every node. Okay, so make sure all those properties hold. All right, as an exercise, also try to compute the black height for each of the nodes in the tree. All right, I hope you are able to do all of that and verify. All right, now let's say we are doing an insert and we want to insert a new key. Okay, so the way this works is you are going to try and actually find the key. So you're going to search for that key, but because the key doesn't exist and you're inserting it, you're going to end up at some leaf. And let's say you end up right here, okay, at this leaf. Now what you're going to do is the leaf is going to get deleted and you're going to get the newly inserted node. All right. Now the question is, what color? So this part is okay. So this part follows the same algorithm as binary search tree. Number 1, first same algorithm, original binary search tree without the red-black. But there is a key important point. Okay, so there is a key important point. What color do we give this node. And in this example, let me illustrate this. Suppose I colored it red. The problem is, if I colored it red, then I have what is called a red-red violation. And the reason is, I colored a node red and its parent is red. So a red node has a red child. Okay, so here is a red node, here is a red child. Okay, so if I colored it red, I get a red-red violation. What happens if I color it black? What happens if I color it black? Well, if I color it black, you will find that the black height at some nodes, like for example, the node that I'm pointing to here, the black height becomes ill-defined because you'll have different number of black nodes on different paths. All right, so for example, this path, the blue path, will have different number of black nodes than the yellow path. All right, so if I color it black, so I cannot color it red, I cannot color it black, so I have a problem. And the problem is, after insertion, how do I maintain or how do I restore the broken red-black property? All right, so this is important. All right, how do I restore the broken red-black property after I insert? All right, okay, so here is the basic idea. So red-black tree, insert. All right, so the first thing is, whatever node I insert is always colored red. Okay, so number one, so whatever node I insert is always going to be colored red. So for example, let me draw a red-black tree, and let me illustrate this in a second. Okay, so here I have shown you a red-black tree in green. All right, the nodes that are colored red, I have shown you red, and then the newly inserted node, and remember, this is always going to replace a leaf, so it's going to be at the very bottom always by the BST insertion algorithm. So the newly inserted node, I show it in blue, and following this rule, it's always colored red. All right, so number one, if I am lucky, okay, the parent, and let me call this new node X, parent of X is colored black. If the parent of X is colored black, okay, so if the parent of X is colored black, so this is case one, okay, then basically there is nothing that remains to be done. We are home free. Why is that? First of all, if the parent is black, all right, so this is not the situation you see in this example, so let me try and illustrate this situation. All right, so here is an very simple red-black tree here. Let's say we have nil, very, very simple. And then the newly inserted node is right here, and it's colored red. Okay, so in this case, let's say the parent is black. So first of all, if the parent is black, then the red violation doesn't occur. So I don't have, like in this case, you have a red violation because the parent of a node is red and the node itself is red. Okay, so that violates one of the rules of a red-black tree. Whereas if the parent is black, there is no red violation. And furthermore, the black height of existing nodes, it's unaltered. So inserting a red node here does not change the black height of one of the other nodes. So for example, let me call this node X, let me call its parent Y. Okay, so what is Y's black height? Y's black height used to be 1 and it still remains 1. Okay, the root's black height used to be 2 and it still remains 2. So every node's black height remains unaltered and you don't get a black height violation. So in case 1, when I'm inserting a new node and its parent is already red, it's already black. If the parent of X is already black, colored black, nothing else needs to be done. So this is the lucky case. On the other hand, in the unlucky case, what happens is that the parent is red. So this is unlucky. Okay, I mean slightly unlucky, so I don't want to call this unlucky, but this is the case that we are really concerned about, when the parent of the node that you have inserted is already red, so you are causing a violation called a red-red violation. Okay, how do you fix this red-red violation? So here is the idea. So here is the situation. So I have a red-black tree. I am inserting a new node like that. Okay. And unfortunately, the newly inserted node, let me call it X, and its parent Y. Okay, so let me all right, and let's say the parent has something hanging off to the right. All right, so this is called a red, and there's something up here. Okay, this is called a red-red violation. Okay, so now what is one of the cases is, let's look at the grandparent. So if you look at the grandparent, so for example, if the parent is the root, so if Y is the root, then this cannot happen, right? So a root cannot be red, the root has to be black, so the parent cannot be the root. So Y cannot be the root. So there is a grandparent. There is a grandparent. Let's call this grandparent Z. All right. And the grandparent has another child. Okay. And let's say this child is red. So, so I'm going to use family relations. So let's call this for the lack of a better term, let's call this the uncle. Okay. So X has a red uncle. Okay, so the grandparent Z is black, Y is red, and the uncle is red. Okay, let's call the uncle W. All right, now we have a trick. What is the trick? The trick is this. So what we can do in this case, if X has a red uncle, so this is case 2, what we can do is we can recolor the tree, and we recolor the tree like this. So what we do is we take Y and W and color them black, and we color Z red. So what we do is we take Z, we change the color of Z to red. Okay, and then we take Y and W and make them black, and X can remain red. So now what happens is we took a black node here, Z used to be black, and we made it red. And to compensate, if you did that, then the black height is going to change. So to compensate for the change in black height, you make Y and W both black. All right. So as a result, what happens is, even though the black height of Z increases, the black height of everything above Z does not change. All right. So every ancestor of Z still has the same black height, because I took on every path, I took one black node and made it red. I took one red node and made it black. So interestingly enough, I solved the red-red violation. So I solved the red-red violation between Y and X. And what happens is I do not affect the black height of any node other than Z. Okay, so Z's black height increases by 1. But other than that, I don't affect the black height of any other node. But there is a problem. Okay, if I made Z red, what could happen is Z's parent could have been red. So then I have yet another red-red violation. But this is a recursive case. So I can now solve this recursively. And what happens is, think of this like a toothpaste tube. So it's like you have a tube with toothpaste in it, and think of the red violation as the toothpaste at the bottom of the tube. You're pushing this toothpaste up to the top, and it comes out at the root. All right, so if Z became the root of the tree, then what you would do is simply recolor it black and you're done. All right, so even though I may have a red violation, what happens is I solve a red violation lower in the tree, and I may have a red violation a little bit up in the tree. All right, so this is case 2 of insert, where X has a red uncle. So the last case, which is case 3, okay, case 3 is this case. All right, so the next case is when W, the uncle, okay, that's just a joke, the uncle is colored black. Now, if the uncle is colored black, unfortunately, I cannot take Z, make it red, and make Y and W red. That's going to mess up with the black height. Okay, so in this case, what we do is we perform an operation called a tree rotation. Okay, so what is a tree rotation? So in this case, what happens is we are going to do a tree rotation, and so there are 2 types of tree rotation. So let me first talk about tree rotations. So there are 2 types of tree rotations. Okay, so if you have a node X, if you had a node Y, okay, so we reversed order here. Let's call this subtree alpha, let's call this subtree beta, and let's call this subtree gamma. Okay, so there are 2 types of rotation. So one kind of rotation is called a right rotation. So what's a right rotation? So if I did a right rotation, what happens is X comes up, Y becomes the right child of X. Okay, and then what happens to the children of X? Well, alpha, so the subtree that used to be the left of X, will still remain to the left of X, but beta is now going to become the left child of Y, and gamma is going to be like that. Okay, so you can actually verify that this preserves all the properties of red-black tree. So suppose the value of X was V, then everything in alpha is less than V. Everything in beta is greater than V. Okay, suppose the value at Y was, let's call it U, then, well, everything in Z and gamma must be greater than U. So let us make sure that these continue to hold. So the value at X is V, the value at Y is U. By the way, V is less than U, all right, or U is greater than V, same thing. All right, so therefore this is correct. Y must be the right child. Everything here is less than V, that's correct. Beta, so okay, so beta, is it in the right place? Well, remember, it used to be to the left of U, so everything in beta is also less than U and greater than V. So less than U, greater than V. Okay, so therefore it's in the right of V and to the left of U. So this is correct. And gamma, everything is greater than U, so it's to the right. Okay, so if you remember this whole thing, this right rotation works. All right, so what is right rotation? So I hate this term right rotation because right and left, I tend to mix them up. But the way to remember this is clockwise rotation. All right, so the reverse of right rotation is called left rotation. So in left rotation, you have the following situation. So you have your parent Y, the node X. All right, now same thing. So let's have let's call this alpha, let's call this beta, let's call this gamma. So in left rotation, it's now going to be anti-clockwise. All right, x is going to come to the top, y is going to become the left child of x, alpha is going to remain to the left of y. Okay, now beta is going to end up here and gamma is going to end up here. So this is called the left rotation. And in fact, if you now right rotate y, so if you left rotate x, you get this. If you right rotate y, you get back to the original thing. All right, so these are important operations, left rotation and right rotation. How are they implemented? So they are simply implemented through pointer swaps. Okay, and hopefully you will learn, once you learn how to write a tree data structure in a programming language like Python or C++ in your data structures class, you will learn how to implement left and right rotations. All right, okay, so very good. So let us go back to red black tree insert. Okay, so this is the situation we ended up in. So we have the newly inserted, which is red. We had its parent, which is red. Okay, so now you have the red violation. Okay, and unfortunately the grandparent has to be black, Z has to be black, but unfortunately W is black as well. Okay, so in this situation, the way to fix it is by rotating. So we do a rotation. Okay, so when you do a rotation, you get to the following case. All right, so what case do you get to? So you get to this case. So now Y comes up. Okay, so Y comes up and it will be colored black. All right, what will happen to Z? Z will become the right child of Y. Okay, so Z goes here. Okay, and W, everything W and all of that is to the right of Z. All right, so let's call this beta. So beta goes here. Okay, and X goes here, and everything below X. Okay, so and this is through right rotation. Okay, and what are the new colors? The new colors are going to be, well, I'm going to give X a red and Z is also going to be a red. All right, and what will happen here is the black height of W, so the black height of Z in the old situation and the black height of Y in this new situation, they are going to be the same. All right, and furthermore, we will find that the black height remains balanced, so we are not going to change the black height. So W is still going to come here. Okay, and what you will find is everything is fine now. The red violation has vanished and the black height remains balanced. All right, so nothing more needs to be done. All right, and there is one last painful situation, and in this painful situation, so we assumed here that X was to the left of Y. So what happens if instead you had the following painful situation where you had Y, okay, and you had X here. Okay, so this is the newly inserted node X. So this is still the uncle. Okay, but unfortunately you don't have X to be the left child of Y, which is the left child of G, X, so you have left and right here. So in this situation, what you first do, and then there is a red. Okay, so what you first do is you first do a left rotation and you would get to this situation up here, and then you do a right rotation. So this is all covered in the book. Okay, now what's the bottom line? What's the bottom line? Lots of cases. What are the cases? Well, you are inserting a new node. The new node inserted is always a red and its parent is black. So this is X and this is Y. So in that case, all clear. So this is case 1. Okay, case 2, Well, the parent is not black, the parent is also red. So the newly inserted node is X, the parent is Y, okay, and nil, nil, okay. But fortunately, let's say the grandparent Z, there has to be black, and let's say the uncle W is red. All right. So in this situation, there is an easy fix. Well, there is a fix where I color Z red. So now Z becomes red, and Y and W become black, and X continues to be red. So in which case, the red-red violation near leaf is pushed one level up. Potentially. Because it depends on the color of the parent of Z. So now we are pushing the red-red violation, if at all, to the parent of Z, which I didn't think about before. All right. So in which case you will recursively try to eliminate that red-red violation. But you have solved the red-red violation locally. That's case 2. Case 3 is you have Z, Y, X, W, okay. Now the colors are like this. X and Y are red, and W here is black. So what you will have to do is you do a right rotation, and Y comes up. It becomes a black node, and then X and Z are here, and they are both now red. And what you will have is W gets pushed down. All right, so then you do the same thing for a right rotation. All right, and then there is a sub case, which is if you don't have Y as the left child and X as the left child of Y, if you have the zigzag situation. So in that case, you have a situation like this. Okay. And you still have the red-red violation. Well, in this case, I first do a left rotation here at Y, convert it to the case 3 above, and then do the right rotation. So this is all covered in the book. The problem is, how do I remember this? And my solution to this is don't try. So remember the principles. And if you ever need to just look up the pseudocode from the book. Okay, so I'm never going to ask you to remember something as complicated as insert, and if you thought insert is complicated, delete is even more complicated. So again, it's the same principle. You do a delete as if it were a binary search tree, and then you try to fix the properties and restore the properties. So the good news, that something to note is that, okay, so the two things to note is that insert and delete both have complexity theta log n. Okay, and the main trouble is to fix up or repair the red-black tree properties after we are done inserting or deleting. And that's the most important part. And because of this, there are tons of cases and you have to look through all of them. And it's usually recall the principle, and look up the pseudocode if needed. Okay, so that is mostly it for red black trees. I'm not going to ask you to remember how to insert, how to delete, remember the details. I would ask you to remember a few things. I would ask you to remember left and right rotations of trees, which is important. I would ask you to remember the basic idea behind insert. The fact that the inserted node is going to be red, okay, you get something called a red-red violation. There are some easy cases where the violation gets resolved, and then there are some slightly harder cases. Okay, so that's the basic idea behind insert. I'm not going to bother you too much with delete. All right, so this has been a presentation of red-black trees, and mostly I have focused on understanding the principles, trying to give you a flavor of how insert and delete work, but I'm not going to go deeper into this because this is going to be something where you understand the principle, and if needed, you're going to implement it by looking through the book. All right, if you understood the principle, then you can look up the book any day and it will start to make sense. All right, so hopefully if that's good, in the next lecture we will look at some easier alternatives that are slightly less performant but still much easier to implement. See you then. Bye.
Hello, and welcome to this lecture. We are going to be talking about a very interesting data structure called skip lists. Okay, and skip lists are interesting because of many reasons. These are extremely interesting alternatives to balanced binary search tree data structure, to balanced trees. So we are going to be talking about that, and much easier to remember what they are and implement when compared to something more complicated like a red black tree. So we're going to be talking about that. And secondly, they are a randomized data structure. So they're going to be randomized. So they're going to be using probabilities to get excellent average case performance. So it's a very cool randomized algorithm. Okay, so it's a randomized data structure. All right. And last but not least, the skip lists are interesting ideas, and they probably will give rise to more interesting ideas. So it's a good thing to study interesting ideas sometimes for their own sake. And I always think of skip lists as a very interesting and simple data structure idea that's very nice to learn about. And so maybe 3 reasons to learn skip lists. All right. Who invented skip lists? Just a small note about that. Skip lists were invented by Bill Pugh, who's a very who has made lots of contributions to computer science, including contributions to the Java virtual machine, contributions to programming languages, software engineering, and this is one of the reasons we know about Bill Pugh's contributions. All right. So, what is a skip list? As I mentioned, it's an alternative to a balanced binary tree data structure. So what does that mean? That means that it's going to support insertion. So it's going to support insertion efficiently. It's going to support the search for a key. It's going to support delete. And it's going to help us iterate through all the items in some kind of a sorted order. So, so these are the operations. I should also mention that certain operations like finding the minimum is quite easy in a skip list. So it can also serve as an alternative to heaps. And so on. So it can do, like, for example, order one, find min. It can also do find max quite easily. Okay, things of this nature. So you can find the minimum element, the maximum element, and all of that quite easily, as you will see in a second why that's the case. Okay, it's also a randomized data structure, which means that it's going to provide probabilistic guarantees, not precise guarantees. The worst case for a skip list will be it will run forever, which is not very interesting, but it's going to be providing us probabilistic guarantees. All right. And it's an elegant approach to data structure design. All reasons I mentioned previously, just reiterating them on this slide. Okay, very good. So let's talk about the basic idea of skip lists. And to me, a skip list is very much based on a subway system or a train system where there are express trains. So suppose you have a bunch of stations on a train. So you have a bunch of stations, right? You have a bunch of stations, and here is the Manhattan subway system. So you have a bunch of stations. Express train is going to stop at some of these stations. Let's say it's going to stop at these stations. So suppose you want to get to somewhere in the middle that's not served by an express train. So what you would do is you would take an express train until some station, like the closest station that the express train serves, and then from there on you would continue your journey in a local train. And doing so, you would have arrived the fastest. So this is a combination of taking an express train and then taking a local train. Okay. Now, this is this idea translated to data structures, number one, translated to data structures. And number two, there are going to be many levels of express trains. So there are going to be many levels of express trains. Okay. And if you combine these two ideas, voila, you end up with a skip list. All right. So without any further ado, here is a skip list. So a skip list data structure is basically going to be, you can think of it as a bunch of lists. And at the bottom level, we have the entire data structure here. So these are all the elements that are going to be in our data structure, and they are going to be in the bottommost layer. All right. And for convenience, we put two sentinels, minus infinity and plus infinity, to mark the ends of each layer. Now, on top of the bottom layer, and so imagine these as all your local train stations. All your train stations are here at the bottommost layer. Now, one layer above, you will see there are going to be some of these stations. So one layer above, you have the next layer above, and you find that there is a subset of the stations in this next layer above. So here you have 5, 12, 25, and 37. All right, so you have 4 of these stations in the layer above. All right, so that's good. So one layer above, you have express. And then a layer above, you have a subset of the layer below. So there is one more layer above. And in the topmost layer, you have just one. All right. So this is the basic idea behind a skip list, which is you have these layers on the top, which are going to allow you, and these are going to be, think of these as your express trains. Think of these as your express layers. And then you have your less express layers until you go to the bottom in where you have every element. So, and then you have two types of pointers. You have a pointer to the next node here. You have a pointer to the next node, a pointer to the next node. So these are right pointers. And then you have a pointer to the same element a level below. And these are your down pointers. So you're going to have 2 pointers, your right pointers and your down pointers. All right. Now, the basic idea is this. Suppose I want to get, and you start always from the top layer, and the leftmost sentinel, which is the minus infinity. All right. Another thing to notice is each layer is sorted in ascending order. In this example, it's sorted in ascending order, and that's important. So one thing, many layers. Each layer has a subset of the elements in the layer below. Bottom layer has all the elements in the data structure, and each layer is sorted. Last but not least, in some order, remember there's going to be down pointers to the layer below and right pointers to the next biggest element in that layer. All right, I hope these are all clear. If these are all clear, then let's consider a simple example of how do we use a skip list, and let's say get to this node, 22. So our goal is to get here. And imagine skip list is like a train system. How do we get to 22? All right. And that's the idea. So let's talk about that. Okay. So how is that going to happen? Let me just get rid of some of these things. Oops, not all of these things. I just wanted some of these things to be gotten rid of. All right. This should be enough. So here is how we do it. So suppose I wanted to get to 22. That's my goal. I start from the top and I get to 12. Well, 12 is still smaller than 22, so I'll keep going. if I went a little bit farther, then I get to infinity. That's too far. So if you think about this, then the only choice I have is to go down from 12. So I go down from 12, and now I am one layer below, and I go one to the right. Now I get to 37, but that's too far. So I backtrack and I come back to 12 here. I go one layer below. I get down. Okay, I get to 25. That's too far. That's larger than my target 22. So I come down, and then now I'm at 12, and I go right 18, and I go right 22. So I go from 12 down, 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 and right. Okay. For instance, suppose I wanted to get to 31. Let's do this. Suppose my target is to get here to 31. Again, I go to 12, and then I take one more step. Well, that's too far. Let's go back to 12. I take to 12, I go to 37. Well, that's too far because I'm interested in getting to 31, and 37 is bigger than 31. So go back, go down, 12, I go right, 25, that's great. Keep going, 37, too far, come back, then go down, 25, 31. So to 31, I would go like this. Okay, so this is the basic idea behind skip list, and this is how it connects to this whole idea of taking an express train, which are represented by the top layers, and the bottom layer is the local train. And the goal is to find is to get to the best way of reaching to some element. Okay, very good. So if that's clear, here is the highlight for everything that all these points that I mentioned in the previous slide. All right, so how do I get to 22 then? Again, we went through this. So you get to 12, you make the step here but then it goes too far because you are interested in finding 22. So go back, go down, and then again, try going right, too far, go back, go down, try going right, too far, go back, go right, right, and you found it. So that's how I would find 22. Just to reiterate, how do I find 8? Well, I would go out right here to 12. Well, too far, therefore go down, go right here, again 12, too far, go down, right here, I go to 5, that's great, and then go again to 12. Well, too far because 12 is more than 8. Again, backtrack, go to 5, go to 8, and I reach 8. Likewise, so hopefully this gives you an idea of how to find various elements in the tree. Now let's see if I can find 28 here. Again, I go right, then I try going right, but too far, I reach infinity, which is more than 28. Again, I go right, I go too far, 37, more than 28, go right, 25, which is less than 28, so keep going, 37, which is greater than my target, so 25, 31, oops, this is too far, this is less than, this is greater than target, this is less than target. So I conclude that the target doesn't exist, and if it were to exist, it would exist here. Okay, so that's the idea of finding an element in a linked list. So you can search for elements that exist, you will find them, or you can search for elements that do not exist, and then you will find the place. If they existed, they would have been there. Okay, so far? All right, so here is everything I said in the last slide, just summarized. Okay, now let's talk about insertion of an element into a skip list. All right, the way an element gets inserted is as follows. So first, try to find the element. So try to find the element. So in this case, I will go here. So I'll go here and I'll conclude it doesn't exist. And I know that if it exists, it has to be here, just like I said on the previous slide. Now what I do is I insert 28 here. I insert a node 28 in between 25 and 31. So far, so good. And then what is the next step is the key step. What I'm going to do is I'm going to take a coin. Okay, I'm going to take a coin and toss it. I'm going to toss a coin. If it turns up heads, I'm going to go one level up. I'm going to remember this. I'm going to remember this. And I'm going to create a node between 25 and the next node to the right. Okay, I'm going to remember that. And I'm going to toss a coin again, And if it's heads, I'm going to remember this. I'm going to create a node between 28 and 37. Now again, I toss a coin. Suppose it's tails, I stop. If it's heads, I'm going to create a node 28 again. So as long as I keep tossing a coin and it's heads, I'm going to create layers above. And don't forget to add the down pointer. Don't forget to add the down pointer. And so I'm going to augment to my linked list. Now, suppose I toss a coin and it's heads again. Now I create a fresh layer. I create a fresh layer. And I make this connection like this, like this, like this. So I'm going to create a fresh top layer with just 28. As long as I keep tossing a coin and it's heads, I keep doing this. The moment it's tail, I stop and I'm done with insert. Okay, so that's the insertion algorithm. I keep tossing a coin, and let's say the probability of heads is half, which is the probability of tails. And so as long as I keep getting a heads, I will do this. Okay, and this will give rise to a geometric distribution. You keep tossing a coin until you see your first tails, and that's a geometric distribution. So this basically summarizes the insertion algorithm, which is insert the element in the last layer while maintaining sorted order, and toss a coin with probability half of turning up heads, while latest coin turned up heads. If current layer is a top layer, then create a new layer and set it to current layer, else make the current layer point to one layer above. Create a new node in the current layer and insert it so that it's in sorted order. And to do this, we have to remember how we came down to the node. And if we remember how we came down to the node, then we can always figure out what's to the left in the layer above. Okay, and that's how we do this. Add a down pointer to the new node and keep going. Toss a coin again. So while your tossing is coming up heads, you're going to create new nodes of the same value, and you're going to create a tower of these nodes in the layers above. Okay, so this is how you're going to do insertion in the skip list. All right, and you can also see how the layers are getting formed. Okay, now what is the analysis of height? So what's the average height for every node in a skip list? So every time a node gets inserted in the skip list, then you're going to keep tossing a coin, and you're going to keep producing a version of that node in the layer above with probability p or equals half. So with half probability, you're going to do this until you get to a tails. So how many coin tosses? On an average? So expected number of coin tosses until you turn up tails is going to be summation. Okay, so let me just do it as a summation. So you could have turned up tails in the very first try, in which case this is the only layer you create. Or you could have turned up one heads and a tail, in which case you're going to create one. Or you're going to create two. Excuse me. You're going to create two. Or you're going to create three versions, which requires you to have two heads and a tail. Or you're going to have four, which requires you to have three heads and a tail, and so on ad infinitum. And this summation yields, when you solve it, is 1 by 1 minus p. This is also the expectation for a geometric random variable. Since you're all data science students, you should know that this is the expectation for a geometric random variable with success probability. In this case, actually 1 minus p, depending on success is when you stop, then it's 1 minus p. So it's 1 by 1 minus p. In this case, it's 2. So on the average, I expect to have about 2 each node to have height 2. Okay, that's the average height of each node. Okay, in the skip list. Okay, now what is the probability of exceeding height h? So suppose I have a node in the skip list that I'm inserting, and I'm inserting. What's the probability that I would have inserted at least h of these nodes or more? H or more, okay? But I have to exceed at least h. What's the probability of that? Well, the probability of that is I have to get h heads of the coin, and then I can get a tail, or I can get a heads and a tail, or I can get 2 heads and a tail. It doesn't quite matter what happens to that. Right? This is the probability of getting h heads. And when you sort this all out, okay, so this is p to the h, 1 minus p times 1 by 1 minus p, which is simply p to the h. So the probability that a skip list single skip list node has height h is p to the power h. But that's not we are asking, right? We are asking what's the probability that a skip list with n nodes has height at least h. So here we are talking about a different probability, but related. Here, suppose I have n nodes in my skip list. I have done n of my insertions, and this is the bottom layer. Now, each node is going to go up to some height. This, let's call it h1, let's call it h2, and then hn. So there's going to be some node which is going to have the longest height here. And my question is, what is the probability that at least one of these nodes has exceeded height h? So at least one node has exceeded height h. And the answer is, you can get this from something called Boole's inequality. Boole's inequality. So the probability that at least one node exceeds height h is less than or equal to the summation over I equals 1 to n, the probability that node I exceeds h. And this is called Boole's inequality. Okay, it's a standard inequality in probability. This we already just calculated. This is nothing but p to the power h. So it's summation p to the power h, or it is less than equal to n times p to the power h. Okay, so the probability that at least one node has exceeded height h is bounded above by n times p to the power h. Okay, n times p to the power h. All right. So what do we do with that? So here's what we would do with that. Okay, so we can ask, what is the probability that the height of the skip list exceeds c times log n? Why log n? Because remember, in binary search trees, we had log n as the height of a binary search tree with n leaves. So we want something similar for skip lists. So we want to know what is the probability that its height exceeds c times log n. Well, this is going to be n times, okay, n times, if you go back to the previous slide, p to the power h. So p to the power c log n. Now this is 2 and p is 1 by 2. So n by 2 to the power c log to the base 2n, which is n divided by n to the power c, or n to the power, or 1 by n to the power c minus 1. And this is an upper bound. This is an upper bound on the probability. So for example, if I say n equals 100, okay, so excuse me, oops. Suppose I say n equals 100 and c equals, let's make it a power of 2. So let's say n equals 128 and c equals 2. So I want to know what's the probability that the height of a skip list with 128 nodes exceeds twice log 128, that is like 14. Well, the answer is 1 by 128 to the power 2 minus 1, which is 1 by 128. Okay, so suppose n is a bigger number, something more reasonable, 1024, and let's say c equals 2, then this is going to be 1024. So this is 1024. That's 20. Okay, so the probability that a tree with length 1024, a skip list with 1024 exceeds height 20 is going to be 1 by 1024. What about height 30? For 3 log 10, it's going to be 1 by 1024 squared. So if c equals 3, then it's 1 by 1024 squared. That's approximately 1 in a million chance. 1 in a million chance that it's going to exceed height 20. So this is going to be great. So with high probability, height of a skip list is going to be bounded by log n to some factor. It's going to be bounded by log n to some factor. So with very high probability, the height of a skip list is logarithmic. So this is quite comparable to binary search trees. So this is comparable to binary search trees. Okay. Now the question is, what is the expected running time of finding a node in a skip list? So suppose I wanted to find a node in a skip list. What's the running time of this algorithm? Well, if you remember the find algorithm, we started like this. On the top layer, we went right until we found a node which is less than key, but then its successor was greater than key. In that case, we went down and then we went right until we still found a node which is less than key, but then its successor was greater than key. I'm not drawing the successor here. Then we went down less than equal to key until the successor was greater than key. Okay, so, and then we ended up here and then we found key. Okay, now the interesting thing is, let us consider this path, this up, down, right, down, zigzagging path. Now, one of the things in this path is you have to traverse down h levels, where h is the height of the tree. So you have to traverse down h levels, okay? And there are h down pointers. And then there are right pointers. Now the question is, how long does this go on for? Now, one of the interesting things, and let me point this out, is look at all the nodes in the middle here. My claim is we cannot have a down pointer to these nodes from the level above. No down pointers can exist. No down pointers. Why? Well, these nodes, remember, are all less than key because the layers are all arranged in strictly ascending order. Okay, so if they had down pointers, then wouldn't I have gone right one more step and come down, or two more steps and come down on the top, right? So I wouldn't have gone, I wouldn't have come down here. I would have come down here. So you can conclude that these intermediate nodes do not have down pointers. So they do not have down pointers. They only have right pointers. So you couldn't have come down from above onto these nodes. Same for here. All right. So then the question is, think of this path as going in the reverse, right? So if you go in the reverse from key back to the root, if you will, then the way this works is like this. You keep going left, you keep traversing back left. The first time you have a pointer that's coming down from a layer above, go up, keep traversing left. The first time you have a pointer coming down from above, go left. First time you have a pointer coming down from above, and then go left until you reach the root. So then the point is, the size of this depends on the size of all of these rightward segments. So the size of all of these rightward segments, let's call this x1, x2, x3, x sub h. So the size of all of these rightward segments, so summation x sub I plus h down pointers. So that is the expected time. Actually 2h, because I have to also consider these nodes from which I have to go backtrack, so plus 2h. All right. So interestingly, this 2h is depending on the height of the tree. Now, what about this x sub I? Well, each x sub I, what is on average, what is the length of these x sub i's? Well, you can say on average, each x sub I is going to be a node without where I did not go up, right? And remember, when I inserted a node, I would have created a node above it with probability half. So each node in the skip list, has a node above with probability half. And the other way around, does not have a node above with probability half as well. So it's again a geometric random variable. If you look at a node, you keep going left, if you will, until you find a node with an up pointer. And what's the probability of that? Well, you can claim that this is a geometric random variable, and the expectation of each xi is 1 by 1 minus p, which is 2. So each of these xi's is of 2. And so the whole thing in expectation has 4h, 4 times the height of the tree. And then the height of the tree itself is going to be in expectation C log n with very, so what you can now claim is that the whole thing is some factor times C log n. And that's the expected length of the path that you're going to traverse to find any node. So you can find any node in at most C log n steps. There is a way to make this more rigorous, but I will skip this for now because that requires you to know some inequalities like Chernoff's inequality, which I will skip for now. Okay, so I've already finished up all these analysis of height of a skip list. So I hope it's clear how you can find out the expected running time of the find algorithm. So to conclude, what do we know about a skip list? Well, a skip list is a data structure with many layers, okay, where each layer above is a subset of the layer below, okay, and it allows you to efficiently search in expected time log n, okay, in expected time log n, and it also allows you to solve operations like insert and delete, also in expected time log n. Okay, so those are the important things. So it has the same kinds of complexities up to a constant factor as a binary search tree, as a balanced binary search tree. One of the interesting things in a skip list is you can find minimum, maximum, and such quite easily in constant time, because the minimum is just the first element in the bottom layer, maximum is just the last element. You can iterate in a sorted order. All of those are cool, and that makes skip lists quite interesting as a data structure. So I will stop here, and we will talk about other topics, but I hope you enjoyed this presentation on skip lists. Thank you. In this lecture, we are going to talk about graphs and serve as a basic introduction to graphs, realizing that most of this should be a revision of concepts. So we are revisiting a lot of concepts you should have learned in CSCI 2824, your discrete math class, and a little bit in your discrete data structures class as well. So hopefully this is a good revision to get us started on graphs. What's a graph? Well, a graph is a very interesting object. It's a mathematical object which models a relation over a finite set, okay, a binary relation over a finite set. And typically we draw the elements of this set as vertices of this graph, also called nodes or vertices. And the arrows are the edges. Okay, so this is an example where the set of vertices or the set of nodes is the set V1, V2, V3, V4, and the set of edges V1, V2, V2, V1, V1, V3, V1, V4, V2, V3. That's it. Oh, V2, V4. All right. Typically, there are two things that we don't consider, typically do not consider. We do not consider self loops in graphs. Like that. Okay. So our graphs generally do not have self loops in this class. Even though we can handle self loops, it's just a question of do we handle it? No, generally our algorithms don't work on self loops. The other thing some graphs may have are multi-edges, and we don't have that. So we cannot have multiple edges between two nodes. You can just either have an edge or not have an edge. All right. And the other concept you might have learned is the difference between a directed graph and an undirected graph, which is a very important concept. So in a directed graph, the edges between the nodes have direction. In an undirected graph, the edges are considered directionless, or better still, bidirectional, which means that you can think of this as a graph where every edge is a two-way edge. If you have an edge from V1 to V2, you also have the edge going back. And typically then we do not draw the arrow. We simply draw a straight line without an arrow to denote that it's an undirected graph. So in terms of relations, an undirected graph would become a symmetric relation. Okay, so hopefully these concepts were clear to you. Where do graphs come from, and why are they important? Where do graphs come from? Okay, and that's a very important question, because graphs are a very important data structure, and you might have already learned where they come from. Computer networks are graphs. In a computer network, these are servers and these are links, communication links between servers, and that forms a computer network. Social networks, where the nodes are people and the edges are relations. So that could be a customer-client relationship. It could be a friendship, so on and so forth. And then you get different types of social networks. This could be ecological networks. In an ecological network, these could be species of animals, and these could be predator-prey relationships. What other kinds of networks do we get? They could be electrical circuits. The nodes are junctions and the edges are wires. All right, they could be programs. There are multiple graphs that come out of programs. The nodes could be variables, the edges could be data dependencies, the nodes could be control locations in the program, the edges could be control flow. You get different kinds of graphs like control flow graphs, data flow graphs, and so on. All right, so graphs come about in a lot of places, and we often wish to perform operations and run algorithms on graphs. Oh, by the way, the Google Maps, roads, street addresses. Okay, so there's plenty of graphs, and we would like to solve problems on graphs. What are the kinds of problems we would like to solve? There are many kinds of problems, starting with traversal problems, identifying cycles in graphs, ranking the nodes in graph. What else? Finding shortest paths. Finding spanning trees. You will find there's very important applications to finding what are called spanning trees, and we'll talk about this. Flows on graphs. Okay, very, very important problems. All right, so with all of these, you really need to understand how to represent graphs, how to run algorithms on graphs. All right, so first question is, how do we represent graphs on a computer? So how do we represent graphs on a computer? So you should already either know this, or you will study this very soon in your data structures class. If you haven't already taken it, you will study this very soon, and that's where you will explore these ideas a little bit better. But for the purposes of this class, there are many representations of graphs, and the complexity of the algorithms will depend on what representation you start with. The simplest representation is called an adjacency matrix. In an adjacency matrix, a graph is just defined by a matrix where the vertices form the rows and the vertices also form the columns. If there is an edge between ni and n sub j, you place a 1 entry for I comma j. So this means that edge from n sub 2 in this case, let's call this n sub j, to n sub j. So in general, the I comma jth entry says, is there an edge n sub I, n sub j in the graph, in the edge set of the graph. All right, and if there is, you place a 1 there. If there isn't, you place a 0 there. So it's a matrix of zeros and ones, and this is called the adjacency matrix. And if there are k vertices in the graph, the size of this representation is k squared. Okay, and often graphs have lots of vertices and very few edges. This is the case in many of the graphs that I have listed here. So for example, computer networks, if you think about the internet, there are billions of vertices on the internet, but there aren't billions of communication links. Each vertex is connected to very few other, relatively few other computers with a physical link. All right, so this is an example. Social networks, there are millions of or billions of people on Facebook, but each person has a few hundred friends, right? So each person could be friends with a billion people. But no, we are not friends with a billion people, except maybe for Mark Zuckerberg. The rest of us are friends with maybe a few hundred to a few thousand people, okay? Or a few tens of thousands of people if you're really, really, really social. Maybe really, 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 really social, then you are friends with about 10,000 of people, or if you are a celebrity. Otherwise, you are friends with about 1,000 people, beyond which I wonder what the term friend means. All right, ecological networks. There are tons of species, thousands or tens of thousands of species on the planet, but not every species has a predator-prey relationship. We have a set of foods that we eat. So if we are the predator, then our prey consists of, let's say, chicken and lamb and so on and so forth. But it's not every species on the planet. Well, unless you are someone who does eat every species on the planet, which hopefully you aren't, right? So what you see is that these graphs in the world generally have what's called sparsity structure. So even though a graph with k nodes can have up to k times k minus 1 edges, okay? So that's the maximum number of edges that a directed graph with k nodes can have. Real graphs have much, much, much fewer edges than this big maximum number. What does that mean for an adjacency matrix? Which means that most of this matrix is zeros. Very few entries of this matrix is 1. So a lot of space in this matrix is wasted in just storing zeros, okay? And very few of them are ones. So there's a different representation that's more commonly used because of this sparsity, and this is called the adjacency list representation. So the adjacency list representation, here we don't represent it by a matrix, we represent it by a list. So every node n1 points to a list of its neighbors, n2 points to a list of its neighbors, nk points to a list of its neighbors, or adjacent nodes, okay? What's the size of the adjacency list representation? So if your graph has, let's say k nodes and m edges, then the adjacency list is going to have one cell for every node. So there's going to be k cells. Each cell is going to point to a neighbor, but remember, a neighbor is characterized by an edge. So for every neighbor, there is an edge that defines that neighbor. So each of these entries is corresponding to an edge in the graph. So the total number of cells is k plus m, k cells for each of the nodes, and if you add up all the sizes of the list hanging off of each of the nodes, that gives you the number of edges. So you have k plus m, or the number of vertices plus the number of edges, which in many cases can be much smaller than the adjacency matrix representation. So this is a win if your graph is sparse. Okay, so then you represent your graph using an adjacency list representation. Now there are other representations. There's a very, very popular representation called the incidence matrix representation, and of course the incidence matrix representation has some linear algebraic properties. It gives rise to something called the graph Laplacian and so on. We'll not talk about that. Let's just stop with adjacency matrix and adjacency list, noting that there are some other representations which are also important for certain kinds of algorithms. All right, so hopefully we are revising, and hopefully you remember all of this, or you have encountered all of this. We know what a graph is. We know why we care about graphs in computer science in general, and what are the two ways to represent a graph: an adjacency matrix and adjacency list representation. So if we understood all of this, then we are now ready to look at some algorithms on graphs. Thank you. Okay, so now we are going to talk about breadth first search. Okay, so the idea here is to do an operation over a graph called a graph traversal. So what's a graph traversal? So a graph traversal is an operation in a graph where, suppose you're given a graph. In this case, let us follow the book, and for some very unspecified reason, the book does this over undirected graphs, but you will see that this is equally applicable to directed graphs. All right, so let's take an example of a graph. And the idea here is, suppose I specify a starting point. Let's say start from 1. Okay, a traversal is going to visit nodes in the graph in some order, but traversing the graph only along edges. So I'm allowed, if I start from 1, I'm allowed to visit 2. If I'm allowed to visit 4, I'm allowed to visit 3. So every time I traverse, I take an edge in the graph and I traverse. Okay, so a traversal basically visits nodes in a graph in some order, but there's a constraint in a traversal, which is I can only visit a node once. If I visit it, I cannot visit it again. All right, there are some nodes where I may not be able to visit them. We'll talk about that later, especially if the graph is disconnected. In this case, suppose there are two nodes 8 and 9 that are completely disconnected, that are islanded from everything else, then starting from 1, there is no way I can visit 8 and 9. So I say I can visit a node at most once. I cannot visit it twice, but I may not be able to visit it. So let me accommodate for that. Okay. Number B, every node that I visit, every fresh node that I visit must traverse an edge along an ordinary already visited node. So if I visit 6, for example, it must be along an edge starting from an already visited node. all right, which means that if I'm visiting 6, I have to have already seen 5. So this is almost like exploring the unknown. So imagine I'm Marco Polo, I start from 1, well, I know that 1 is a port, so I can live here, I can sail along 1 to 2, I can reach 2, maybe I go back to 1, I can sail along 1 to 4, so I know, so I'm just exploring these nodes and adding them to my map of the known world, right? This is interesting. So why would we care about traversals? Who cares about traversals? Well, traversals are a very, very important operations on graphs. Let me tell you a company that makes its living out of traversing the web. We all know this company. It's called Google, okay? And they call it crawling the web. But the idea is the same. The web is a graph with HTML pages and links, hyperref links between the HTML pages. It's a directed graph. And the idea here is I have a bunch of seed HTML pages that I know about. So I start from the known HTML pages, take the links, outgoing links from those pages, and visit new HTML pages in some order. And ideally, I would not like to visit a node more than once. If I visit a node more than once and I don't recognize it, imagine doing a Google search for my name, and imagine how irritated you would be if my home page showed up hundreds of times just because Google crawling the web found the same page 100 times from 100 different ways of reaching my page. That's going to be bad, all right? So we don't want duplicates in this process. And the only way I can get to a node is from a HTML page that I've already seen and a link from the HTML page. Taking the target of that link, I go to a new page. All right, so it's very important to recognize that in traversals, these are going to be the constraints. All right, so in general, there are many kinds of traversals in a graph. But there are two that are really, really important. And so we are going to look at those two. And the first one among those two, and by the way, those two are breadth first search and depth first search, all right? So breadth first search and depth first search. So we are going to start with breadth first search, okay? Very good. So what is breadth first search? In breadth first search, what I'm going to do is suppose I start with the node 1 in this graph, all right? Then I look at what is adjacent to 1. So 1 is the start node. And what is adjacent to 1 are going to be 2 and 4. 2 and 4. I place them in my queue. Okay, hopefully you have seen queues, and these are kinds of queues that we'll study called LIFO queues. FIFO queues. Okay, so hopefully you have studied them in data structures. These are called FIFO queues, first in, first out. This is like the queue that you would form if you are ordering coffee, for example. The person who came in first is going to be served first. So this is the head, this is the tail. Okay, so at every step, I'm going to take the node from the head of the queue, and that's going to be 2. And I will record the fact that 2 was discovered along this edge from 1 to 2. Okay, and then I take 2 out of the queue. I take 2 out of the queue. And now I enqueue the successors of 2, which are going to be 3, and that's it. So 3. All right. So now 2 has been discovered. Now the next node to come out of the queue is 4. So 4 comes out of the queue. Okay, 4 comes out of the queue, and then what? I'm going to record the fact that I discovered 4 along this edge 1 to 4, and 4 successors join the queue. That's going to be 3 and 5. So 3, but 3 has already been visited. It's already been seen in the queue, so I'm not going to see it again. So somehow I have to remember what are the things that have already been either put in the queue or put in the queue and taken out in the past. I don't want to revisit them, so I'll have to do that. While I discuss the algorithm, the code, we will see how that's done. But for 4, I add 5 to the queue, which is the only new thing that 4 has to contribute. Next step, I take 3 out of the queue, right? So if I take 3 out of the queue, what needs to be added to the queue? Well, 6 needs to be added to the queue. And I remember that 3 was discovered along this edge from 2 to 3. All right. Now what else? Well, 5 is taken out of the queue. Its adjacent nodes are 6 and 7, but I have already recorded 6, so 7. So 5 is taken out. 5 is taken out, and I remember that 5 was discovered from along 4. Okay, and then last 6 and 7. 7 is added to the queue. 6 was already there. 6 was taken out, and I remember that 6 was seen along 3. And then 7 is taken out, and I remember that 7 was seen along 5. So this is going to be the overall depth first search, breadth first search. Okay, breadth first search. What is breadth first search doing? So breadth first search is traversing the graph like this. So starting from 1, it's looking at what are all the nodes that are discoverable one step along from 1. So those are 2 and 4. So those are visited. And then looking at 2 and 4, what's one step away from 2 and 4? Well, 3 and 5. So those are visited next. And what's one step away from 3 and 5? 6 and 7. So those are visited last. All right. So this kind of an algorithm is called breadth first search. And the important thing is this search is driven by a queue data structure, which is going to store the nodes that we are going to discover. Okay, so it's going to have a FIFO queue data structure, and that's going to define the behavior of breadth first search. All right. So how is the code for breadth first search? Well, to understand the code for breadth first search, the book has a special way of doing things with colors to nodes and so on. Let me do it in a slightly different way. Okay. So what are the attributes? So every node I'm going to store some attributes along with the node. So for every node V, I'm going to store some attributes. So pi is going to be the BFS parent. So in some sense, it's going to be, I'm going to tell you who, along which edge did I come to this node V. So for example, 2.pi will be 1, 4.pi will be 1, 3.pi will be 2. So just to know that I discovered 3 along the edge 2 to 3, 5.pi will be 4, 6.pi will be 3, 7.pi will be 5. So this is going to be a field in the data structure. So pi, it's going to be the BFS parent. All right. D is going to be the depth of the node. This is going to be interesting. So the depth of the root, let's call it 1, or let's call it 0. Okay, let's start from 0. I'll give the depth 1 to 2 and 4, 2 to 3 and 5, and 3 to 6 and 7. And we will see how this depth is created. And then I will have a Boolean called visited, which is true or false if the node is already visited. Okay, and there are a few more things you can add, but I will not worry about that. The book has a coloring scheme. I will not worry about the coloring scheme just yet. Let me just start with this. So I'm going to use this. So BFS graph G, starting from the starting node, let's call it S following the book. So I give you the graph and the node to start with. All right, so what do we do? So first of all, we initialize a queue that's only going to contain the start node. The start node's depth is going to be initialized to 0. The start node is already seen, and the start node's parent is nil. It's the root node. Okay, now while the queue is not empty, what? Well, let me dequeue a node from the queue. Let me take the node from the head of the queue. Let's call it V. Okay. Now for all, in fact, let me call it U for a reason you will see in a second. So let me call it U. Okay. So for all V that's in the adjacency of U, Okay, so for every v that's adjacent to you, so if it's 2, then the adjacencies are 3 and 1. Okay, so those are the adjacencies. All right. What do we do? Well, if v has not yet been visited, then what? Then let's do a few things. Under this if condition, let's do a few things. First, let's set the depth of v to the depth of u plus 1. So give it depth which is 1 more. Let's set the parent of v to u, just to make sure that we know through which edge did we discover v, right? Let us say that v has already been seen. What's last? Let us NQ. Let's put the node into the queue. That's it. All right. So this is the breadth first search algorithm. What does the breadth first search algorithm do? Starting from the start node S, I place that node in the queue, and then every time I take the node at the head of the queue through the dequeue operation. All right. And then I look at everything that's neighboring to it. So if I'm looking at 1, the neighbors are 2 and 4. If I'm looking at 2, the neighbors are 1 and 3. 4's neighbors are 1 and 3. Okay, so I'm looking at the neighbors. If the neighbor has not already been seen, okay, if the neighbor has not already been seen, which means v dot seen is false, then update the depth of the neighbor to be the depth of the node through which I saw the neighbor for the first time, plus 1. Update its parent to that node. Say that the node has been seen, which is true, it's been seen just now. NQ that node in the queue. That's it. Okay, and through this process, I'm going to perform breadth first search. And remember, breadth first search is characterized by 2 things. One is that this data structure that's going to keep the set of nodes to be processed is a FIFO queue. Number 1. And number 2 is whenever I see a node, I try to visit all the nodes that are adjacent to it 1 level down before I visit nodes that are 2 levels down, before I visit nodes that are 3 levels down, and so on. So breadth first search is going to go breadth wise through the graph. So starting from 1, it is first going to try and visit 2 and 4, which are going to be 1 level down. Next is going to visit 3 and 5, which are going to be 2 level down, and then it's going to visit 6 and 7, which are going to be 3 levels down. Okay, and because of this, we are going to get some very important properties of breadth first search. One important property is that if you started breadth first search from node 1, you get the shortest edge length path from 1 to a given node. How do you do that? So suppose I wanted to find out the shortest path from 1 to 6. Well, start from 6 and just look at its parents. So its parents are 2, 3. Okay, so first parent is 3. And I know that by looking at 6.pi. The second parent is 3, 2, which I know by looking at 3.pi. And then 2's parent is 1, which I know by looking at 2.pi. And 1 is the start node. So I know that to get from 1 to 6, I have to go 1 to 2, 2 to 3, and 3 to 6. Okay? And in fact, this is a path of edge length 3. And it's the shortest path from 1 to 6, assuming that all edges are equal length. And that's important assumption. But what you see is that breadth first search is also our first shortest path algorithm. Okay, so we are going to see some of the properties of breadth first search coming right up. Thank you. In this lecture, we are going to look at depth first search. Okay, so far we've seen breadth first search. And how does breadth first search work? Okay, so it can be a directed or an undirected graph. So let's take a graph like this. Let's start with some vertices. So BFS starting from vertex 1 is going to do, first it's going to visit 2, then it's going to visit 3, and these are vertices at depth 1 from the starting vertex, which is at depth 0, and then it's going to finish with vertex 4. So this is how it works, and the main structure that drives this is a queue, also known as a FIFO queue, a first in, first out queue. Okay, so hopefully you have seen this. In this lecture, we are going to look at a different kind of search called depth first search. All right. So what is depth first search? In depth first search, we are going to do things differently. So for example, starting from vertex 1, we will visit vertex 2, okay, its neighbor. But starting from vertex, instead of then visiting vertex 3, which is going breadth first, we are now going to visit the neighbor of vertex 2, come back up, and then visit vertex 3. So a depth first search is going to go 1, and then 2, and then 4, return, and then it's going to visit 3. So it's going to go depth first, seeking deeper and deeper nodes, and then it backtracks and then visits the other nodes. All right. So that is called a depth first search, and it's like breadth first search. It's very, very important. It satisfies certain properties which are going to be super important for building other algorithms on top of depth first search. All right. With that being said, let us look at how depth first search works. All right. So let me take this example, okay, this very example, and start to work out, make it bigger, and start to work out the principles of depth first search. All right. So what are some of the nice things about depth first search? All right. So first things first, let me make this example a little bit bigger. 5. Let's put an arrow there. 6, and then let's put an edge back to 5. Something like this. So let's make this example a little bit bigger. All right. And let's remove some of the superfluous stuff. Some of these annotations not needed. Okay. All right. Now we are ready. So okay, so this is the graph. All right. So a DFS visit is going to start from some node in the graph. All right. And so let's designate 1 as the starting node. It doesn't always have to be 1, but let's just designate it at the starting node. All right. So if I do a DFS visit, it's going to first visit 1. Okay. And now what it's going to do is it's going to look at the first successor of 1. So then it's going to visit 2. But instead of going back to 1, it's going to now recursively visit one of the successors of 2. And the successors of 2 are just 4. So it's going to visit 4. All right. So you're getting the idea. So it's going to visit 4. And let me write down a timestamp. So this is at time 1, at time 2, at time 3. All right. What else? When it gets to 4, it's going to visit the successor of 4, visit 5. When it gets to 5, it's going to visit 6. Now when it is at 6, it's going to try to visit 4. But the nice thing about this is 4 is already been seen. So it's already been seen, so it's not going to revisit 4, in which case it's going to return, backtrack and return. Okay. It's going to return to 5. There's nothing else for 5, it's going to return to 4. Nothing else at 4, it's going to return to 2. All right, nothing else at 2, it's going to return to 1. Well, with 1 I have visited its neighbor 2, now I'm going to visit 3. And then all the neighbors of 3 are already pre-visited, so it's going to return. So these dotted arrows are the return arrows, right? So this is going to be it. So it's going to first visit 1, 2, 3, 4, 5, backtrack, 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 visit 3, backtrack. Okay, and this is happening at this is the 6th node in the sequence to be visited. What is the code for DFS? Let's call it DFS visit. Okay, for a graph G, let's visit a node V. All right. So what are the nodes that I'm going to fill out as part of this visit? So as part of this visit, I'm going to keep a global time. Okay, so this is going to be global, somewhat icky, but initialized to 1, and it's going to be globally incremented. So it's going to be global. All right. It's a little bit of annoyance. Global variables are not always encouraged, but here we will keep it as global for convenience, all right? And we will figure out how to implement it later. All right, and then what? For every node V, I will need to fill out 3 fields. One field I will fill out is its parent, and this parent is going to tell me along which edge did I visit a particular node. So for example, 2's parent in this visit will be 1, 4's parent in this visit will be 2, and so on, and 3's parent is going to be 1. All right, so that's number 1. So I'm going to make up a parent which is initially going to be nil for everyone. Okay, then I'm going to keep something called a discovery time. When is the first time I discovered a node? And the last thing I'm going to keep something called a finish time. All right, and initially these are let's say undefined, and I'll keep a Boolean variable called seen. Initially it's false. If I have seen a node, I'm going to mark it as seen. So these are the fields or attributes of a node that are going to be useful for doing bookkeeping. Okay, and unlike the book, I am not going to assign a color to a node and so on and so forth, but the book has an excellent presentation which goes into much more detail, and I highly recommend you look through that, but I'm going to give you the idea here and then refer you to the book for the bigger details of when is a node gray or white or green and all of that stuff, all right, later. Okay, so what is the main idea behind a DFS visit? So if I am asked, starting from a given graph, given a node of the graph to visit, the first step is if the node has already been seen, then just return. There's nothing much to do. Okay, if a node has already been seen, just return. Otherwise what? Otherwise, for all adjacent, okay, so for all adjacent nodes, so what are adjacent nodes? So let me say for all, and for convenience, just to keep track with the book, I'm going to call this node U. So for all V that are adjacent to U, what does this mean? This means that there is an edge from U to V. Okay, so U is the node that I'm currently visiting, and V is the node that's adjacent. Okay, so there has to be an edge in that direction from U to V. One subtle difference is when we were doing BFS, breadth first search, we were looking at undirected graphs. Okay, and I'm not really sure why the book chose to do BFS on undirected graphs, but we will keep it that way. DFS and BFS can be done on directed graphs as well. Okay, so we are doing it on directed graphs. All right, so for all adjacent nodes, what should I do? Well, first of all, let me make sure that if V has not been seen, if V has not been seen, then, well, let's say V has been seen. V's parent, the parent that enabled me to see it, is U. So I'm going to store the parent. All right. What else am I going to store? I'm going to store the discovery time. I'm going to advance my time. Okay, so time increases every time I do something like this, time increases. What else? And then I'm going to do V. I'm going to do a DFS visit, and this is the recursive call starting from V. So here's the idea. If I visit a node U, I'm going to go to its first successor or first adjacent node V, and I'm going to start exploring the graph from V. After I'm done exploring, I come back to U, and then I go to the next successor. All right, so that is kind of important. So the idea behind DFS is if I'm at node 1, I will visit node 2, and from node 2 I will visit everything that's reachable from 2, that includes 4, 5 and 6, come back before I visit the other child, which is node 3. And when I am visiting node 3, even though 2, 4 and 5 are reachable from 3, I will not revisit them because they have already been seen. The seen marker for them will become true. All right, and then what? And then after all my children are done, I am done too. So I'm going to record the time at which I am done. So time equals time plus 1. And I'm going to say the discovery time, the finish time of u is time. So record when I finished. Okay, and in fact, I could have done the following. I didn't have to set the discovery time here. One thing I could have done, just to make the algorithm look nicer, is I could have set the discovery time here. Same thing. Because time is a global variable, you will get the same answer. Okay, time equals time plus 1, and then set u dot discovery time equals time. Okay, that looks nice and symmetric. Set discovery time, and then when you're done, set the finish time. So start your clock. When you're done, stop your clock. All right. So this is the overall algorithm for DFS visit. All right. So there are 3 or 4 things that come out of this. So first thing that we'll have to understand is that when DFS finishes running, it creates a tree. It creates a tree, just like BFS. Just like breadth first search, it creates a tree. And this tree is called the depth first search tree, DFS tree. So how do I know the DFS tree? Well, if I am in a node, I have its parent, 2.pi, and that equals 1. So that gives me the DFS tree. So 4.pi equals 2, 5.pi equals 4. So the DFS tree for this graph is going to be, in this case, 1 is connected to 2, 1 is connected to 3, and 2 is connected to 4, 5, and 6. So that's going to be the DFS tree. Note that every edge in the DFS tree is an edge in the original graph. It needs to be in the original graph. I'm just picking up some of the edges in the original graph, and that forms a tree called a DFS tree. This cannot have a cycle. Okay, these edges cannot have a cycle. All right, so that is a very important thing that DFS produces. All right, and what about the edges that did not make it in the DFS tree? So some of these edges made it, but unfortunately some of these edges are not making it in the DFS tree. So let me add the edges that made it in pink. So 2's parent is 1, so the edge 1 to 2 makes it. 3's parent is 1, so this makes it. So these are the tree edges, the edges in the DFS tree. Now there is many other types of edges. So now if I look at the edges that did not make it, what is one example? So one example is 3 to 2, 3 to 4, and 3 to 5. Okay, and another example is 6 to 4. Okay, so these are the edges that did not make it. All right, so there are names for each of these edges. All right, so there are names for each of these edges. What are the names for each of these edges? So the name for this edge going back from 6 to 4 is called a back edge. Okay, this is called a back edge, and the reason it's a back edge is because 4 is an ancestor of 6 in the tree. So whenever you have a node from a descendant back to an ancestor, it could be a parent, it could be a grandparent, great grandparent. So those kinds of edges are called back edges. So these are called back edges. Okay, these kinds of edges, and so these are 3 is neither a descendant nor an ancestor of 2. 3 and 2 are kind of siblings, right? 3 and 4 are kind of again, they are not direct descendants or direct ancestors. So these kinds of edges are called cross edges. Okay, these kinds of edges are called cross edges. All right, and there is one other type of edge. So let me add a new edge here. Let me add an edge from 1 to 6 in the original graph. So if there were an edge from 1 to 6 in the original graph, okay, then that edge is going to be like this. And this kind of an edge is called a forward edge. And this goes from an ancestor to a descendant, but not a direct child, but like a grandchild or a great grandchild in the tree. Okay, so these are the three types of edges which we will have to remember. Okay, so coming back in the next lecture, next part of this lecture actually, we are going to do a larger example of DFS. We are going to revisit this concept of forward, back, tree and cross edges, and we are going to come up with criteria for forward, back, tree and cross edges. So what are the criteria for these edges? How do I identify these edges using my discovery and finish times? And we are going to study some basic properties of DFS coming right up. So now we will look at a slightly larger example. Okay, so in this example, I have nodes 1, 2, 3, 4, 5, 6, 7 and 8. And 7 and 8 are disconnected. Okay, so how do I manage to visit all the nodes in the graph in this case? The simple answer is I cannot do that. And therefore, what I will do is I will run an outer loop that's going to do for I equals 1 to n, where n is the number of nodes in the graph. I'm going to simply call a DFS visit on the ith node. All right, that's it. Which means that would I still then revisit nodes that I have seen before? So if I'm calling a DFS visit on 1, you can see it's going to visit 4, right? It's going to visit 3, okay, and then it's going to go back to 1. Try to go back to 1, no, return, 5, 6, return, right? So it's going to visit 1, 3, 4, 5, 6. If I call it on 2, it's going to try to go back to 1. Does that mean that it will revisit the entire graph? It won't, because I've already marked 1 as being seen. So the very first line will return. Likewise, if it tries to go to 3, it will return. So as you can see, what's going to happen is that DFS is not going to visit nodes that it's already been seen. So therefore, things will work out, hopefully. All right, so I'm going to call DFS visit on every node starting from node 1. So if I start from node 1, well, 1's parent is nil. Okay. Now what's the discovery time of 1? It's being discovered at the very, very start. All right. And then it's going to try and visit node 4, which is the only node adjacent to 1. So 4's parent is going to become 1, okay, and then 4's discovery time is 2. All right. Now 4 is going to try and visit its successors. The first successor, let's say it's doing it in increasing order, so it's going to visit 3. So 3's parent is 4. Let's note that down. And then what about 3's discovery time? It's going to be 3. Okay. Now 3 successor is 1, but 1 has already been seen, so there is nothing else for 3 to do, so 3 is going to finish right away, and so its finish time is 4. Now that's going to return to 4, but 4 is not finished. 4 is still trying to do this loop, so it's going to now go to 5. So 5's discovery time is 5 and its parent is 4. Okay. Now 5 is going to call 6. 6's discovery time is 6 and its parent is 5. Okay, so the table is getting updated, and then 6 is going to finish, nothing else to do. It's going to return back to 5. Let's see. 6 is going to finish. It's going to return back to 5. It's going to return back to 5, and that's going to finish. Finish time is 8. That's going to return back to 4. 4 is done, so its finish time is 9. Okay, and that's going to return back to 1. 1 is done. Its finish time is 10. All right. So this is going to be the first run of DFS visit starting from the node 1. Okay, and hopefully, if you have a paper and pencil, you are following along. All the other values of seen are false. Now I'm going to execute this outer for loop for 2. So if I execute it for 2, what happens? Well, I go a DFS visit for 2, and its discovery time is going to be 11, and its parent is going to be nil. Okay, its discovery time is going to be 11, and it looks to visit 3, but 3's seen is already true, and 1 has already been seen. So it's going to try and visit 1 and 3, but it can't do that. So it's going to immediately return, and its finish time will become 12. Okay, and 2 has already been seen. Now what about next? the loop will run, it will run for 3, but 3 has been seen, it will run for 4, 4 has been seen, 5, 6, it's been seen. Next time it will do is 7. So 7's parent is nil, and 7's discovery time is 13. Okay, time is keeping incrementing. 7's discovery time is 13, and it is going to call 8. 8's parent is going to be 7, and its discovery time is 14. Its finish time is 15. 7's finish time is 16. And the outer loop is also done. It will try to call 8, but nothing will happen because 8 has already been seen. Okay, so this is how the entire DFS works. Now, what does the DFS tree look like? So the DFS tree is no longer, unfortunately, a tree because it's not going to be connected. So it's going to look like this: 1, 4, 3, what else? 5 and 6, 2 all alone by itself, and then 7 and 8. So those are going to be the DFS tree. And how do I know? I know it because 4.pi is 3. So therefore 3 comma 4 needs to be there. I know that 3.pi is 4, so 4 comma 3 needs to be there. I know that 4.pi is 1, so 1 comma 4 needs to be there. So by knowing the pi pointer, so the pi of 4 is 1, the pi of 3 is 4, the pi pointer of 4 is 5, like that. So the pi pointer is pointing in the reverse direction to the tree edge, okay? Now what about the edges that did not make it in the tree? So those edges, I'm going to show them in blue, are 8 to 7, 2 to 1, 2 to 3, what else? 3 to 1, and 4 to 6. So the blue ones are the ones that did not make it in the DFS tree. What kind of edges are those? Okay, so we've already learned the classification of DFS edges. So let me write down the classification. Okay, so the tree edges, we already know what they are. Tree edges are the edges that are in the tree. All right. What are the other kinds of edges? So the other kinds of edges are back edges, forward edges, and cross edges. Okay. So first things first. This is not a tree strictly speaking, because first of all it's directed. Trees have to be undirected. Okay, that's number one. But let us forget about that fact, and for the time being just assume these edges are undirected somehow. All right, and then it starts to look like a tree, except that 7 and 8 are out here hanging by themselves, and 2 is really out here hanging by itself because these blue edges are not part of the tree. Right. With that being said, it's no longer a tree. It's a forest. What is a forest? Well, a forest is a collection of trees, of course, that's a forest. Okay, so it's going to be a DFS forest, not a DFS tree, technically speaking, because your graph can be disconnected. And you can see that here. Number one. Number two, how do I classify the edges? First of all, what are back edges? So back edges are edges from a descendant to ancestor in that tree. So is there an edge that goes from some descendant to some ancestor? Yes, there is. You can see this edge from 3 to 1. It goes from a descendant in the tree to an ancestor in the tree. So the edge 3 to 1 is a back edge. There is another back edge 8 to 7. So it doesn't have to be a proper ancestor, it could be a parent. Your parent is your ancestor. So it also, there is an edge going from 8 to 7. That is a back edge. Now forward edges are edges that are going from ancestor to descendant who is not a child. Okay, if it were the child, then it's already a tree edge. Okay, so here example of a forward edge is the edge from 4 to 6. It's going from an ancestor to a descendant. So an example of a forward edge is the edge from 4 to 6. Now what about cross edges? These are edges that are going between different trees in the forest or between inside the same tree from a node that's neither a descendant nor an ancestor of the target node. Okay, examples are 2 to 3, 2 to 1. Those are the cross edges. There is another way to identify these three kinds of edges, and that is by looking at the discovery time and the finish time. Okay, and this is going to be interesting. So let us work out and see if our intuitions are correct. All right, so if your intuition about DFS is correct, you should be able to characterize these edges in terms of discovery and finish times. Shall we look at that? So a back edge, so for example from U to V is going to be like this. Okay, so this is the path that DFS takes. So from U I visit a path, I go to V, but from V I visit a path and I go to U, but then there is an edge here which is the back edge. All right, now what is happening? So first V is discovered, and then U must be discovered, and then U finishes, and then V finishes. So this is the criterion for if U comma V is a back edge, then this is the criterion. V dot discovery less than U dot discovery less than U dot finish less than V dot finish. Now what about a forward edge? So in a forward edge, the nesting property is exactly reversed. So in a forward edge, I get U's discovery. So in this case, the forward edge, let's call the source of the edge U and the target V. Okay, so this, so I'm going to always call the edge from U to V. So the forward edge, the source of the edge is discovered first, and then the destination is discovered, and then the destination is finished, and then the source is finished. Just the opposite, okay? But this is going to be nested. So this is the interval for V, and this is the interval for U. And in a forward edge, it's contained this way. In a back edge, it's just the opposite. V's interval will contain U's interval. Now what about for a cross edge? So for a cross edge, you will find out that their intervals are disjoint. U dot F, U dot D, so this interval, discovery finish interval, is disjoint from V dot D, V dot F. So let us look at this example. So here 2 to 1 is a cross edge. So if you look at 2, its interval is 11, 12. 1's interval is 110. So you can see it's actually disjoint. If you look at the forward edge from 4 to 6, you can see 4's interval is 2, 9, and that's going to contain 6's interval, which is 6, 7. So 2, 9 is the big interval, 6, 7 is the small interval. If you look at a back edge, let's say the back edge from 3 to 1, 3's interval is going to be 3, 4, 1's interval is going to be 110. 110 is the big interval, 3, 4 is the small interval. So that's the three kinds of edges you will see in a depth first search, and there are two different ways of describing them, one based on how they look in the forest, in the DFS forest, and other simply based on the discovery and finish times. Now should you remember this? Well, I think you should just try and remember the basic definition here, and then if you develop intuition for DFS, it should be a piece of cake for you to work it out yourself. I never try to remember this, I just work it out if I need to by just imagining DFS. If there is a forward edge, then imagine how DFS goes, and then imagine which node will be discovered first, which node second, which node will be finished first, which node second. For example, same for cross edge, same for back edge. So remember, there are 4 types of edges: tree edges, edges along which DFS proceeds, so those are called tree edges, back edges, forward edges, and cross edges. Okay, and these are going to be quite useful in some problems. And so one example is going to be, does a graph have a cycle? All right. So does a given graph have a cycle? And how do you know if a graph has a cycle? So what is a cycle? So for example, in this graph, 7, 8 is a cycle, or 1, 4, 3 is a cycle. So how do you find out cycles in a graph? And I'm just asking a yes no question. I'm not asking you to even tell me what the cycle is. Can you tell me if the graph has a cycle? Okay. And this is where the classification of edges comes in useful. So theorem, a graph has a cycle if and only if DFS produces a back edge. If there is a back edge, there's going to be a cycle. If there is a cycle, you will see a back edge. Can you convince yourself this is true? If there is a back edge, it represents a cycle. That's easy, right? Because you're going from the descendant of a tree to an ancestor, and that immediately means from that ancestor you go to the descendant, and descendant back to the ancestor through the back edge. So of course there's going to be a cycle. Now if there is a cycle, then DFS will discover that one of the edges in the cycle as a back edge. Now that's a very interesting property to prove, and I will leave it to you as a test of your understanding of depth first search. So this is one of the main uses of DFS. If someone gives you a graph and says, hey, is there a cycle in this graph? Can you print the cycle out? Well, the algorithm is do a DFS, okay, do a DFS, and then look for back edges in your DFS. If there are back edges, then every back edge is going to correspond to a cycle. How is that? Because the back edge and the path from the tail of that edge to the head back in the DFS tree is going to give you the cycle. Okay, this is a wonderful algorithm for you to practice when you are trying to understand DFS, which is convince yourself if there is a cycle in the graph, it needs to have a back edge, and if I do a DFS and find the back edge, I can actually tell you what nodes are involved in the cycle. All right, good. So there are further problems you can solve using depth first search, like finding bridges, finding disconnecting points, finding articulation points, and so on. And these problems are in the back of the book, and we will use them to enhance our understanding of DFS and understand why we care so much about tree edges, back edges, forward edges, and so on. All right. If that's clear, then let's move on to the next lecture, where we are going to use DFS for something important. See you then. Bye. Okay, so now we are going to come up with a very cool application of DFS, depth first search, to do something called topological sort. So what is topological sort? So often what happens is you have a, let's say, a directed acyclic graph. A directed acyclic graph, and this is also shortened as a DAG. Okay, so suppose you are given a directed acyclic graph like this. So V1, V2, V3, V5, V4, V6, something like this. All right, so what I would like to do, and let's say these are all tasks. Okay, so the vertices are tasks. V1 through V6 are the tasks we need to do. And edges denote that V2 can only be started after V1 is finished. Okay, so the edges say, okay, so you can only start V2 after V1 is finished. You can only start V3 after V1 is finished. So these edges are what are called, sometimes called dependencies. All right, so for example, let's talk about making tea. So take a cup, take a pot, a kettle, place kettle on boiler, add water to kettle, bring water to boil, place tea bag, pour water in cup, so on. Okay, add sugar. So these are going to be the steps for making milk, but let's say they are not in order. These are just the steps. So take a cup, V1, take a kettle, V2, place kettle on the boiler, V3, V4, and so on. Now there are going to be some natural dependencies. So for example, I need to finish V1 before I can pour water in the cup or place tea bag. So V6. So V1 needs to happen before either V6 or V7 needs to happen. All right. And likewise V8. V8 needs to happen only after both V6 and V7 happens. Likewise, V2 needs to happen before V3 happens, and definitely before V4 happens, before V5 happens, and so on. Okay. And then V5 needs to happen before I pour water, so V7. So you can see there is a dependency graph here, okay, where the vertices are the tasks and the edges say that some task has to be finished before some other task can be started. All right. Otherwise, we might end up just pouring water without placing a kettle on the boiler, and that's dangerous. Or we might add milk without boiling the water. We might put the tea bag in cold water. That's not going to make very good tea. All right. So we need a way by which we can, given a graph like this, a directed acyclic graph, we need to sort it. So in this case, let's put V1 first, and then V2, and maybe V5, and then V3, V4, V6, and this is called the topological sort, such that every edge goes from, so you place the vertices in ascending order such that every edge goes from a lower ranked vertex to a higher ranked vertex. So V1 to V2, V1 to V3, V2 to V5. So every edge in the graph is going from an earlier vertex in my sort to the later vertex. All right. And this can only be done if your graph is a directed acyclic graph. If your graph has a cycle, you cannot do this kind of a sort. Why is that? Let's take an example of a cycle. T1, T2, T3. Now, no matter which one I place first, one of the edges is going to go backward. So this can only work if your graph is a directed acyclic graph. So question is, given a DAG, print its topologically sorted order. How do you do it? All right. And here is the basic idea. So the basic idea is as follows. What we will do is we are going to run a DFS. So we are going to run a depth first search on this graph, trying to visit every node. So you'll have the outer loop that's going through every node and the inner loop that's going to do a DFS visit. Second step, we are simply going to sort the nodes in descending order according to their finish times. That's it. Okay, so we are going to do these two steps, which is we are going to first do a DFS, and then we are going to sort the nodes in descending order according to their finish times. And now the interesting thing is this: we can fold these two into a single DFS operation. So as you are doing DFS, as things are getting finished, we can add those nodes to the head of a list, and we can be done. So how does that work? So let us do it on this example graph that we have to see exactly how, as you are doing a DFS, you can also end up topologically sorting the graph. All right, so let me make some space for that. And let me make up the familiar table for the DFS. All right, and I'm going to just store the discovery and the finish times. Okay, and let's start the DFS, I don't know, from V1. For now, let's start it from V1. So V1 is discovered right away, and then let's go to V2. It's discovered at time 2. Then it goes to V5, which is discovered at time 3. Okay, and then that goes to V4, which is discovered at time 4. And then it goes to V6, which is discovered at time 5. And then V6 is finished at time 6. So now I'm going to have my sorted list, and I'm going to put V6. Okay, and then as V6 is finished, it's going to go back to V4. V4 is going to finish at time 7. Then I'm going to put V4 because that's the second thing to finish. All right, and then V4 is finished, then V5 finishes. So as things are finishing, put them at the head of a list, and this list is going to get my topological sort. That's all. So I'm folding these two steps in one. All right, both doing the DFS and sorting things in the reverse finish time. And the point is, I don't need to do a separate sort, because as DFS is finishing on a node, which is the very last step of DFS, just place it at the head of a list, and you're starting to reverse sort it according to the finish time. Okay, now what else? Then I return back to 2, whose finish time is 9. Okay, and then I go back to 1, but V3 remains unexplored, so I'm going to do V3, whose discovery time is going to be 10, finish time is 11, and finally to V1, whose finish time is 12. So finish time 12, 11, 9, V4, V5 is 8, 7, 6. As you can see, descending order sorted. Finish times, and that's the topological sort. So it's going to be very easy to write code for this. It's just DFS, depth first search, and as I'm finishing, I place the node at the head of a list, which effectively sorts the nodes in descending order of their finish times. And for a directed acyclic graph, this is it. This is it. Okay. Now, what happens if you are not sure if your given graph is directed acyclic? Well, whenever you see a back edge in DFS, you immediately declare that it cannot be topologically sorted. It's meaningless to topologically sort it, because a back edge corresponds to a cycle, and you should not be seeing a back edge. And that's a sanity check that you could also do. What's the total time taken for topological sort? Well, very simple. Suppose I visit every node. I'm going to visit every node exactly once, and I'm going to see every edge exactly once. So the total time is going to be theta of the number of vertices plus the number of edges. And that's going to be also the traversal, the time taken for DFS. It's just the number of vertices plus the number of edges, because if I place $1 on every edge and $1 on every vertex, I can collect the dollar on a vertex whenever it's visited. Okay, whenever I call DFS visit on it, I'll collect the dollar. And for every edge, when the vertex, I loop through all the adjacent edges, I'll collect $1. And that accounts for all the steps that I have to do. And so therefore, the total amount of money I will need is the number of vertices plus number of edges, which is the running time of DFS. And in this case, that also does topological sort. I hope this is clear. This is a very simple example of how depth first search can end up solving a very interesting and important problem. Thank you. Okay, so in this lecture, we are going to look at strongly connected components of a graph. So given a graph, okay, and we will talk about directed graph, a directed graph G, directed graph. Okay. Strongly connected components are very, very important because they are going to be a point of departure for many other constructions on graphs. So it's very important to understand what they are, define them, and figure out how we are going to use what we know already, like depth first search, to find strongly connected components. So what is a strongly connected component? So let me start with an example. So let's take an example graph. So here is an example. Okay, so here is a graph with 9 nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9 with the edges that I have shown along with the directions. And I would like to look at the strongly connected component. So what is a strongly connected component? And we call it an SCC. So an SCC is first of all a subset of vertices. Okay, so it's a subset of vertices V. All right, so as an example, 2, 3, 4, and 5 is a subset of the vertices. Number 2, for all pairs of vertices, there exists a path from Vi to Vj and vice versa. Okay, well, and vice versa, because you can always interchange the order of Vi and Vj. So let me just remove this vice versa and say for any 2 vertices that I can think of, there is a path from one of the vertices to the other. Of course, if I think of them in the reverse order, then there has to be a reverse path as well. So it follows from my definition already. And furthermore, this path must entirely lie inside S. All right. So let's start by parsing this definition. And before I parse this definition, just to make it interesting, let me add one more edge to this graph, just to make it more interesting. All right. So what is a strongly connected component? Well, first of all, it's a subset of vertices. It has to be a subset of vertices. So like 2, 3, 4, 5, or 7, 9, or another example of a subset would be, I don't know, 4, 6, something like that. All right. So here is 3 possible subsets, and let's see if it meets the definition. So for any pair of vertices, so if I choose any 2 vertices, and if they are the same vertex, then it's trivial. But if I choose 2 different vertices, let's say 2 and 5, there must be a path from 2 to 5. Is there a path from 2 to 5? 2, 3, 4, 5. Yes, of course, there is a path from 2 to 5. The path must lie entirely inside that subset. It does. 2, 3, 4, 5. As you see, the edges of the path are entirely inside the subset. So 2, 3, 4, 5. Let's take 3 to 4. Yes, there is a path from 3 to 4. Let's take 4 and 3. There is a path from 4 and 3 that's entirely inside the component. So check that S1, which is the set of vertices 2, 3, 4, 5, is an SCC. All right, easy. Now what about S2, 7 and 9? Yes, there is a path from 7, 9. There is a path from 9, 7. And the path entirely lies inside the set 7, 9. The path does not need to go out of 7, 9. So yes, it's a strongly connected component. What about 4, 6? Well, there is a path from 4, 6. But first of all, the path moves outside of the set 4, 6. So if I start from 4, I need to go to 5, which is outside this set. Number 1. And number 2 is there is no path from 6 to 4. So this is not a strongly connected component for 2 reasons. One is that if I try to go from 4 to 6, I have to move outside the set. But if I try to go from 6 to 4, then there is no path. Okay, let me give you one other example. What about the set 2, 3, 4, 5, 6, and that's it. All right. What about 2, 3, 4, 5, and 6? Well, now one of the objections is gone. So yes, there is a path from 2 to 6. There's a path from 3 to 6, 4 to 6, 5 to 6. And these paths entirely lie inside the set. But there is no path from 6 to 3. So this is not an SCC because no path from 6 to 3 or 6 to 2. right? So there's plenty of counterexamples, so it is not a strongly connected component. So what is a strongly connected component look? Well, it's a subset of the vertices of the graph. So there are things inside, and inside this subset, there is a path from every node to every other node. Not necessarily an edge, but a path. So if I start from any source and any destination, I can reach that source and destination, and I'm not allowed to leave and re-enter the set S in the process of doing so. Such a set is called a strongly connected component. Examples: 7, 9. 6, 7, is 6, 7, 8 a strongly connected component? If you look carefully, there is no path from, well, 8, 6. Yes, in fact, it is a strongly connected component. You see there's a triangle, it's a cycle, and so there's a path from 7 to 6, 6 to 7, 8 to 7, 7 to 8, 6 to 8, 8 to 6. So in fact, it is a strongly connected component, and the path does not need to leave 6, 7, 8. All right, very good. All right, so that's definition number 1, that of a strongly connected component. Okay, and this is often a source of confusion, so I'm giving a separate term for this. I call it a maximal strongly connected component. A maximal strongly connected component, which means that it is a strongly connected component that's as big as you can make it, but no bigger. So S is an MSCC, maximal strongly connected component, if and only if, first of all, it better be a strongly connected component. If something is like the maximal X, it better be X in the first place, so it better be an SCC. And secondly, for all vertices that are not in S, S union that vertex is not an SCC. What's the idea here? The idea here is it's a strongly connected component where if you try to add anything else to the strongly connected component, then you do not get a strongly connected component. Such a component would be called maximal. Okay. In fact, I will make this slightly more general. So I would say for all subsets S hat, S union S hat is not, so this is for all subsets of V, S union such that for all subsets S hat of V such that S hat is not itself a subset of S, then S union S hat is not SCC. In other words, if I try to, this is better explained in English than in math. The idea here is it's a strongly connected component that cannot be extended by the addition of any other set of vertices in the graph. If you try to add more vertices to it, no matter what vertices you add, it fails to be a strongly connected component. So let's take an example. So let us take 2, 3, 4, 5. Okay, 2, 3, 4, 5. Now this is already established to be a strongly connected component. We did that. Is it maximal? Is 2, 3, 4, 5 a maximal strongly connected component? And let us try adding different things to 2, 3, 4, 5. Suppose we added 1 to 2, 3, 4, 5. Does it still remain a strongly connected component? No, it does not, because if we did that, there is no way to go from 5 to 1. Suppose we added 6, right? It's no longer a strongly connected component because there's no way to come back from 6 to 2. So you can sense that 2, 3, 4, 5 is actually a maximal strongly connected component. In other words, there is nothing else that I can add to it, no other set of vertices that can be added to it that makes it a bigger strongly connected component. This is as big as it can get. Okay. Now what about S2, which is 7, 9? Is it maximal? And the answer should be no, because if I added 6 and 8 to it, if I added 6 and 8 union S2, 6, 7, 8, 9, that's a strongly connected component. Right? So there is a bigger SCC that contains it. All right. So if there is a strictly bigger SCC that contains it, then it cannot be maximal. So if you want me to update this definition, you can say, instead of saying S is a maximally strongly connected component, you can say for all S hat, you can say it in the negative. I tried to say it in the positive. Now let me say it in the negative. So for all S hat superset of S, superset, so strict supersets of S, S hat is not an SCC. So what is a maximal strongly connected component? Let's try to reword it, but now I will say it in the negative. Well, a maximal strongly connected component is one that is a strongly connected component, and for any superset of it, any strict superset of it is not a strongly connected component. So if you try to add more things to it, it fails to be a strongly connected component no matter what you add. Okay, it's the same thing, but now I am saying it in the negative, which is probably easier to say than trying to say it in the positive. All right, and we saw some examples. So 2, 3, 4, 5 is a maximal strongly connected component, and likewise 6, 7, 8, 9 is a maximal strongly connected component. Is the entire graph G a maximal strongly connected component? If I take 1, 2, 3, 4, 5, 6, 7, 8, 9, is that a maximal strongly connected component? And if you think about it, the answer is no. It is not a strongly connected component, therefore it is not maximal. So this graph has 3 maximal strongly connected components. What are they? The set 1 by itself is a strongly connected component and is maximal. 1 by itself is 1. The set 2, 3, 4, 5 is another maximal strongly connected component, and the set 6, 7, 8, 9 is a third maximal strongly connected component. Right? Each of them is maximal, and that's it. So let me write this down. Okay. Hopefully you have been following me so far. So this graph has 3 maximal strongly connected components. So what are the 3 maximal strongly connected components of this graph? 1 by itself, what we previously saw, 2, 3, 4, and 5, 6, 7, 8, and 9. So there are 3 maximal strongly connected components, and together they account for every vertex of the graph. All right, and this is called a trivial MSCC. Okay, it's just 1 by itself, so it's trivially a maximal strongly connected component. 2, 3, 4, 5, 6, 7, 8, 9. And if I gave you these 3 subsets, this is called the MSCC decomposition of a graph. And it's the starting point of many algorithmic techniques for solving many problems about graphs. Trying to understand a graph, you start by decomposing it into maximal strongly connected components. For many reasons, you would want to do that. All right. And so now the question is, given a graph, can we decompose it into a maximal strongly connected component? Okay, into a set of maximal strongly connected components. All right. Before we do that, let us look at some simple properties of these MSCCs. Okay, so let us start by looking at some simple properties of maximal strongly connected components of a graph, coming up next. Okay, so let us talk about the properties of maximal strongly connected components. Okay, so first property of maximal strongly connected component. If S1 and S2 are 2 different MSCCs of a graph, then S1 intersection S2 better be the empty set, which means that maximal strongly connected components cannot share a vertex. If they are different maximal strongly connected components, they cannot share a vertex. Why is that? Let us take an example. So suppose you had a vertex in common between the two MSCCs. So let us have MSCC 1. Okay, so bunch of vertices, MSCC 1. All right, and what's the idea here? It's full of these cycles. You can go from one place to another. And let's have MSCC 2. And this node that I've shown here, let's say, is in common between the two MSCCs. All right. Now the problem here is that suppose I had two different MSCCs. Okay, two different MSCCs. So they are not both the same MSCCs. So they are different. At least something is different. But let us say that they have some vertex in common, at least one vertex in common. Let's call this vertex V. Well, the problem is, if I take any V2 here in the second MSCC, well, there is a path from V to V2 and V2 to V. That is why it's a MSCC. There are paths here. And likewise, if I took a vertex V1 here, well, there is a path from V1 to V and V to V1. And therefore, let me take S1 union S2. Take S1 union S2. If I took any two vertices in S1 union S2, then there exists a path from V1 to V2 and vice versa. And this path only involves nodes in S1 union S2. How is that? Well, from any vertex V1, first get to V. From V get to V2. So that's how I can hop from V1 to V2. If I wanted to hop from V2 to V1, hop from V2 to V and from V to V1. So I can hop. Therefore, S1 union S2 is a larger SCC containing S1 and S2. So here is a bigger SCC that subsumes S1 and subsumes S2. So which means that the M part of the MSCC can be attacked. So therefore, S1 cannot be maximal or S2 cannot be maximal. And that yields a contradiction. So because that yields a contradiction, you cannot have things in common between S1 and S2. So if you have two different maximal strongly connected components of your graph, they cannot have a vertex in common. They must be disjoint. Let's take a look at our graph here as our example, 2, 3, 4, 5, 6, 7, 8, 9. So they are disjoint, right? So they are disjoint maximal strongly connected components, okay? So therefore, if you take a graph and you start writing out its maximal strongly connected components, each vertex can only appear in one of them. If you take the vertex 4, well, it only belongs to one of the maximal strongly connected components. If you take the vertex 6, it only belongs to one of them. And by the way, every vertex must belong to some maximal strongly connected component. And if not, we allow for it to be a trivial MSCC by itself, right? So 1 here belongs to a maximal strongly connected component of itself. So because we allow that, the set of maximal strongly connected components partitions the vertex of the graph. So S0 union S1 union S3 in this case, I should have named it S2, I named it S3, is the set of vertices of the graph. So if you take the union of all the maximal strongly connected components, that forms your entire vertex set of your graph. And if you take the intersection of any two, that's the empty set. So together they partition the graph into many disjoint subsets, and these subsets are called the maximal strongly connected components. Now we get to a very interesting bit of terminology. What is that interesting bit of terminology? Well, the interesting bit of terminology is the word maximal in front of the SCC. So in many books, when they say SCC, they actually mean MSCC. Okay, and that is kind of confusing. Some books will say strongly connected components, and they mean maximal strongly connected components. I am trying to be a little bit pedantic here to decompose the two aspects of the definition. One aspect is the notion of a strongly connected component, and the other aspect is the notion of a maximal strongly connected component. Okay, so we will simply say maximal throughout my lectures, but note that in many books, in many presentations, just a strongly connected component, already they mean a maximal strongly connected component. So it's a notational thing that people sometimes cannot agree upon. So I will keep saying maximal just to remind you of what I mean. But note that many people will say strongly connected component, in which case you might want to ask them whether they mean maximal strongly connected component, and typically they will know what you mean. All right, so this is how it goes. So this is the first property of MSCC, that they are pairwise disjoint. What's the second property of MSCC? Well, it's closely related, and this is also a very important property. Okay, so let me make space for this property. So this property says, okay, you can making some space, almost there. All right, there we go. Okay. All right, what's the second property? Well, suppose in this graph, I take each of these maximal strongly connected components and I build what is sometimes called a supergraph, or people will call it an MSCC supergraph, which is take every maximal strongly connected component and compress it into a single node. So 1 becomes a node by itself, 2, 3, 4, 5 becomes a node by itself, and 6, 7, 8, 9 becomes a node by itself. All right, and then let me add the connections that only go across MSCC. So there used to be an edge from 1 to 2, and now that's an edge from 1 to the entire 2, 3, 4, 5. There used to be an edge from 2 to 6, now that becomes an edge from 2, 3, 4, 5 to 6, 7, 8, 9. Are there any other edges we should worry about? No, there's no other edges. Every other edge is internal to MSCC, so we leave them out. Okay, and this is called, sometimes called, not everyone wants to call this is called an MSCC supergraph. All right, just decomposing every MSCC, compressing it into a single node, you get a new graph which looks like this in this case. Well, this is the second important property of MSCCs, which is the MSCC supergraph, okay, is a directed acyclic graph. The main important thing is it is acyclic, cannot have cycles. And that's super important to note, that this MSCC cannot have cycles. Why cannot it have cycles? Well, let us imagine that your MSCC supergraph had a cycle. Okay, so there was a cycle. So what does it mean? It means that in some graph you could go from, let me say, some MSCC M1. Let's say I could go from there to M2 all the way to some MK, M sub k, back to M. Okay, so suppose there was a cycle in this graph, in this supergraph. Well, unfortunately, now consider M1, consider the union of all the nodes along the cycle, M1 union Mk. Well, if I start from any vertex in M1, well, there is a path to the head of this edge. Wherever this edge went, there is a path to the head of this edge. From there I take the blue edge, and then inside M2 there's going to be a path to the head of the next edge. And if I keep traversing, what you notice is that this whole union is an MSCC. Why is that? Because if I wanted to go from any node to any other node, like some node in M1 to some other node in MK, well, there is a way for me to get there. I hop from one MSCC to the exit. From the exit, I hop to the next one. I hop to the exit, I get to MK, the entrance of MK, and from there I will find a path, because each of these M1, M2 to MK are themselves MSCCs, right? So I can go from anywhere to anywhere else. Likewise, I can go from any node in MK to any node in M1 to any node in M2. So because of that, this entire union becomes an MSCC which is larger than each of them individually. So it's larger than M1, strictly larger than M2, strictly larger than MK. These are not empty sets, right? If not, then it contradicts the fact that each of them is maximal. Maximal means they cannot be extended anymore. But if there is a cycle in this graph, well, the entire cycle will collapse to a single big MSCC, which is the union of all these small nodes, and that cannot simply be. And so therefore, it is an acyclic graph. So there cannot be a cycle in this graph. It's an acyclic graph. Okay. So interestingly, a lot of algorithms have this combination of taking the maximal strongly connected components, constructing some kind of supergraph, and then doing some kind of topological ordering on the supergraph. So that is, for example, a very standard approach in many algorithms, okay, that comes up all over the place, for example. And you can do that because it's a DAG. The supergraph is a DAG. It's a directed acyclic graph. All right, so two very, very important properties of maximal strongly connected component. Now finally, there is a third property, okay, and I'm simply going to state this property, and I hope you have learned enough now that you should be able to do a proof of this property, okay. The third property, which is all important, is that the reverse graph G transpose has the same MSCC as the original. Let me explain what is the reverse graph and why do we put a transpose on it. Well, in the reverse graph, you take the original graph and reverse the direction of every edge. Okay, I'm showing it in green. You simply reverse the direction of the original edge. So they are all now in green. So that's the reverse graph. Okay, take the original edge and just reverse the direction. Okay, how do we do that with an adjacency list? In the adjacency list representation, you have to iterate through each edge in the adjacency list and create a new adjacency list where you add the reverse edge. Okay, I hope you know how to do this in the adjacency list. How do you do it in the adjacency matrix? Well, if you have an adjacency matrix of zeros and ones, you simply transpose the matrix. So you turn all the rows into columns and columns into rows, and that becomes the reverse graph. And that's why the notation for the reverse graph is G transpose. You transpose the adjacency matrix, you obtain the reverse graph. Okay. And for adjacency list, it's a little bit more time consuming than transposing, but you know how to do it. I hope you know how to do it. All right. Now the claim is, if I reverse the direction of all the edges in the graph, I still get the same set of MSCCs for this new reversed graph. Why is that the case? Well, first, it's easy to see that every MSCC will remain an MSCC. Why is that? If I could go from 2 to 4 in the original graph, I could go from 4 to 2 in the same way in the reverse graph. If I go from 2, 3, 4, I can go 4, 3, 2. Right? So, and likewise, if I can go from 4 to 2 in the original graph, I can go from 2 to 4. So, the definition, from the definition of MSCC, you notice that reversing the direction of the edges keeps an MSCC and MSCC. So, the MSCC property is preserved under reversal of edges. And furthermore, you also notice that if it was not an MSCC in the original graph, so for example 1, 2, 3, 4, 5 in the original graph was not an MSCC, in the reverse graph it will still not be an MSCC. So MSCCs remain MSCCs, not MSCCs remain not MSCCs, and therefore you can combine these two arguments to prove that the set of maximal strongly connected components are not altered when the direction of the edges are reversed. And that's super important, and that's the third property. All right, now that we have these three properties, we can now do depth first search to discover all the maximal strongly connected components of a graph. And given a graph G, the goal is to print 1, and then print 2, 3, 4, 5, and then print 6, 7, 8, 9. So I want to print the set of strongly connected components of a maximal strongly connected components of a graph, given the graph in, let's say, the adjacency list representation or adjacency matrix. Doesn't matter, I want to print out all the strongly connected components, the maximal strongly connected components, not just the strongly connected components, okay? We are making that distinction for the purposes of this lecture, even though the book does not make that distinction. I hope this is all clear. If this is all clear, we can move into the algorithm in the very next lecture. See you then, bye. Okay, so now we are going to look at the algorithm for finding the maximal. Okay, so I'm going to keep saying maximal. Not everyone likes to say it. Okay, so we may at some point silently drop it, but I'm going to keep saying maximal. All right, maximal strongly connected components of a graph. All right, now the algorithm is actually really simple. So first we are going to do a DFS on the original graph G, and then some little bit of mumbo jumbo, which I'll explain. With that being said, we are going to do a DFS on the reverse graph G transpose by reversing the direction of all the edges, and magically all the strongly connected components, the maximal strongly connected components, are going to get printed in this process. How is that even possible? Let us start by doing the first DFS on the original graph G. Well, remember, in DFS there are two things we care about: the discovery time of each node and the finish time of each node. All right, so let's do that. So we start, let's say we start from 1. We could start anywhere. If we started from 2, then we'll have to do 1 later on. All right, let's start from 1 itself. It is discovered at time 1. DFS goes to node 2, which is discovered at time 2. Then it goes to node 3, which is discovered at time 3. Then it goes to node 4, which is discovered at time 4. Node 5 is discovered at time 5. Then 5 has no successor that's new. Every successor, every adjacent node has already been seen. So we finish the DFS there, return. That happens. So the finish time of 5 is 6. Finish time of 4 is 7. Finish time of 3 is 8. Now we come back to 2. We are not done yet. We are going to go to 6. Now the discovery time of 6 is 9. From 6 we go to 8, whose discovery time is 10. From 8 we go to 7, whose discovery time is 11. From 7 we go to 9, whose discovery time is 12. 9 is finished, 13. 7 is finished, 14. 8 is finished, 15. 6 finishes, 16. 2 finishes, 17. 1 finishes, 18. So you run your DFS, and out comes the start time and the finish time of every node. And now comes the second part, and here is the magic. Okay, so we are done with the first DFS. Now the second DFS is going to be slightly different. So now reverse the graph. If you are in the adjacency list representation, what is reversing a graph mean? So reversing a graph means that, for example, if I have 1, its adjacency list has 2. If I have 2, its adjacency list has 3 and 6. So now I'm going to iterate through this graph and create a new adjacency list. So if I see that 1 is connected to 2, in this new adjacency list, I'm going to add 1 to the outgoing edge of 2. Okay, and likewise I'm going to add 5 to the outgoing edge of 2. So I'm going to iterate through this. Reverse the edges and add to a new empty graph. And when I add to that new empty graph, I create the adjacency list for the new empty graph. If I had an adjacency matrix, I simply transpose the matrix. So I comma j becomes j comma I. All right. With that being said, now I have the reverse graph. How am I going to do the DFS on the reverse graph? Well, here is how I'm going to do it. It's not just a DFS like a regular DFS, but it's going to be in the descending order of finish times. So how do I do that? Well, the naive way would be to, like we, to sort the list of vertices by the descending finish times. But a clever way to do that would have been to equip this DFS with a list of finish times, finished nodes, and keep tacking every time a node gets finished, keep tacking it onto the head of the list. So the list is going to have the node that finished the last, which is going to be 1, followed by the node that finished after that, 2, followed by the node that finished after that, 6, 8, 9, no, 6, 8, 7, 9. Okay, so you're going to maintain a list descending order of finish times. This is important. So you do it in the descending order of finish times. The next step is essentially do a new DFS visit on the reverse graph. So now this DFS is going to be on the reverse graph G transpose, not on the original graph, but on the reverse graph. Okay, but this DFS visit is going to start, so first start from the head of this list. So I'm going to do it in the descending order of the finish times of the forward DFS. Okay, now that's the trick. When I do it that way, I'm first going to do DFS visit starting from 1 on the reverse graph. So if I do a DFS visit starting from 1, and I'm going to record every node that's visited and remove them from consideration. So if I do it from 1 on the reverse graph, what are the outgoing edges of 1 on the reverse graph? Well, on the reverse graph, 1 has no outgoing edges because on the reverse graph, it only has an incoming edge from 2. Remember, directions of all the edges are reversed. So therefore, when I start DFS from 1 on the reverse graph, the only node that's visited is 1 itself. So remove it from consideration. Now start a DFS from 2 on the reverse graph. So to help you, I'm going to draw the reverse edges in green. Just to help you see what's happening. So if I start a reverse DFS from 2, what are the nodes that this reverse DFS visit is going to traverse? Well, from 2 it's going to go to 5, from 5 it's going to go to 4, from 4 it's going to go to 3, and from 3 back to 2. So 2, 5, 4, 3, 2, and then remove all the nodes from consideration. 5, 4, 3. Remove all of them from consideration. Okay. So now what you have printed out the second MSCC. Starting from 2, every node that's visited in the reverse order is going to become the second thing from the reverse MSCC. What is left? Well, now the next one in the list that hasn't yet been tackled is 6. So start from 6 and do a reverse visit. So when I do a reverse visit, I'm going to traverse the green edges, which are the edges of the reverse graph. Remember that. So if I start from the reverse graph, well, starting from 6, I'm going to visit 7. From 7, I'm going to visit 8. From 8, I'm going to just return and then come back to 7, visit 9, come back to 6. So this is going to be roughly the order. You can check. And so this is going to become the third MSCC. Remove that. Now, at this point, the list is empty, nothing more to visit. We stop. We've printed out all the MSCCs. But until this list is empty, keep doing it. So let me recap. The algorithm has 2 DFS with modifications. First DFS, just like topological sort, I'm going to give you a list. As soon as a node is finished, attach it to the head of the list. So the list is growing like in the reverse order. So it's going to have the descending order of finish times of the original DFS. Now take the nodes in the list and take the node at the beginning of this list and do a DFS on the reverse graph. When you do a DFS on the reverse graph, it's going to visit some edges and exit. Take those nodes that you visit on this reverse DFS and print them out as your MSCC, at the same time deleting them from this list. When you do that, you will end up printing the MSCCs as you do the reverse DFS visit. Now that's the most interesting part of this algorithm. Now the question is, why does this algorithm work? Why is it that this algorithm actually works? And it's based on two properties. Okay, so let me summarize the properties that we've seen so far. So the first property was that the supergraph is a DAG. Okay, so that's the first property. So if you built a supergraph, that supergraph is going to be a directed acyclic graph. Okay, and number two is going to be the following. The number two part is going to be that the reverse graph has the same set of MSCCs as the original graph. All right. So with those under consideration, what you will find out is this is how the algorithm works. Okay. So what is happening is when I do the first DFS, let me look at the effect of this DFS on the supergraph. So the supergraph has 1 by itself. I don't know this supergraph yet, but this supergraph exists. I just haven't found it out, right? But it exists. 2, 3, 4, 5, and 6, 7, 8, 9. Okay, and so for each of these supergraphs, let me annotate with the largest finish time of any node. So 1 finishes at 18. So let's give that number to the entire supergraph. So 18. If I look at 2, 3, 4, 5, 2, 3, 4, 5, the latest finish time is 2, which has a finish time of 17. So let me give it the finish time of 17, right? Which is 17. So let me give it this finish time, the latest finish time of any node. If I take 6, 7, 8, 9, 6, 7, 8, 9, well, the latest finish time is 16. So let me give it that finish time 16. So if I actually ordered this supergraph according to these finish times, that accounts to a topological sort of the supergraph. So in the very first step, when I'm doing the DFS, even though I cannot topologically sort this original graph, why can't I do that? Because it has cycles in it. Because it has cycles in it, I cannot topologically sort it. But I can think of the topological sort of the supergraph. And why can I do that? Because the supergraph is a DAG, so it has a topological sort. And in this topological sort, 1 is the latest finish time, so it comes first. 2, 3, 4, 5 has the second latest finish time, so it comes second. 6, 7, 8, 9 has the last finish time, so it comes third. All right. And so with this being said, when I do a reverse DFS on 1, on this supergraph, only this supergraph can be visited. So when I do the reverse DFS on the topologically first supergraph, only it can be visited, nothing else can be visited. And once that's been eliminated from consideration, when I do a topological sort, when I do a reverse DFS visit on the second one, the only supergraphs that can be visited are this strongly connected component, and it can go back to 1. It can, because in the reverse graph this edge direction is reversed, so the DFS could go back to 1, but 1 has already been visited, and so it's been eliminated from consideration. So when I do a reverse DFS on this next, on 2, 3, 4, 5, the only nodes that can be visited are 2, 3, 4, 5. Nothing else can be visited, and then that gets eliminated from consideration. When I do a reverse DFS on 6, which is the latest finishing node of 6, 7, 8, 9, the only nodes that can be visited are 6, 7, 8, 9. Even though it will try to get back to 2, 3, 4, 5, those have already been visited, so it will not visit them again. So what is this algorithm doing effectively? Effectively, this algorithm is topologically sorting the supergraph. Even though it doesn't know the supergraph, it doesn't know it, the process of descending order sorting the nodes in the DFS visit of the forward graph, of the original graph, ends up topologically sorting the supergraph. And now when I do a reverse DFS visit on the first topologically sorted node in the supergraph, that will only visit the strongly connected component corresponding to that node. When I do it in the second ranked topologically sorted node in the supergraph, that will only visit this strongly connected component corresponding to it. It might try to take a reverse edge into a different strongly connected component, but the property of this algorithm is that that would have already been visited, so it's not going to go into that. So likewise for the third one. So you can now start to imagine why is this algorithm working, okay? And it's a very clever algorithm. What's the running time of this algorithm? Well, the running time of this algorithm is effectively the running time of 2 DFS and a graph reversal, okay? Running time of DFS is just the number of vertices plus the number of edges, okay? So that's the running time of each DFS. How much time does it take to reverse a graph? Well, if your graph is an adjacency list representation, it's also the same number of vertices plus number of edges. So therefore, the algorithm runs in linear time in the size of the graph. So if the size of the graph is 30 vertices and 80 edges, algorithm takes roughly proportional to 30 plus 80, which is 110 steps, proportional to that. So it's linear in V plus E, and in practice it's a very, very fast algorithm, modulo the fact that you need to reverse this graph. If the graph is too big, sometimes reversing the graph is a problem. But if you are okay with reversing the graph and doing a DFS on the reverse graph, then this algorithm works beautifully and prints out all the maximal strongly connected components. So we have seen the algorithm itself on an example, the very, very simple pseudocode of this algorithm, which is just running 2 DFS with a graph reversal in the middle, and having to make sure that you're only running it on the reverse sorted. And I've given you not a proof but a rationale for why this algorithm works. The proof itself is in the book. I strongly advise you to look at the proof, but I also advise you to play around with this algorithm and convince yourself of this key fact of why this algorithm works, in that it topologically sorts the supergraph in principle. It doesn't know the supergraph to topologically sort it, but this action of doing a DFS and sorting things according to reverse time, according to the finish times in the descending order, ends up achieving that effect of topologically sorting the supergraph. Hopefully this is all clear. If this is all clear, then you have learned a very, very useful and important algorithm for which there are many, many uses in practice. So I hope we will be able to explore some of them through your assignments. Thank you. All right, so welcome to this lecture on amortized analysis, which is a technique for analyzing the cost of operations in data structures. So it's a technique for analyzing the cost of operations, doing operations in data structures. And let me motivate amortized analysis with a simple example. All right. So let us consider an example of a stack where we are able to push or pop everything off the stack. So we have 3 operations: push, pop, or pop all. To illustrate what's happening, suppose here is the current stack, here is the current stack, here is the bottom of the stack, here is the top of the stack. And let's say I push 5, then a new element 5 gets added to the top of the stack. Let's say I pop the stack, then 5 gets removed, and you have 7 now on the top of the stack. Let's say I pop again, you have 4 on the top of the stack. And let's say I do pop all. Now this operation is going to remove all the elements in the stack and result in an empty stack. Now what about the computational cost? The computational cost of a push and pop are assumed to be 1. Okay, you're just adding and deleting an element from the stack. Whereas pop all is going to be as much as the number of elements you pop, in this case 4. Okay, so that's the basic idea behind this stack. Now let's look at the complexity of these operations in the stack. Let's look at the complexity of the operations in the stack. And we want to study it in the form of amortized analysis. So what is amortized analysis? So in amortized analysis, we are going to not ask about the complexity of each individual operation in the worst case. That's easy to answer, and you should know how to answer that already. Push is constant cost. Pop is constant cost, so you'd say theta 1, and pop all is as much as the size of the stack, so theta, the size of the stack. So that's the individual complexity of each stack operation in the worst case. But suppose we are not interested in individual complexity as much as we have the following situation. We do n stack operations. So n of these stack operations. So, and these could be any combination of push, pop, or pop all. The only thing is you can't pop from a stack where you have not pushed anything. So you have to always push something and then pop. Okay. So that's the combination. So we have n stack operations. Okay. And the question is, what's the worst case complexity that can happen? And you could say, well, because you have n operations, the stack cannot at any point have more than n elements. All right. Now the pop all is going to have a complexity that's going to be proportional to the size of the stack. And in the worst case, the size of the stack can be n. So in the worst case, pop all can have complexity that's proportional to n. So you can say I have n stack operations. In the worst case, it can be all pop all, so which is order n, so which is order n squared total. So then dividing it by n, you can say per operation cost is order n worst case. All right. So you have to think about this for a second and pause here and think whether this analysis makes sense or you think it's overly pessimistic. Could we do better? If we have to consider n stack operations, some combination of n stack operations, and we want to know what's the complexity of these n operations together, you can take the individual worst case for one of these operations and multiply it by n, but that doesn't seem to tell us the whole story. And to tell us this whole story is what we do in amortized analysis, which is to look at what's called amortized cost. And so let's talk about amortization then. All right, so what's the idea then? So the idea here is this. If you think about this example in a stack with pop all, one of the things you can say is you can only pop what you push, which almost has this has the flavor of an important saying, right? You can only reap what you sow or something like that. So you can only pop what you push. All right. So suppose you are pushing a bunch of things into the stack. Suppose you're pushing a bunch of things into the stack S0, S3, S4. Then when you do a pop all, you can only pop the things that are on the stack so far. So the cost of a pop is related to somehow all the pushes that have happened before it. Okay, so you can't have this idea of sequence of n pop all. So you can't have n pop alls in succession because the first one is going to empty the stack and then the rest of them have zero cost. They're not going to have order n cost. All right. So the complexity of these operations, like an expensive operation, might be expensive only because you've done other operations before which have made this one operation expensive, right? And if you look at it cumulatively together, maybe the complexity is no more than the number of push operations times 2. All right. And so that's the message that I'm going to be talking about. All right. So let's talk more about this. So think about a more nuanced approach. In this more nuanced approach, let's think about time as the same as money, right? Time is money. So we will say the following. Whenever we push, we will pay $2. We'll pay $2 in terms of computation time. $1 is going to take care of the cost of pushing. And then we store the extra dollar as some prepaid cost. Okay, think about it this way. This is just a way of thinking about it. Obviously, you never do this prepayment. It's not possible to bank time or to bank computation time. But suppose you are allowed to do it. Here is how you would do it, right? You would prepay. And therefore, your stack has the following property. Everything you've pushed, you paid $1 to push it, but you also have $1 that's left. So you pay forward for each pop operation when we push onto the stack. So you pay it forward. So when you pop, so when you push, so now when you push, you have $2. When you pop, your cost is $0 because you're already using the prepaid amount for that. So in this example, every pop is free and every push is $2. Now, what about a pop all? And I'm going to claim this and think about it. It's also free because if I wanted to pop everything off a stack, you can always collect the extra dollar that I have prepaid for every element in the stack and just use that to pay for the pop all. So it works for a single pop, but it also works for popping everything off the stack. So these are all free because I prepaid $2 for a push. Now think about if I had n push, pop, and pop all operations. Now let's do a more nuanced analysis of how much is the worst case cost of it. Well, the worst case cost of it is going to be twice the number of push operations plus 0 times the number of pop operations plus 0 times the number of pop all operations. Because you don't pay for it if you overpaid for push. So it's just twice the number of push operations. In the worst case, all n can be pushed. So this is just 2n. So the total cost of n operations is 2n in the worst case. So the cost per operation is just 2. And this cost has a name. It's called the amortized cost. It's like an averaged cost considering n operations for some large enough n and considering the worst case for any n combination and dividing it by that. So in other words, consider n operations, some n combination of operations, op1, op(n) onto the stack, and look at the total cost in the worst case as a function of n, and divide that number by n, and that gives you amortized cost. That's called the amortized cost. And in this example, you convince yourself that the amortized cost of every operation is just 2. It's not order n, it's exactly 2. It's constant. So its amortized cost is constant, which means any combination of n operations has cost theta n. Okay, so this gives us rise to a method called the accounting method, And to summarize, think of computation as money. Pay money for future operations that can be just used. For a push operation, pay 1 unit for computation time and 1 unit for paid forward, which you're going to use when it's being popped. So amortized cost of a push is just 2 units. For a pop operation, pay 1 unit for computation time and then take away 1 unit of prepaid cost. Okay, so amortized cost is 0. For amortized pop all, to pop k units, k elements of the stack, so k units of computation time, but I've already prepaid it when I pushed it, so k minus k units. So amortized cost for a pop all is just 0. So push, pop, and pop all, amortized cost is constant. And this kind of a method is called the accounting method, where on some operations you pay forward, and then on some operations you can utilize prepaid cost to offset the actual computation cost. So to offset the actual computation cost, I can use some prepaid cost to offset it. Okay, and in some operations you have to pay it forward. Now, obviously, this is not rigorous, but we can make it quite rigorous, and I'll show you in a second how to make it quite rigorous. All right, but let's look at another example before we move forward. In this example, I'm going to be thinking about a binary counter, a sequence of 0 and 1 bits, on your computer. And I'm going to be thinking about the operation of incrementing or adding 1 to the counter. Now, the algorithm for adding 1 to a counter is well known. And let me just summarize or recall this algorithm for you. The idea here is you move from the right, or the least significant bit, to the left, which is the most significant bit. And therefore, every time you see a 1, you make it into a 0. As long as you see a 1 on the right, make it into a 0. When you see the very first 0, when you see the very rightmost 0 here, convert that into a 1 and then stop. So if you have 1 0 0 1 0 1 0 0 1 1, this becomes 1 0 0 1. These are all unchanged. From before. And then the 0 1 1 now became a 1 0 0. Okay, and this is the algorithm for an increment of a binary counter. And you can see in the worst case, suppose I'm asked to increment this number 1 1 1 1 1, and it's n ones, then I essentially have to go all the way and convert all of these ones to a 0. And let's say there is a 0 here, then that becomes a 1. So in the worst case, this is as much time as the number of bits. So theta n time. So a single increment can take theta n time, worst case. Worst case. So suppose I have a binary counter. Let's say I start with 0, 0, 0, 0, 0, and I do m increment operations, I call increment m times. So what's the total time it takes? So it's going to be n for the worst case times m, which is the number of operations. So you can say it's ONM. So for example, if you have a 128-bit counter and you're doing 1,000 increments, so then it has to be 128 times 1,000 in the worst case. Is this correct? Is this tight? And what we can see here is that amortized analysis is going to tell us a slightly different story. Because remember, this worst case is only encountered when every bit to the right is 1, when you have a bunch of ones. And then once you have done this, once you have done the worst case, then if you increment once again, you get 1, 0, 0, 0, 0, 1. So increment the very next step, even though this step took n bits of update, the very next step just took 1 bit of update. So it's not that the worst case keep coming. If you're going to do a sequence of operations, it's not like you keep encountering the worst case again, and again. You encounter the worst case once and then it's okay. So we can do an amortized analysis to see if that improves things. So let's talk about an amortized analysis. Okay, so again, this is the same thing I said in the previous slide. Start with 0, 0, 0, perform k increments. So is the worst case OK times n? And the answer is no, because what we are going to see is even though the worst case for any single operation is as many as the number of bits, that only happens in this very specific situation where the rightmost bits are all 1. If the rightmost bits are all 1, in the very next step, you get 1, 0, 0, right? You get 1, 0, 0, 0, 0, 0. And then incrementing is actually quite cheap. You actually get the best case. So if you get the worst case once, you get the next time you actually get the best case. So obviously, this is not telling us the full story. So what is the full story? All right. And now we'll talk about an accounting method for amortized analysis for the binary counter. And the idea is very simple. Every time we change a bit from 0 to 1, you pay $2. And think of dollars as computation time. So you pay $2. $1 for the actual change, for the actual computation of changing a 0 into a 1, and then pay $1 forward to support a future change from a 1 to 0. So here we go. So every time I change it, I have this extra $1, which is prepaid, and I will write it here. So suppose I have my counter as 0, 0, 0. I increment it and I get 0, 0, 1. And now in the very second step, when I change this 1 to a 0, I'm going to use this prepaid credit. So this doesn't going to cost me. When I change the 0 to 1, I'm going to pay $2 here and then use $1 for the computation cost and keep $1 prepaid credit associated with this one. So here's the thing. Every time in this analysis, I have a counter, then every of these ones has a $1 prepaid credit with it. There's a prepaid credit of $1. So then the next time I increment, I'm going to change this 1 to a 0. I will use this prepaid credit. But if I change the 0 to a 1, then I put a $1 prepaid credit. So there's going to be some prepaid credit that I'm going to accumulate in the counter that I'm going to use to pay for the future. I hope this idea is clear. Now, with this idea, what happens then is suppose I get in the situation where I have k ones to the right of my counter, then I do an update. Well, what's going to happen is the actual cost of this particular update is k plus 1 because you have to take all these k ones and change them to 0. And then you have to change the 0 to a 1. But what I'm going to do is I have already prepaid k dollars. Every time I have these counters, there's already k dollars prepaid. So I'm going to utilize that. So that's going to be prepaid. So this is credit. And so I'm going to pay an extra $1. I'm going to pay an extra $1 here for this 0, which changed to a 1. All right. So the total amortized cost is k plus 1 minus k plus this extra 1. So that's just $2. So no matter how many bits are to the right, because I'm doing amortized analysis, the amortized cost is just 2. So what's happening here is this. This way of counting informs us that if for each operation, the amortized cost is 2. No matter what it is, what the value of the counter is, the amortized cost of each operation is exactly 2. And if I have k increments, the amortized cost is actually 2k. So this accounting method teaches us that the time taken for k operations is exactly 2k. Okay, there's different ways of analyzing and arriving at the same result, but this is a very elegant way of looking at it and convincing yourself that if I did k increments starting from all zeros, if I did k increments, my computation time is not k times n, that's an upper bound, but it's not correct. It's actually more like 2 times k, much smaller than k times n. Okay, so let me illustrate this accounting method with a last example where I'm going to have arrays which allow me to insert elements and reallocate. And we've seen this before, and these are called dynamic arrays. Okay, so dynamic arrays, which are arrays where you can have insertions at the end. So we saw this at the very first lecture of course 1, right? So you can have 2, 1, 3, 4, 7, 8, 10, 12, 18, 25, 32. And so now you have unallocated space. And when you insert a new element, you add it to the end, and it takes up one of the unallocated space. But when you have filled up almost to the brim your unallocated space, let's say now you want to insert a new element and there is no unallocated space, what you do is you allocate a new array which is twice the size of the old array, and then you copy each of these elements over. And now you have unallocated space left. So this is what we are going to think about. What is the cost of this kind of a data structure? And we've seen this. We've seen examples of this in hash tables as well, where we do rehashing. When the load factor exceeds some value, we are going to do rehashing. And so this kind of pattern also happens at hash table. So the analysis that I'm going to do right now is also going to be somewhat important for things like hash table. So I'm going to be talking about that. All right. Okay, so now what's the cost of n insertion operations in a dynamic array? Well, if you have the worst case reasoning, you will say each insertion can potentially cause a resizing. Okay, and cost of the resizing is the current size of the array. The worst size of the array is n. So the worst case of n insertions is order n squared, because each insertion can potentially cause you to resize your array and have to copy over every element into the resize. So each insertion can be order n because you're doing n insertion operations, and therefore worst case complexity is order n squared. But unfortunately, that's a gross overestimation. So let's perform an amortized analysis, because what we see here is this. When you do a resizing, there's going to be some unallocated space. And between this and the next resizing, you will have to fill up all this unallocated space before you get to the next resizing. So it's not like a resizing is going to happen at every step. This is not correct. A resizing is not happening at every step. This is not happening at every step. Worst case size of the array is not n, because that's only at the very end of n insert operations. It's n. So we have to think about this more carefully. So let's think about this using amortized analysis. What's the amortized cost of n insertion operations in this kind of a dynamic array? And here is how I'm going to be thinking about this. Every time I have this dynamic array, okay, let's say it's going to be like this. So suppose I have this dynamic array. Now I have the total size of the dynamic array. This is the allocated size. And I also have the part that's been filled up, Okay. Now, every time I insert an element, I'm going to pay $3 for the insertion. Why $3? Well, I'm going to pay $1 for the actual cost of putting E in there. And then I'm going to pay $2 I'm going to pay $2 for future costs that are going to be associated with resizing. So I'm going to pay $2. Why $2? I'll explain in a second. But I'm going to pay $2 here for future costs. Okay. Now the idea here is something like this. Let us, for example, take an example. Let's take an example. All right. Here, let's start with a very simple example with an empty array. So let's say we insert an element. Let's say we insert a 1. Okay, so we insert an element 1. Okay, so we insert an element 1. And now I carry $2 with me. And then suppose I inserted 2. I inserted 2. Then I have the element. Now I have the array 1, 2. Okay, let's not worry about the cost right now. And let's not forget about 1. Let's say now I have $2 here. Now suppose I inserted 3. Then I'm going to do something like this. Now I'm going to allocate size 4. And then I'm going to copy 1 and I'm going to copy 2. And this $2 with 2 is going to pay for this copy. It's going to pay for this copy. And then I'm going to insert 3 here. And that's now going to have $2. But since I have paid up for the copy here, I am not going to have any left here. So now 3 is going to have $2. Let's say if I inserted another element, let's say 4, that's going to have $2. Now, if I insert a new element, my size is going to grow to 8. And now I have to copy 1, 2, 3, 4. They don't have any money. They are bankrupt. But then I will have to insert 4 more, 5, 6, 7, 8. And I'll have to pay $2 here for them. I'll have to pay $2 for them. Now these $2, one of the dollars will pay for copying them over. The other dollar will pay for copying one of the original 4 elements over. And now when I have to reshuffle and resize to an array of size 16, these will pay for all of them. In general, the picture looks like this. I will have size, let's say total size right now is n. I'll have n by 2 elements that were previously copied over, so they have no money left. Whereas everything that's inserted after that is going to have $2. It's going to have $2. So these n by 2, when I insert them, will give me $2 each. So the total charge, the total amount I've accumulated is 2 times n by 2, which is n dollars. That's the total amount I've accumulated. So when I resize this to 2n, I have to do n copies. I have to do n copies. And so I have the cost already prepaid for a future copy, not just for an element on the right-hand side of the array. I also have prepaid for an element on the left-hand side. So this is how this is going to work. And the important part is every time I resize, I copy n elements, but I keep space for n more. And this doesn't cost me anything. To allocate space doesn't cost me anything. What costs me is the copying. Or you can think of allocating space as costing me a constant, but what is really costing me is the copy operation, which is going to cost me n. Okay. I hope this idea is clear. This is kind of important, where you see that the latest inserts, the latest n by 2 inserts are paying for the previous n by 2, which already paid when I copied this over, right? So it's like the first half cannot pay for it, but then the second half are paying $2, where $1 pays for themselves to be copied over, and then another dollar pays for the previous 4. And then when I copy over, all of these won't be able to pay, but then the next 8 coming in will pay for these 8. Okay, and that's how it's going to go. Okay, so dynamic array, then what's the cost of resizing? Well, when you resize, you have n by 2 elements, for which you haven't paid, n by 2 elements for which each of them you've paid $2. So you've already paid n. So the cost of resizing and copying is already paid for. And then comes the cost of insert. So that's $2 plus $1 for insert. So $3. So even if you resize, the cost of an insert remains $3, or 3 units for every insertion, even if you resize. All right. So to summarize, in dynamic arrays, the amortized cost is 1 unit for computation cost and 2 units paid for future resizing. And when you reallocate, you have n plus 1 units of actual computation cost, n units for copying, 1 units for inserting, but n by 2 elements each having 2 units of prepaid time. So 2 units of prepaid time cancels the n units of cost you need. So it's still 3 units of amortized cost. All right. So you can see that with amortized analysis, I can show that the complexity of n insertions is 3n amortized complexity. Okay, the complexity of each insertion is 3 units of amortized cost. Okay, I will stop here. And then in the next lecture, I will formalize this using something called the potential method that will make this argument quite formal using a potential function. So I'll talk about this and wrap it up next lecture. Thank you. Hello, and in this lecture, we are going to be talking about amortized analysis and introduce the concept of potential functions. So this is going to make some of the concepts we looked at in the very previous video, where we looked at this informal, slightly informal accounting method, and we are going to make this much more formal and much more rigorous using something called a potential function. So what's a potential function? And think of this as inspiration that's taken from physics. So, in many physics situations, for example, suppose you have the following interesting physics situation, very interesting. So, you have a boulder, and your goal is to roll this up a hill. Okay, so that's your goal. So, you're rolling this boulder up a hill and moving this up a hill and moving this up a hill. And let's say you've rested it here. Okay, and your goal is to get it here. So the point is, once you're up here, you give it a teeny tiny push and it's going to roll all the way downhill. And this doesn't need work. This is a lot of work, and this is no work. And the point here is you're building up potential. So you're raising a boulder from the ground height, let's say, to some height up a hill, and that's building up potential. And the potential then allows you to do something where you might think of it as doing work, but it's really no work. Okay, so then you can say the total work that's taken from moving from A to B here is essentially the work that's from A to C, building up this potential. And then the potential does a lot of work moving from C to B. So it's a very nuanced way of analyzing how much work you do. Similarly, another example would be like, for example, if you have a spring, and you press the spring down, then you're building up potential. Or if you have a battery, and you charge the battery, then you're doing some work, but you're also building up potential. Now, the point here is to do the same for data structures and do amortized analysis using these kinds of potential functions, where we can talk about formally about potential that you're building when you do computational work in a data structure. And that would formalize some of the insights we got from the accounting method. All right. So what's a potential function then? It's a mathematically rigorous, in my opinion, way of performing amortized analysis. And it's an alternative to the accounting method where you're paying upfront for operations. What's the basic idea? Very simple. The basic idea is, think of d sub I as an instance of a data structure. So somehow it's a data structure instance in the middle of doing some operations, right? And you're going to associate a function capital phi of d sub I, which is going to map this data structure to a potential value, which is typically a non-negative real number. The non-negative part is not so important, but we will try and keep it non-negative if we can. So it's going to be a non-negative real number, d sub I. Okay. Now the point here is this: anytime you do an operation on the data structure, it's going to move your data structure from d sub I to a new data structure instance, d sub I plus 1. And let's say the C sub I was the computational cost. Then you say the actual amortized cost is defined as, and this is definition, the change in the potential, the delta phi, the change in the potential because you did the operation, and plus the actual cost. So for example, if I'm moving a boulder uphill, then the actual cost is the cost of moving the boulder, let's say 1 unit. But then there's going to be the change in potential between moving up some height, right? So it's going to be the change in potential plus the actual cost, the actual distance traveled, and that's going to be the amortized cost, and we'll put a hat on top of the amortized cost. Okay, and that's the definition, and that's what we call the amortized cost. But here is the main requirement, and let me be careful about this. If you want to sum up all the amortized cost of n operations, let's say your data structure starts off at D0, and then you do some operation whose true cost is C1, you go to D1, with C2 cost, you go to D2, and you keep going until you go to Dn, and then Dn plus 1. So let's say these are the data structure instances you get to. Now, the point is, the total amortized cost is the total change in the potential. So this is the total change in the potential plus the cost, all of which are under the summation. Okay. Now the point is the change in the potential, so delta phi is going to cancel out. So for example, you have phi1 minus phi0 plus phi2 minus phi1. And this is called a telescoping sum, plus phi n plus 1 minus phi n. So this is this summation, the changes in potential, but plus phi1 minus phi1 cancels, plus phi2 minus phi2 cancels. So the only terms that remain are phi at the very last data structure minus phi at the very first data structure, plus the total computational cost. Therefore, the main idea here is the total amortized cost is of n operations. So if you take any n operations, the total amortized cost is the actual cost plus the change in the potential from the final data structure minus the potential of the initial data structure. And therefore, here's the thing. If I can guarantee that for any sequence of n operations, if I can guarantee that any final data structure I get, phi d sub n, is greater than or equal to phi d sub 0, okay, for any sequence of n operations, if I start from some fixed initial data structure instance and I apply some sequence of n operations, I get to this nth data structure instance. Actually, this should be phi d n plus 1, I guess. Okay, so suppose I get here, then what I'm guaranteeing is that phi d plus n plus 1 is greater than or equal to phi d0. So this I need to guarantee. And if I can guarantee this, then the change in the potential and the actual cost means that the total amortized cost will be an upper bound on the actual cost. So the point is, if this happens, then the summation of Ci hat is going to be greater than or equal to summation of Ci. So this is the actual cost, and this is the total amortized cost. So the amortized costs are going to be an upper bound on the actual cost, provided my potential can be shown so that it at any data structure instance, it's greater than or equal to the one that really happens when you start out. This may be a little confusing. Let me try this with a few examples to actually show you. And these are examples we encountered in the previous lecture. So let's look at them. So let's define, so the idea here is this then. Let's define a potential phi d for any data structure instance d. We'll always identify an initial instance d0, usually the empty queue, empty stack, empty tree, and we will calculate phi d0. Typically, this will be set to 0. And then for any data structure d prime after any series of operations, you want to guarantee that phi d prime is greater than or equal to 0. So the potential at any point is greater than the starting potential. Okay, this is different from saying that potential cannot decrease. The potential can decrease, but the point is, if I start from d0, then the potential at any point must be greater than or equal to the potential at d0. So even though potential can decrease, it should still remain above the starting value. So potential should always remain above starting value. That's important. Okay, that's important. The potential can decrease, but it has to be remaining above the starting value. And the amortized cost of each operation is just the actual cost plus the change in potential. All right. So this is to summarize everything we have seen so far. Let me give you some examples. Let's start with the binary counter example. Okay. We analyzed this binary counter example. And if you remember using the accounting method, we said anytime you increment the counter and you make go from 0 to 1, I'm going to prepay an extra dollar on top of my actual cost so that when I go from 1 to 0, you notice that I use this extra cost that's already been prepaid to pay for this. So to pay for the flip back from 1 to 0, I use the prepaid $1. That was, if you remember from the previous lecture, that's what we did. But let's do it in a different way, directly using the potential method. And here we say the potential of any binary counter is just the number of 1 bits. Okay, it's just the number of 1 bits in the binary counter. And this is almost the same as before. We're just expressing it in a different way. So if you have 101101101, then the number of 1 bits is this. So 1, 2, 3, 4, 5, 6. So the potential is 6. And the idea here is it just is counting. If another way of thinking about it, it's counting all the $1s that you have prepaid. So it's counting all the prepaid costs. Initially, your counter is all 0, so its potential is 0. Any data structure B sub I, any intermediate counter has to have phi bi is greater than equal to 0 because you can have negative potential here. So you get phi bi is greater than phi 0. So any potential is above where you start. Now, what's the amortized cost of incrementing a data structure? So suppose you had k trailing ones. Suppose you had k trailing ones here. Then you're going to increment, and all of these are going to go to 0. All of these are going to go to 0. And this 0 is going to go to a 1. So the change in potential, this change in potential is you're going to have a minus k drop in potential and a plus 1 increase in potential because these ones are going to go to a 0. That's a minus k drop and a plus 1. So it's minus k plus 1 is a change in potential. The actual cost is k plus 1, so k plus 1. So the amortized cost is, so actual cost is k plus 1. Amortized cost is 1 plus 1, which is 2. All right. So that's going to be the overall amortized cost of each increment. It's the same argument. So if you think about it, it's essentially the same argument we used in the accounting method, except that now we are using something called a potential, which keeps track of the prepaid cost in a much more rigorous manner than before. Okay, let me look again at an example we saw previously, which is our dynamic arrays. So remember, in our dynamic arrays, we had the following situation where we had n allocated slots, and somehow this is the unallocated space. And the idea here was you would have n by 2 elements in your allocated slot, and these n by 2 elements don't have any prepaid costs. And then you have the ones that are past n by 2, which would all have $2 each prepaid so that you can copy. The way to express that is to say that the potential for a data structure is 2k minus n, where k is the number of elements and n is the total size of the data structure. So that's the allocated size. And remember, if I'm just inserting and I'm not deleting, then one of the things I can always prove is any data structure instance is always more than half full. Because the way I get to some size, let's say 128, was that previously I had a data structure of size 64, and that got full. So I must always be more than half plus 1 full. I must always be more than half full plus 1 element. So this potential 2k minus n is always greater than or equal to 0. Okay. The reason is you must always have k greater than n by 2 in this data structure. So k must always be greater than n by 2 in this data structure just by the very way we operate. Remember, there's no deletion, only insertion. Okay, so here's the idea. When initially the number of allocated elements k is 0, n is 0, so the initial data structure is always 0, and any potential is always greater than equal to 0. So this is good. It's a good potential function. All right. Now, suppose I add an extra element, right? Then there are just two possibilities. If I resize, then you basically double n. or you resize n, and then so just after resizing n is 2k, so just after resizing n is 2k, and so phi t is 0, otherwise 2k greater than n, so phi t greater than 0. This is just reiterating the argument that the data structure always has to be more than half full. So data structure always is more than half full. By the way it's designed, it's always is more than half full. That's all. It's reiterating the same argument. Okay, so let's get to the analysis of dynamic arrays then. So how do you think about dynamic arrays? So suppose you have phi t, which is 2k minus n, which is you have an array which has k elements already in it, and n is the total allocated size. Suppose you insert a new element and then move from t to t prime. Suppose no resizing happened, which is k less than n. So in this case, the new k is k plus 1, and the new n is just n. And the computation cost of this is 1. So the amortized cost is 1 plus the potential of the new data structure t prime minus the old data structure t. And if you do the math, it's 1 plus k prime is k plus 1. So it's 2k prime minus n prime plus 2k minus n. So this is minus, sorry, this is the change in potential. So this better be a minus. This is the change in potential. Now n prime and n are the same. This is just 2. The difference is 2, so it's 1 plus 2, which is 3. On the other hand, suppose resizing happened, then k prime, the new k is k plus 1. So here is what resizing means. K was equal to n. Therefore, the new k is going to be k plus 1. One element came in, one extra element inserted. And then the new n is 2n, because you double the size of the allocated space. So the new n prime is 2n, and the cost is n plus 1 or k plus 1, because you have to copy all these k elements here. You have to copy them over, and then this extra one element. So n plus 1. And if you do the math, the amortized cost is the actual computation cost plus change in potential. Actual computation cost is n plus 1. Change in potential is this minus this, which comes out to be 3. Again, it's the same argument we came up with for the accounting method. It's just that we are using a potential to make it more formal. Just to give you an example that we couldn't have done with the accounting method, let us talk about dynamic tables now with deletion as well as insertion. So now the table has some allocated space n and some number of elements k that have been allocated. And not only do we, when the whole thing gets full, not only do we expand and allocate a new one with 2n, okay, and copy over. Suppose we also do the following. Suppose if the table gets too empty, let's say if the table gets less than half full, let's say. So this is k, this is n. Suppose k is less than n by 2. Let's shrink it. Let's basically take this and shrink it to half its size. Let's go back. Okay, let's go back and shrink it to half its size. So what if we also allowed shrinking in addition to expanding? What happens to this table? Now, first thing we will note is that the amortized cost is going to be really bad. Why is that? Why is that? Let me give you an example that illustrates a very bad case. So think of a data structure that just got to full. Okay, so that just got full. And so now, just after it got full, you're going to reallocate this data structure, and you're going to copy over the elements. And here is the new element that got inserted. Okay, so this is 2n, and this is k plus 1. Now, the problem is, if I took this new element and I just deleted it, then it's going to get less than half full. So it's going to go back here. So if I just did a deletion of an element that I just inserted, I have to reallocate. So I have to reallocate and copy everything over again. I have to copy everything over again. Now, once I did a deletion, suppose I did an insertion, then I have to expand to twice, and then I have to do this again. So if I keep doing an insertion, deletion this way, then I'm going to tickle this halfway boundary, and I'm going to do reallocation, unallocation. And what will happen is the amortized cost of n operations will become O n squared. And in this case, theta n squared, because that's going to be bad. It's going to be bad. So this is bad. I don't want to keep inserting and deleting over and over again. That's going to cause reallocation and deallocation. So expanding and shrinking over and over again, and that's going to be bad. How do I deal with this problem? Well, the way to deal with this problem is something like this. So suppose I just expanded. Suppose I just expanded, right? You see, the next time I expand, previously, I had to fill in all of these elements before the next expansion. But for contraction, I don't have to do anything. I just have to delete one element to contract again. So what I will do is something like this. Instead of contracting when the table is half full, I'm only going to contract when the table is less than 1/4 full. So I'm going to allow you to keep some elements. So you will have to delete all of these elements to contract. Okay, I'm going to contract only if the table is less than 1/4 full. And then to avoid the repeat of the same situation, when I contract to a data structure where it's 1/4 full or it's half full, and then you still have half empty. So I'm going to contract to a data structure of half the size when it's 1/4 full. So contract to half the size when 1/4 full. Now that's going to avoid this continuous expansion and contraction. Why is that? Let me give you an example. So suppose my data structure currently has 100 elements in it and its total size is 200. Okay. Now, suppose I delete 50 elements. Suppose I delete 50 elements and then I delete one more. Suppose I delete 50 elements and then I delete one more. Then it's going to become less than 1/4 full. So then less than 1/4 full. And what I'm going to do is I'm going to take the 24 elements and I'm still going to put them in a data structure of size 50 or 48. In this case, 48. Okay, so the point here is I am still going to have these. So if you need to expand this data structure, you have to delete all these. You have to insert 24 more to expand, or you have to delete 12 to contract. So you can't immediately expand or contract. You still have to either insert 24 more or delete 12 to expand or contract. So that gives you some way to make the amortized cost manageable. So you're not going through expansion and contraction. If you have studied some physics, this phenomenon is called hysteresis. So I'm going to keep some hysteresis between expanding and contracting. So you'll have to do some extra work before you can contract again if you just expand it. So the idea here is we can do the following. So let me summarize. If k equals n, if the size of the allocated number of elements is equal to the allocation, then we are going to, when we try to insert, we are going to allocate. So this is on insertion. We're going to allocate a 2n size table and copy elements over. But if k less than n by 4, so if we get less than 1/4 of the elements of the allocated size, then we allocate a n by 2 size table and copy elements over. So we are going to do that, n by 2 size elements. And we are going to make the potential function like this, 2k minus n if k greater than half, or n by 2 minus k if k less than n by 2. Okay, so this is going to be the new potential function. It's actually much easier visualized on a graph. So I did that. So here is on a graph, here is k going from 0 elements to n elements. And really, it's going to be up to n by 4. You're never going to go here because I'm going to shrink. If I go here, if I try to go beyond this, I'm going to reallocate. Because this is full, I'm going to reallocate. Okay, so this is the limit of where I would go. And then the potential function looks like this. So it's going to be for k less than n by 2, it's in this blue potential function. This is n by 2 minus k, and otherwise it's 2k minus n as before. The cost of an insertion is the same as before. When you insert, the change in potential is going to be plus 2 for the change in potential, and the actual cost is plus 1. If you hit the reallocation, it's exactly the same analysis as before. It's still going to be 3. Okay. Now the interesting part, and of course, when you actually insert here, your cost of insertion is 0 because your potential change is -1 and the actual cost is 1, which cancels, so it's 0. On the other hand, what about deletion? Well, when you delete and no resizing happens, so when you're in this blue zone, when you are deleting and no resizing happens, well, the change in potential is +1 and the actual cost of the operation is +1. So the amortized cost is at most 2. On the other hand, when you delete and resizing does happen, what happens then? Well, if resizing does happen, let's do the math. You're going to go from this case where you're here to a new table where the new value of k is n/4 minus 1 because you've deleted 1, and the new value of 1 is n/2. So if you compare the potentials, the change in the potential is 1 minus n/4. The computation cost is the cost of copying over n/4 elements. So that's this. And so the amortized cost is this, 2. So once again, your amortized cost of n operations becomes 2n, and these operations can now be insert and delete. But the important thing is this: you have to wait for some time before you delete. The moment you expand, you cannot immediately trigger a deletion. And to do that, I put a gap. So I only delete if my data structure is less than 1/4 full. And when I delete, I go to a new data structure, which is half full. So with these two changes, I can make sure that my amortized cost still remains a constant times n. Okay, so I hope this was clear how we can build dynamic tables that both shrink and expand with amortized analysis. Thank you, and I will see you in the next lecture. Welcome back. So now we are going to talk about minimum spanning trees. All right. So what are minimum spanning trees? So these are a concept that work for undirected graphs. So let's take an example. And because the graph is undirected, I'm not going to draw directions for the edges. Okay. Now the edges in this graph are going to have weights. So these are weighted undirected graphs. So 3, 1, 2, 4, 6, 5. Let's have some weights. Now what do these weights mean? So these could be an example. These could be servers in a network. And the weights could be link traversal times or delays. All right. So this is an example of a weighted undirected graph. So we'll assume each of the links is a two-way link. So each channel can transmit packets on both sides from 1 to 2, from 2 to 1. And 3 is the measure of the time delay it takes to go from 1 to 2, or takes to go from 2 to 3, and so on. And this could be an example of warehouses, and the weights could be transportation costs between warehouses. All right, so these are examples of graphs where there are weights. All right. Now, what is a minimum spanning tree? So often enough, when you build a network like this, we build a network with more links than are strictly necessary. So we may even add one more link here, and let's say the cost is 10. Okay. Now, so one of the problems is, suppose I wanted to route packets from, let's say, 1 to 6. So I wanted to route packets from 1 to 6. Well, there are many possible ways to route a packet from 1 to 6. So I could go from 1 to 2 to 3 to 6. I could go from 1 to 2 to 4 to 3 to 6. I could go from 1 to 5 to 6. So there are many ways of routing a packet. So a standard algorithm is, if 2 is a switch here, okay, now 2 has 4 ports that are coming in, right? So there are 4, 1, 2, 3, 4 ports at 2. So let's say a packet comes in from 1. One of the strategies that 2 could use is a strategy that's known as flooding. So what it could simply do is whatever message comes in from 1, it could simply broadcast it on all the 3 ports. So it's going to reach 3, it's going to reach 4, and it's going to reach 5. It's not going to send it back to 1 because, let's say, it's intelligent enough to know that I'm not going to send it back to you if a message came from you, but I'm going to send it to everyone else. And this is called flooding, broadcasting. In sometimes it's called gossiping, even though that's slightly different terminology, so we won't use that terminology too much. It's called flooding, broadcasting, and so on. Okay, so this is an example of a routing algorithm. So if something comes in from one of the ports, I will just send it to every other port which it's not coming from. So when a packet comes, message comes from 1 to 2, 2 is going to send it to 3, 4, and 5. Now what about 3? Well, a message came in from 3, so it's going to send it to 6. And let's say 6 is the destination, so the message reached the destination. But it's also going to send it to 4. 4 is also going to send it to 2. 2 is also going to send it to 1. So as you can see, because of these cycles, flooding is going to be bad because it's going to keep resending the message over and over again. It's like it's going to keep circulating. And 6 is going to get the message from so many sources that it's going to get confused. So flooding takes a lot of work. So flooding means lots of lost bandwidth because I'm sending useless message over and over again because of cycles in my network, okay? Excuse me. And furthermore, because there are multiple ways to reach 6, 6 is going to get the same message 3 times, which is another way bandwidth is wasted. So bandwidth is wasted because of 2 things. One is there are cycles, and second is there are multiple ways by which I can get from a given source to a given destination. So how do we solve this problem? On the other hand, why would we like to do flooding? Well, the reason we would like to do flooding is it's brain dead. Okay, the algorithm is super simple, and internet switches, believe it or not, they are processing a lot of traffic volume. So a lot of traffic is coming to me, especially if I'm in the core of the internet. A lot of traffic is coming to me if I'm Verizon, and I need to route it quickly. I can't be making a decision every time. Oh, Sriram wants to send a packet to Google. Let me send it through this port. If I start making this decision every single time, life is going to be difficult. So I want to make simple decisions and I want to make it fast. All right. If I wanted to do that, then how do I move about this process, right? So here is how I do it. All right. So what I do is I'm going to construct out of this network, I'm going to remove some edges. Or said in the positive, retain some edges. I'm going to retain some of the links, and I'm going to retire or temporarily retire some of these links. So for example, I could take 1 to 2, that's a necessary link. I could take 2 to 3. I could take 3 to 6, and then I could take 2 to 4. Then I could take 2 to 5. So here I am retaining some of these edges. I'm retaining 1 to 2, I'm retaining 2 to 3, I'm retaining 3 to 6, I'm retaining 2 to 4, I'm retaining 2 to 5. Okay, so retain, instead of some, let me say enough edges such that number 1, the resulting graph has to be acyclic. I should not make a cycle up in the graph. So no cycles in this graph. And number 2, it is fully connected. Strongly connected. What does it mean? There is a route from 1 to 6. There is a route from 6 to 1. There is a route from 4 to 1. There is a route from 1 to 4. There is a route from 5 to 2, 2 to 5, 5 to 3, 3 to 5. So every node is reachable to every other node. And what is the name of a graph that's acyclic and strongly connected? Well, that's a tree. So I want to retain enough edges to create a tree, and such a tree has a name. It's called a spanning tree. All right. So now we are encountered the concept of a spanning tree. So what is a spanning tree? A spanning tree is a subset of edges First of all, it's a subset of edges. So let me call it the subset of edges, S, subset of E. So it's a subset of edges such that the graph of vertices with the edges S is a tree. Okay, so it's strongly connected and acyclic. That makes it a tree. All right. So first of all, a spanning tree can only be built if your original graph is itself a strongly connected graph, which means you cannot have islands in your graph that are separate from the rest of the graph. So assuming that your original graph is strongly connected, I want to find a spanning tree. Not only that, I want to find a spanning tree which is minimum or minimal. So a minimal spanning tree is a spanning tree such that the sum of the edge weights is as small as possible. So among all the spanning trees, find me one spanning tree that minimizes the sum of the weights of the edges. So for example, here is the spanning tree. What is the sum of the weights of the edges? Okay, so 3 plus 1 plus 4 plus 2 plus 6. So 17. Let's take an example of another spanning tree. So we can go from 1 to 2 to 5 to 6. From 6 we can go to 3, and from 3 we can go to 4. So this is another example of a spanning tree of the same graph. And what are the edge weights? 3 plus 6, 9 plus 10, 19 plus 4, 23 plus 5, 28. So I would prefer this spanning tree here over the other spanning tree that I have shown. So given a graph G, given an undirected graph G, also fully connected or strongly connected undirected graph G. So our undirected graph is weighted, strongly connected, undirected graph G like this. I want to find a minimal spanning tree, a spanning tree of the graph whose sum of edge weights is as small as possible. Now imagine if I found such a spanning tree. Well, this is going to be my routing tree. So such a tree can become my routing tree. What does it mean? So if a packet comes from 1 to 2, okay, if a packet comes from 1 to 2 and the destination of this packet is to 6, well, there is no need to flood anymore, because it's a spanning tree. I know that there is exactly one port that I can send out to reach 6. I know that I can reach 6 by going out to 3. Okay, and so what each node does is build something called a routing table. It builds something called a routing table. So the routing table says, if my destination is 6, send the packet immediately to 3. If my destination is 5, send it to 5. If my destination is 4, send it to 4. So now I can build this routing table, and this routing table tells me if a packet comes in from 1, destination is 6, I know exactly where to send it to. If the destination is 5, I know. So there is exactly one for every destination. There is exactly one outgoing edge that I can send things out to. Okay, so if it comes from 3 with a destination, so if it comes from 6, for example, to 3 with a destination of 5, 3's routing table is going to tell it to send it to 2. All right, so there is no more need for flooding. There is no more need for flooding. Number one. Number two, even if I flooded the network, what you will see is that first of all, that flooded message is not going to persist. So even if I were dumb enough to flood the network, okay, I didn't want to keep this routing table business, I don't want to flood the network, I'll still flood the network. So I flood a message from 1 to 2, I broadcast it to all the descendants of 2 along the spanning tree. Well, that's going to reach 5, it's going to reach 4, it's going to reach 3. 3 is going to send it further to 6, but 4 is not going to send it further because I don't send it on the incoming link, I don't send it back, so I'm not going to send it further. So if you notice, even if I decided to broadcast, the message is going to traverse and reach every node and traverse every edge exactly once, which is beautiful. Even if I decided to flood, I'm going to take a hit, but it's not going to be as bad as flooding the original network. All right, so now you can start to begin to see why minimal spanning tree routing is a very, very important concept, because if I route along this minimum spanning tree, and let me say that for every source destination pairs are equally likely for me, then in the end I end up with the best possible average time. So on the average, I will end up paying the least amount of time possible, because time here is money. So if I had warehouse locations and these were transportation costs, and there was equal amount of traffic from all the warehouses to all the other warehouses, like let's say it's equally traversed. If I shipped my goods along these spanning tree edges, then I will find myself having to pay the minimum transportation cost overall. So this gives me, computing the spanning tree gives me a strategy for sending traffic. So I will never send a traffic from 5 to 6, I would never send, those edges are retired, I would never send the traffic from 3 to 4, I would only try to send the traffic along the spanning tree edges. Now you may imagine, why do people bother sending 5 to 6 and 3 to 4? Well, often links go down, roads have problems, roads have traffic congestion, internet links can go down. And if they go down, then what I will do is I will try and revive these links that are backup. So if this link goes down, then I will revive the 3 to 4 link. So is this really being used in the internet? Yes. So spanning tree routing is an example of an algorithm that's actually used in the internet. It's slightly more sophisticated because it's done in a distributed fashion across all the nodes of the network, but still it's a very, very important algorithm. And so spanning trees tend to be super important, and we will have to study algorithms that, given a graph, computes the minimum spanning tree, minimum weight spanning tree of the graph. All right, so we will look at this algorithm coming right up. Okay, so now we are going to look at algorithms for minimum spanning trees. By the way, I shouldn't call it minimum spanning tree. Typically, it's called minimal spanning tree. In mathematics, minimal acknowledges that there could be many spanning trees with the same weights, and each of them is equally acceptable. Minimum typically implies that there is exactly one that achieves the minimum. It's a very technical point. Just read minimal spanning tree whenever I say minimum. All right, let's look at an example. And first, before we go into the algorithms, there are two very interesting algorithms. One is an algorithm by Prim. It's called Prim's algorithm. Another is a very interesting algorithm as well. It's an algorithm by Kruskal, Kruskal's algorithm. Both are equally interesting algorithms, and they are both greedy. So this is an poster child for greedy algorithms, and they are both based on very similar principle. They just exploit it differently. So let us first talk about this principle and then talk about how do the two algorithms exploit it separately for each algorithm. All right, let's take an example. So let's take an example. All right, let me put some weights. All right, and let us figure out that we have a minimum spanning tree. All right, and let me color the edges in the minimum spanning tree with pink. Okay, every non-minimum spanning tree edge will still remain green. Okay, so let me actually color it in pink without, so 1 to 2 is going to be part of it, let's say 1 to 3, all right, 2 to 4, all right, 4 to 5, all right, and then 4 to 7, and 6 to 7. The other edges are not going to be part of it, so I'm going to make them dashed. Hopefully you can still see them. So that's going to be the minimum spanning tree. The edges that are not going to be part of the minimum spanning tree are 2 to 3, 2 to 5, 5 to 6. All right. So I claim that the edges that I have shown, oh, by the way, 3 to 4 is also not part of the MST. All right, so the MST itself is, let me redraw it again. It's going to have 1, it's going to have 3, it's going to have 2, 4, 5, 7, and 6, and the total weight is going to be 1 plus 1, 2, 2 plus 1, 3, 3 plus 1, 4, 4 plus 2, 6, 6 plus 1, 7. So I claim this is the minimum spanning tree. Now there is a very, very simple principle. So there is a simple principle to know when a spanning tree is minimum. So if I take any of these edges that did not make it, okay, so number 1, take an edge that did not make it. So take an edge that's not in T, that's not in T. So for example, let's take the edge 2 to 5. Its weight is 3. Temporarily add it to the tree. So take any edge that's not added to the tree. So suppose I added 2 to 5 to the tree, it's no longer a tree, right? The reason it's no longer a tree is it now has a cycle. What's that cycle? The cycle is 2, 4, 5, and then the extra edge 2 to 5. So it's going to have a cycle. Well, in fact, it's going to have exactly one cycle. The cycle is going to be from 2 to 5, right? Now, all the edges in T along the cycle must have weight less than or equal to, so let's call this edge E, the weight of E. So which means that if I added 2 to 5, its weight is 3. Now let me look at the edges along the cycle that are already in the tree, 2 to 4, 4 to 5. Well, those must have weights that are less than 3. Okay, that is the principle. So take any edge that's not in the tree. So let us take another edge, 2 to 3. Its weight is 2. Let us take from 2 to 3, let us take all the edges that are in the tree. So those weights are 1 and 1. 1 is less than 2, 1 is less than 2. Let us take 5 to 6. Its weight is 3. Let us take the path from 5 to 6 along the tree. Its weights are 1 less than 3, 2 less than 3, 1 less than 3. So this is the principle. So any MST, any minimum spanning tree, must satisfy this property, this principle, and if it satisfies the principle, it is in fact a minimum spanning tree. Okay, it's an if and only if condition. Now why is that the case? Let us, for example, imagine there was an edge here from 1 to 6, like a giant shortcut, whose weight, let us say, was, I don't know, 1. So suppose there was an edge from 1 to 6 whose weight was 1. But let us say this minimum spanning tree did not consider this edge, right? It did not consider this edge. So it considered So suppose I traverse from 1 to 6. So 1, weight is 1, so far so good, less than or equal to. Now if I look at 2 to 7, its weight is 2, and 7 to 6, its weight is 1. So I could do a surgery to the spanning tree. So what is the surgery I do? Well, let me take this offending edge, whose weight is actually greater than the weight of this edge that was left out. Let me delete it, let me take it out of the spanning tree, and instead add this new edge from 1 to 6. If I did that, then I still get a spanning tree. So if I take T union this E, but if I remove this edge F such that the weight of F was greater than weight of E, then the overall sum of the weights will have to decrease, right? So I have taken an edge of weight 2 in the original tree out. I took it out and I replaced it with an edge of weight 1. So the entire weight of the tree has to go down from 7 to 6. So this is not going to be possible in the minimum spanning tree. If you already claimed it's the minimum weight spanning tree, sum of the edge weights is minimum, I should not be able to take an edge out, add a new edge in, keep it a spanning tree, and reduce the weight all at the same time. Take an edge out, add a new edge in, maintain a spanning tree, all at the same time while decreasing the weight. Should not be possible. And therefore, if you found a true minimum spanning tree, it has to satisfy the principle. And what is this all-important principle? This all-important principle is the following. If you take any edge E that's outside, so I'm fixing the example back, if you take any edge E that's not in the spanning tree, take an edge E not in the spanning tree but in the original graph, but not in the spanning tree, temporarily add this edge to the tree, okay? If you temporarily add this edge to the tree, so this edge is no longer there, okay, so I took it away. But take any edge that was originally in the graph, like the edge from 3 to 4, temporarily add it to the tree, consider it adding it to the tree, it creates a cycle. Traverse the cycle along the tree. All the edges in the tree that were along the cycle must have weight which is less than this new edge that you're trying to add. So if this new edge has weight 2, these edges have weight 1, then that's okay. And this must hold for every edge not in the tree. Okay, and if your tree satisfies this important property, then it is a minimum spanning tree. All right, and the proof is by contradiction. All right, if that much is clear, then we are now ready to look at two algorithms, Prim's algorithm and Kruskal's algorithm, starting with Prim's algorithm, that are going to exploit this principle to make up a spanning tree. Hopefully this principle is clear. If it's not clear, plenty of examples should be taken up and you should verify this principle. Take an edge not in the tree, look at the path from one of the points in the edge to the other end point in the edge, or look at the cycle that's created when you add it back to the tree and traverse that cycle along the tree. Then the nodes, edges that are already in the tree must have less weight than the new edge you are proposing to add. If that is indeed the case, then you have a minimum spanning tree. All right, very good. Okay, I will see you in the next lecture where we are going to talk about Prim's algorithm. Okay, so welcome back. And now we will study the other kind of algorithm for computing minimum spanning tree, and that's called Kruskal's algorithm. So we already saw Prim's algorithm, which worked in a way where we grow a tree starting from 0 nodes to n nodes. And when we have n nodes, we are done. N is the number of nodes in the graph, and that's how we worked in Prim's algorithm. So this was Prim. In Kruskal's algorithm, the intermediate state of this algorithm is not going to be a tree, it's going to be a forest. So the intermediate state is going to be many different, little minimal spanning trees that we will then try to connect up. That's how this algorithm works. So initially, it's going to be a forest of all nodes just by themselves. So in this example, Let me just work it out through an example. Okay. So it's going to be an isolated forest of every node by itself. That's going to be the initial state of this algorithm. So then the idea is sort the edges in ascending order. So I'm going to take all the edges and sort them in ascending order of weights. All right. So let us take and each of the edges in turn, starting from lower weight edges to higher weight edges. So let's say 3 to 6 is the lowest weight edge. So I'm going to add 3 to 6 if it's going to connect two different trees. Okay. So for all edges in sorted order, if E connects different forest, so if E connects two different trees in the forest, okay, so it's getting hard to see because the marker is losing its potency. So I'm going to, instead of writing it down, I'm just going to spell it out. So if an edge connects two different trees in the forest, add it and make them into a single tree. So if I took this edge 3 to 6, well, it connects two different trees. I'm going to add it, make it into a single tree. Let's keep iterating. So 1 to 3, it's going to connect two different trees in the forest. So add it and move on. So now 4 to 5 is connecting two different trees. So add it and move on. 5 to 6 is connecting two different trees. So I'm considering the edges in increasing order of their weights and just doing this. 6 to 7, okay. Now all weight 1 edges have been considered. So let me consider a weight 2 edge. So 1 to 4 is of weight 2. But if I connect 1 and 4, they belong to the same tree in the forest. So now the forest has 3 trees, right? 1, 3, 6, 5, these are going to be part of one tree. 2 and 8 are going to be all by themselves in a separate forest, right? So if I try to connect 1 and 4, that's not going to connect two different forests. It's an edge inside the same tree, so I'm not going to connect 1 and 4. Let me connect 4 and 2. Well, 4 and 2 are connecting two different trees that are in two different parts of the forest, so I'm going to connect 4 and 2. 3 and 8. And now I consider 8 and 7, which is an edge of weight 3. I'm not going to consider it because it's connecting the same tree and so on. So what is the idea? Sort the edges in increasing ascending order. For all edges E in sorted order, if E connects two different trees, well, if E connects two different trees, then just add E to the forest, which means that the trees are going to get connected and they are going to become the same tree. All right, that's it. So that's the entire algorithm. So hopefully the algorithm is clear, even though my marker has become quite unclear at this point. I hope this algorithm is clear, and it's a very, very simple algorithm. All right, what is its time complexity? Well, number one, to sort, I need time E log E. To sort all the edges in ascending order, I need time which is proportional to E log E, which is the number of edges log the number of edges. You can use quicksort with median of median tricks or any sorting algorithm you learned which works in this time, and that's the best sorting algorithm we know. Okay, number one. Number two, what do we need to do? As we go through these edges, we need to see, does E connect two different trees? Okay, now this is a step which I have not taught you how to do, but this step is achieved using something called a union find data structure. Okay, and take my word for it, if you use a union find data structure, the total time taken is something like this. It's something like V and a very, very strange function called log star V. Okay, this is slightly more advanced, not too much more advanced, just slightly more advanced than what we teach in this class, and this is called the inverse Ackermann function. It's a very, very slow growing function, so it's almost linear. Okay, so the overall time is simply going to be this. Now, if you do it in a naive way, if you simply do it in a naive way, the total time taken for this is roughly what? So you need to find out if E connects two different trees. So you need to find out if there is a path already from the head of E to the tail of E. And in a tree, that takes about V time. So this whole thing can take E times V if I do it naively. So if I wanted to do this algorithm naively, the running time is EV plus E log E. If I do it more intelligently, I can get it down drastically. Instead of V times E, I can get it to V log star V. All right, and that's going to take a little bit more effort using a data structure called a union find data structure. All right, so this is Kruskal's algorithm. It's a very, very simple algorithm, not too difficult to implement actually, and it just goes through the edges in the ascending order, maintains a forest. Whenever the current edge connects two different trees in the forest, I connect those two different trees, and those two trees become one tree because they are now connected. And as I grow this tree, I get, and I'm exhausted through the list of all the edges, I am done. All right, so that's it. So hopefully this was clear. Very, very simple algorithm. The only complexity is trying to implement it efficiently. Requires you to know this data structure called a union find data structure, which we did not cover in the class. So I hope this is clear, and the complexity you get, so this alpha is in place of log star, is something like E log E plus V, alpha being the inverse Ackermann function, also sometimes written as log star of V. All right, hopefully this is clear, and this is a simple algorithm. The implementation and the bookkeeping is slightly hard, so which is why we don't teach it at this level. Thank you so much. All right, so welcome to this lecture on union find data structures, which is going to be a very interesting class of data structures. So let me briefly explain what the main problem of union find data structures is. So in many applications, we wish to maintain a family, and let's call this family of disjoint sets. So let's write this down. So in many applications, we need this family, hold on, of disjoint sets. So what does this family of disjoint set means? So it means the following. So suppose you have a universe, and let's say this universe has 6 elements, okay? And these are all the elements that we care about. And a family of disjoint sets looks like this. So a family of disjoint sets could look like this. So for example, we could have one set 1, 2, let's call this S1. Let's call the other set 3, 4, 5. And let's call this third set 6. All right. So you have a collection of subsets of your universe. Okay. So collection of subsets of your universe U, and this is going to define a family. Important thing is the elements of your family are mutually disjoint. So the intersection of two sets is empty. Okay, and this is the empty set. So you have that the elements of two are mutually disjoint. One more thing by convention is every member of this family is going to have a representative element. So the representative of S1 is 2, the representative of S2 is 3, and the representative of S3 is 6. So we are going to maintain a representative for every family. Why is this important? So this occurs a lot in mathematics. So for example, in mathematics, we are constantly needing to represent, and I'll just mention this in case you've seen this before, equivalence relations. So one way of representing equivalence relations is through their equivalence classes. Equivalence classes, in case you're aware, what an equivalence class is, you would represent them by equivalence classes, which are essentially going to be this family of disjoint subsets of your overall set U. And you would have a representative for each of these equivalence classes. This is an example. Another example is, for example, think about a graph, and we've already seen this before in last lesson or last week, hopefully. Think of a graph and think of all the strongly connected components of this graph. So 1, 2, 3, 4, 5, 6. So you have your strongly connected component 1 by itself, 2, 3, 4 by themselves, and 5, 6. So this is an example where you can maintain these strongly connected components as a family of disjoint subsets. Disjoint subsets of your set of vertices. So this is an example where we would do this. And this week we are going to study algorithms for minimum spanning tree on graphs, where this is going to be useful as well. So we are going to see how this is going to be useful. All right. So these are the reasons why we would like to have disjoint families of disjoint subsets. Now, as a data structure, we would like to represent these disjoint subsets. So how do we represent these disjoint subsets? And the idea here is we will study disjoint set representation. So what is this? So a disjoint set representation is we want to represent a family of subsets. For example, in this, let's say 4, 6, 5, 7, 8 by itself. So let's say we have this family of subsets, and each one of them we have a designated representative. All right. And so we would like to represent this. An easy way to represent this may be through something like this. So it could be like a reverse tree data structure. So imagine 3 as the root pointing to itself, and let's say 2 points to 3, 1 points to 2. So this could be like a representation. So imagine in another subset, 4 is by itself, 6 is right here. Imagine in another subset, 5 here, 7 here, 7 points to 5. So the representative is always going to be the root of this tree. And then the directions of the pointers are reversed. So from every node, you have a pointer back to its parent. And the root is going to be the representative. So from 6, you have a node to 4. From 7 to 5, 8 is by itself. So this is a representation. And these are called forests. Why are they called forests? Because a forest, remember, is a collection of individual trees. So these are trees in our forest. So each set is a tree, except that the direction of edges is somehow reversed. We still think of it as a tree. And in the root, we designate the root by just having a self loop to itself, just to designate the root by convention. And that would be the representative for every set. Okay, so these are called disjoint set forests. Okay, these are called disjoint set forests. Okay, and what are the operations we would like to support on this data structure? So the first operation we would like to support is the operation called make set, and you would give an element j, and I would like to make a set j. And the idea here is you would take j as a singleton by itself, and you would make a self loop around it. Okay, and then you would add it to your forest. Now, the point is you cannot do this if j is already present somewhere. Then it leads to an error. So let's assume that j is not present anywhere else and j is fresh. So you can always take j and make a fresh node out of it. So that's one operation. So that's the make set operation. This is how we are going to create singleton set. All right. The second operation is the find operation. So suppose I call find on an element, let's say 1. The idea here is to look for the set that contains 1 and then find the representative of that set. So in this case, find of 1 should give me back 3, because 1 in turn points to 2, in turn points to 3. So if I chase the parent pointer until I find the node whose parent is itself, I get to its representative. For example, find of 8, this is 8, find of 8 should return back 8. Okay, so these are the find operation, which is the second operation we wish to support, make set, find. And the last operation we wish to support is the union operation. And here I'll give you two numbers, like let's say 2 and 7. I wish to take the union of 2 and 7. And the idea is 2 leads us to the set that's represented by 3, and 7 leads us to the set that represented by 5. So we take this set S1 and this set S3. Okay. And when you do a union, you have to create a new set which merges the two sets. So now you have to create the set 1, 2, 3, 5, 7. And what do you do in terms of the tree? So you're going to take these two trees and you're going to merge them. So let's say 3 becomes the representative. You have what used to be a different set, 5 and 7. 5 used to point to itself in the past. It no longer points to itself because it's no longer the root. Now it simply points to 3 because 3 has taken over as the representative. And then 1 and 2, 1 and 2 are going to be children of 3 as usual, like this. So this is going to be the new set formed through union. Okay, these are the three operations. Notice there is no deletion operation, there is no like disconnect or disunion operation. There's just make set, find, and union. And these are the three operations we wish to support. Okay, now I hope this description is okay. So for example, let me just take an example. Let's do this operations make set of 1, make set of 2, make set of 3, find 3, and then let's do union 3 comma 1, and then let's do union 1 comma 2. Let's say these are the operations, and then let's say find 2. What is going to happen? So make set of 1 by itself is going to create a node 1 just by itself. Make set of 2 by itself is going to create a node 2 with a self loop. Make set of 3 is going to create a node 3 with self loop. Find of 3 is just going to return 3. Union of 3, 1 is going to create something like this, 1, and it's an arbitrary choice which one is the representative. So, but now 3 has become the representative. Union of 1, 2, well, when I have 1, its representative is 3, and if I union with 2, let's say now creates this tree. So these two trees are no longer there. They have been merged into this tree. Okay. Now union of 1, 2 means this tree goes out of existence, and you have a single tree in your forest. Okay, and find of 2 should return back 3 in this case. Okay, so I hope these operations are clear and what they do is clear. Now comes the interesting question: how do we do this and what's the complexity? All right, so it turns out in the worst case you're going to have a very bad complexity unless you're careful. So let me give you an example. Suppose I do make set of 1 all the way to make set of n. And let's say I do union of 1, 2, and then I do union of, let's say I have union 1 and 2, I union 2 and 3, until I union n minus 1 and n. So I just union things in pairs, 2, 1, 2, 2, 3. Eventually, you're going to combine everything into a single set. And then let's say I do find of 1. So what can happen is something like this. So initially, after all my make set, I am left with n distinct trees in my forest, which have 1 and n. But when I do union of 1, 2, let's say I always create the bigger number as the representative. That's my policy. So then when I do union of 1, 2, I have 2 and 1 points to 2. Suppose I do union of 2, 3, and let's say the bigger number is the representative. Now I have created this chain 1, 2, 3. Okay. Likewise, if I go all the way and to the end, I create this enormous chain 1, 2, 3, and it's going to go all the way to n, which is going to be the representative. So suppose I keep doing find of 1. If I do find of 1, I have to traverse this entire pointer chain. I have to traverse this entire pointer chain all the way to the root, and I discover its end. Suppose I keep doing repeatedly. So suppose so far what I have done, I have done n make set operations, n make set operations. I have done n union operations, or more precisely, n minus 1 union. And let's say I keep doing find of 1. Somehow I just keep doing it again and again and again. And I'm forcing you to traverse this entire pointer chain again and again and again. All right. And let's say I do it m times. What's the total complexity of all these operations together? Well, n make sets is going to be n. N unions is again going to be n. Okay, roughly theta n, theta n, theta n. Okay. Now the problem with each of these find operations is they are going to traverse the entire pointer chain, so it's n times, right? So this is going to be theta n plus theta n plus theta m times n. So this is going to be m times n. So this is going to be a lot. So if n is in the order of 1 million, then each of these find operations is going to take 1 million. Okay, this is not good, not good. Can we do any better? Okay, and so to do better, we are going to look at two ideas. The first idea is called union by rank. Okay, and the idea here is the reason we were able to create this long chain, was a rather arbitrary policy that when we did union, we would select one of these to be the representative, and we would always select the representative to be the larger number, right? That's not a good idea. So what we are going to do in union by rank is we are going to associate with every tree. So suppose this is how a tree looks in our, let's say this is a tree, okay, as an example. This is how a tree would look, right? In the midst of this algorithm, let's say this is how a tree would look. We are going to maintain with every node a notion of rank, where rank is the length of the path from the root to a leaf, right? So the length of the longest path. So in this case, the length of the longest path is 3, okay? Whereas, and you can realize it by this path or this path, the path going from 1 to 3 or the path going 1 to 4. All right, and that's 3. The length of the longest path is 1. The rank of this is 2, 1, and 1. Okay, so we associate a rank with every node, especially with the leaf, which is going to maintain the depth of the tree. It's basically another name for the depth or the length of the longest path from that node to a leaf node. In this case, we don't have nil or sentinels. We just use 4 as a leaf. Okay, let's call this the rank. All right. Now, what we do is, suppose we are going to union this tree with another tree. Let's call this tree 1, 2, 3, 4, 5. Let's have 6, 7, and 8 in this tree. So let's say 6, 7, 8. And let's say this tree is like this, and the rank of the root is 2. Okay, the rank of the root is 2. And then the rank here are 1 and 1. Okay, the ranks of the non-root nodes do not matter. So it doesn't really matter to know the ranks here. So we might as well not worry about the ranks here. But the rank of the root is something I worry about, and that's 2. So suppose I union these two. Okay, so suppose I compute the union of these two trees in my forest. Then what I do is I say the tree with bigger rank becomes the representative. So in other words, if you have a rank 3 and rank 2, the tree with rank 3 is going to become the representative. So in this case, 1 is going to become the representative, and then the node with 6 is going to become a subtree of 1. So like that. Okay, and you're going to have the remaining nodes. So you're going to have 2, you're going to have 4, you're going to have 3. So now this entire tree will continue to have rank 3 because this tree has rank 2, so it gets subsumed. Okay, so this entire tree is going to continue to have rank 3. So the rule is the bigger root rank is going to become the representative. Now, in case they are of the same rank, let me give you an example where they're of the same rank. Here, let's go with 2, and let's go with 3, and let's say the rank of this is 2. Okay, let's go with another node. We are unioning it. Let's say 1, 3, not 3. You cannot have 3 again because then it would no longer be disjoint. Let's go with 1, 7, and 8. 1, 7, and 8. And this rank is also 2. So they're both of equal rank. So I can randomly select one of them. So let me select 1 as my representative. And then 7 and 8 continue to be its children. And then 2 gets subsumed here. 3. And then the rank of 1 becomes 1 more. So it's now its rank is 3. This rank is 2. Rank is 1. Rank is 1. Rank is 1. So now you randomly choose either one of them to break the tie. You can break the tie arbitrarily. And when you break the tie, you have this. Okay. So this is kind of going to be important. Why is this important? So the reason this is going to be important is this strategy now disallows our tree from growing too much. So let us go back to our pathological example again. Okay, so let's go back to this pathological example again from way back. All right, now how is this tree going to grow if we went strictly by rank? If we went strictly by rank, this is going to grow like this. So let me just give you an illustration of how this tree grows. So then the make set again is going to produce these singletons from 1 to n, because that's what make set does. When I union 1 and 2, I'm going to create 1, 2, okay? And the rank of this node is going to be 2, and this rank is 1. Now, when I union 2 and 3, 2's representative is 1, and when I do union this with 3, 3 has a rank 1. So what's going to happen is this node with the lower rank is going to become the child of the node with the higher rank. So 3 is going to get subsumed here, and the rank remains 2. And likewise, when I do union of, let's say, 3 and 4, 3 representative is 1. I just find that out. And then if I union that with 4, 4 itself just has rank 1, right? And so this is going to subsume. And again, I'm going to have 1 as the root. And then I'm going to have 2, 3, 4. So when I finish all the unions, instead of that long branch, I'm just going to end up with a single root 1. And then all the other n-1 nodes are just its children, and the rank is just 2. So then if I do any find operation, it's just going to have unit cost. Any find operation has unit cost, cannot have more than a single unit of cost or constant cost. So now if I do this, then if I do m find operations, n union, and n make sets, then I have simply theta n plus theta n plus theta m, which is almost constant time per operation in this case. So this sounds like a good idea, right? So this sounds like a good idea, okay? And this is called union by rank. And what is union by rank? Just remember, union by rank means that when I union two trees, T1 and T2, I look at the rank of the roots, and then whichever one has the larger rank, then T1's root becomes representative. Otherwise, if R2 has the larger rank, then T2's root becomes representative. Or if they are the same rank, then break ties arbitrarily and make one of them representative. Okay. Now notice one interesting property. In these two cases, whichever one becomes the root, its rank does not grow, because let's say R1 was larger than R2. Then T1's root becomes the root of the whole thing, and T2 just subsumes itself underneath T1, and the rest of T1 is here. So here is the root of T1, here is the rest of T1, T2 just subsumes, and the rank remains R1. So if R1 is greater than R2, the rank remains the same, okay? So if the two trees, when you do a union, if the two trees have different ranks, then rank remains same. On the other hand, if they have the same rank, which means T1 has the same rank R, T2 has the same rank R, then when you union, arbitrarily one of them is made the root. Let's say T2 is made the root. then you have the rest of T2 here, and then T1 itself becomes a child with rank R. So in this case, the rank of T2 increases and becomes R plus 1. So if two trees have same rank, then what happens is union will increase the rank of the root, whichever ends up being the root, by 1. I hope this is clear. This is kind of interesting, but this is important in understanding why we are doing this important step of making things ordered by rank. Okay. And now what will happen is when we order things by rank, we will get some really good advantages. We can prove that then the size of the tree, suppose we did n make set operations, and we created, let's say, n different singletons in the first place, and then we do arbitrary series of union and find operations. Okay. But let's say we do an arbitrary series of union operations. So we created nodes 1 to n, and we are arbitrarily unioning them in some order. Okay. And then we are doing arbitrary find. What we can show is that the rank of the tree, the rank of whatever tree you end up with, is always going to be less than or equal to log n. Okay, it can't be more than much. It can't be much more than log n. Okay, so we are going to show this in a second. All right. When we show this, we'll show that the complexity of the find operations cannot be too bad either. So it's going to be really good. And this all depends on the following strategy of this union by rank. Okay, union by rank. So this all depends on doing things as union by rank strategy. Okay, so let's examine this in a little bit more detail coming up in a second. Okay, so let's look at this again, right? So what is happening here? So my goal is to convince you that suppose I created somehow n singleton sets, and I'm going to do union in some arbitrary order. So I can do union 1, 2, union 3, 4, union 7, 8. So some arbitrary order of unions until I create a single big tree, right? So I create a single big tree with all of them underneath. So we already saw one example where we did union 1, 2, and then we did union 2, 3, and then we did union 3, 4, and so on. Initially, we found that if you merge the trees arbitrarily or by some simple brain dead strategy, then you can create really bad depth. So you can create large trees of some rank n. So you can create these large trees, and then this is going to make find very hard because find has to traverse all the way from the leaf to the root in the worst case. But we saw that if you did the rank strategy, then if you did union 1, 2, 2, 3, then you end up actually creating a very nice, simple, small tree. Okay. Now the question is, what's the worst I can do in terms of the rank of the tree? Like, what's the biggest rank tree I can create, considering all possible, clever ways of doing union, where my goal is to create the biggest rank possible, or the maximum depth possible. What would be the maximum depth? I claim the following fact. Okay, and here is the idea. How do I create a tree of rank R plus 1? So what kind of a union creates a tree of rank R plus 1? We already saw this. The only way to create a union of a tree of rank R plus 1 is to take the union of two trees of rank R each. So the idea here is that if you wanted to create a tree of rank R plus 1, you had to take two trees, each of whose rank is R, and you have to union them. And then one of the trees becomes the child of another tree, which becomes the representative. Okay, so this gives us the following interesting fact. Okay, let us call n sub r, or n of r. So let us designate n of r the minimum number of nodes a tree with rank R must have. Which means that it cannot have smaller number of nodes than that. For example, n of 1 is 1. A tree with rank 1 must have at least one node. Okay, so n of 1 is 1. What about n of 2? What's the minimum number of nodes a tree with rank 2 has? So here is an example of a tree with rank 2. The minimum number of nodes it can have is 2. What about n of 3? What's the minimum number of nodes you can get away for a tree with rank 3? And remember, you can only construct, you have to have the following invariant, that the only way to create a tree of rank plus 1 is to union two trees of rank at least r. Okay, so if you wanted to do that, then a tree of rank 3 must have at least one child of rank 2. So one of the subtrees must be of rank 2. So you can have like something like this. Then the other one must have rank at least 1. So something like this. So this is the smallest tree I can consider of rank 3 that can be formed with the rank strategy. There is no other way to form a different tree. For example, a tree like this, 4, 3, 2, 1, can never be formed by a union with rank strategy. Why is that? Because let's call this rank 4, rank 3, rank 2, rank 1. The only way you could have formed this is at some point you constructed this tree with 2, 3, 4, and this tree has rank 3, and you union this tree with a tree of rank 1. This is the only way you could have formed this tree. And when you did this and you go by the rank strategy, it turns out 1, which has a smaller rank, must be subsumed, and 2 must be the representative. So you can never form a tree like this with the rank strategy. You can only form a tree like this. So with that being said, what's the minimum number of nodes with rank 3? Then you get the answer to be 4. So something like that. Okay, so I want to know something about the minimum number of nodes with a given rank. So this would be 4. So what's the minimum number of nodes for a given rank? So here is the idea. So I can say that a tree of rank r plus 1 can only be formed if you make a union of two trees of rank r. So you must have this inequality, that the minimum number of nodes a tree of rank r plus 1 must have should be at least more than twice the number of nodes that a tree of rank r must have. Okay, so with that being said, you can immediately clear out this fact that n of r must be greater than or equal to 2 to the power r, given that n of 1 is 1. So you can go that n of 2 must be at least 2, n of 3 must be at least 4, and so on. So with that being said, n of r, you can say, is 2 to the power r minus 1, to be precise. 2 to the power r minus 1, to be precise, right? So then what you can show is, suppose I have n nodes, what's the largest rank I can have? So it turns out then you need to have n greater than or equal to 2 to the power r minus 1, and simple math reveals that r must be less than or equal to log 2 n plus 1. So the largest rank I can have of a tree with n nodes is log n. So that's the largest rank I can create, log n plus 1, which is theta log n, as far as we're concerned. So it turns out that using the rank strategy, my trees cannot get too deep. Okay, so my trees cannot get too deep. So suppose I did a bunch of make sets and a bunch of unions, then the worst case, my tree can only have rank log n, theta log n. And suppose I kept doing find operations, worst case find goes from a leaf all the way to the root. Well, that's simply theta log n. So the total cost of n make set and union and m find operations is something like n plus m log n. This is the number of make sets, and this is the number of find operations I do, arbitrary find operations, but each find operation cannot cost more than log n. So this is already a big saving from a very simple strategy of following rank. Okay, now there is one more very cool strategy that comes out, and this strategy is called rank compression. Okay, so I hope the rank strategy was clear. Now, what do we do with rank compression? So what we do is the following. Suppose I have a tree, some tree where I want to find and then what the representative for J is. So I traverse the pointer chain all the way up. So here is J, here is the parent of J, here's the parent. So I traverse this pointer chain all the way up and I find the representative of J, right? Now I can use this work to do something. So since I know that the representative of J is this, I can directly shortcut and I can connect J directly to its representative. So whatever the root is, so since I discovered this path to the root, I can take whoever the parent of J is and I can connect directly J to the representative. And by the way, I can do that for all the intermediate nodes in the middle. So every node I traverse in the middle, I can do that. Let me give you a concrete example of this idea. And this idea is called rank compression. It's going to make the rank of nodes smaller. What's the idea? Suppose I have this tree. Let's make this tree 1, 2, 3. Let's make it 4. Okay, and let's say 2 has a child. Let's say 5. Okay, so let's say this is the idea. And then 5 has a child, let's say 6, something like this. So let's say this is the tree that I have. Okay, something like this. Okay, so this is the tree that I have. Okay, now let us say I wanted to do a find on 6. To do a find on 6, I traverse this pointer, I chase this pointer, and I go from 6 all the way to 5. I go from 5 to 2, 2 to 1, and I know that find of 6 is 1. But in this process, I can take this pointer from 6 and I can directly shortcut it to 1. And by the way, since I visited 5 along the way, I know that I can take the pointer from 5. So it's a little bit of work. I can do this. So the process of doing find, I can arrange the tree, and I can every node from which I directly go to the root, I've discovered it, so I can do this. Next time I do find of 5, for example, I just do single operation find its root. Or if I do find of 6 again, it's going to be easy, right? So, and this idea is called rank compression. Okay. Now, rank compression makes this algorithm very, very powerful, because not only is if I have an expensive find in one step, if I have an expensive find operation in one step, let's call it expensive. Let's say it takes log n time. The very next step, it will just take 1 time. Okay, so it's going to be some amortization. There's going to be some amortization of work, which is going to make it very nice for future. All right. Now it turns out this is a little bit harder to analyze, but we can still do this. Suppose I did n make set operations as before, and then some union operations, let's say n of them. And then I did m find operations. It turns out that the complexity is going to now become, instead of n log m, which used to be the case before, it's actually going to become something much nicer. It's going to become n alpha of m, and we call this alpha the inverse Ackermann function. Okay, and this is a very interesting function in the sense that alpha is a function where as m goes to infinity, alpha does go to infinity. So it does eventually go to infinity, but it's going to do so slowly. For example, alpha 10 to the power 80 is still less than equal to 4. So even for astronomically large numbers, alpha is just a very, very tiny value. For most practical numbers that you can imagine on the planet, alpha is going to be some really small number like 4. Okay, and this is called the inverse Ackermann function. The Ackermann function itself is one of the fastest growing functions. So inverse Ackermann function is a very, very, very slow growing function. This is practically a constant, though technically it is not. It still goes to infinity as m goes to infinity, but it goes slowly that it's practically a constant as far as we wish. Okay, so then doing n make set and m find is going to take time, n alpha of m, and this is amortized complexity, which means it's the averaged complexity of each operation by taking the sum. All right, so I hope this is clear. So what have we done? We talked about disjoint set data structures, and we talked about rank strategy for union, and we talked about rank compression for find. And this is a very interesting data structure. It gets used once in a while for many interesting purposes. So we will see one such thing with Kruskal algorithm. Okay, coming right up. So thank you so much, and I will see you in the next few videos.
Okay, so in this lecture, we are going to introduce the shortest path problem. Okay, so what is the shortest path problem and why is it important? All right, so what's the shortest path problem? So you can guess what it is. You are given a weighted directed graph. Okay, let's put some cycles in there, no problems. So you're given a graph and the graph has weights on the edges. It can even be negative weights. All right, so it has weights on the edges, and suppose I have a source and I have a destination. Okay, so you ask the question, what is least weight path from the source S to the destination T? Okay, so you want to know what's the path of least weight, and what's the weight of a path. So suppose I go directly from S to T. Suppose I go directly from S to T. The weight of this path would be the weight of the edge S to T, which is 1. Now suppose I go from S to A, A to B, B to T. Then the weight of this path is 2 plus 3 plus 1, which is 6. Suppose I go from S to B and B to T. The weight of that path would be 2.5 plus 1, 3.5. All right. So, all right. So what about the negative edge here? So maybe I can go from S to A to B, B to T, T to A to B, B to T. But that makes no sense, because if I take this cycle here, 3 plus 1 minus 3.5, if I take this cycle here, then this cycle is going to have an extra weight of 0.5. So it makes no sense to take cycles. All right. And we will see this formally in a second. All right. So the least weight path from a source to a destination. And this is a very important problem. Every time you log on to Google Maps, you are entering a source address from, you are entering a to address, and you get a route to go from your address, your from address to your to address. So that's an instance of the shortest path problem, right? Now, the interesting thing about that is, what are the weights in your graph, right? What are the weights? The weights can be travel times. The weights can also depend on congestion, how much traffic is there. All right. The weights can also depend on the distance. Even though travel time is correlated in a positive sense with distance, it doesn't necessarily mean that as the distance increases, travel time also increases monotonically. Sometimes the distance can increase and the travel time can decrease, because you are traveling on a faster highway with faster speed limits, with higher speed limits, right? So it depends really. And Google gives you the option. It gives you the option to sort, right? Google gives you the option to choose distance or choose travel time, right? So it's an interesting way, and it's actually more sophisticated, way more sophisticated than the shortest path problems that we are going to study in this class. But what we are going to study in this class forms the foundation for understanding everything else, so it's going to be important. All right, where else are shortest path problems solved? Well, in a lot of other places as well. So shortest path problems are solved by companies like FedEx or UPS, who are doing logistics, like travel websites for planning airline routes. Right? So shortest path problem is not just solved by Google, it's being solved in a lot of places. And there are many problems which do not have anything to do with graphs, which do not have anything to do with shortest paths per se, but knowing shortest paths, you can solve them using shortest path. Like for example, playing Pac-Man, playing games like Pac-Man. If you ever played the Pac-Man game, you have a bunch of evil characters. You have a bunch of evil characters that are trying to eat your good character, okay? And your good character is trying to eat some candy through a maze, and the evil characters are trying to chase after you. Well, the evil characters are basically going to be controlled by some form of a shortest path algorithm. Okay, if you have played, this is a classic computer game. For those of you who were not around in the days of classic arcade games, this is a classic game. Very good. So at least I have given you the impression that shortest path is important. If Google Maps were not important enough, then you know that companies like FedEx, UPS, travel websites, a lot of companies rely on shortest paths. Okay, even networking companies, where during routing I want to know the shortest path from A to B. All right. So shortest paths are important. All right. Let's now talk about shortest path problems, a hierarchy of shortest path problems. In general, we will study two flavors of shortest path problems, single source and all pairs. So what do they mean? So in a single source shortest path problem, you are given a graph. Okay, you're given a directed, weighted, directed graph. All right. If you're given a weighted directed graph, and you're given a single source S, you're given a source vertex, now give me the shortest paths from S to all destinations, S1, S2, S3, S4. So give me from S to all destinations. All right. And the idea here is the output of this algorithm is going to be a table. Okay. So if S itself is the destination, then the cost will be 0. Going from S to S is going to be 0. And the path is going to be simply the empty path. If I want to go from S1, cost is 1, path is going to be S to S1. If I want to go to S2, cost is 2.5, S to S1 to S2. So I want to build up like this. Okay, so I mean, for every possible destination, I want to know what the shortest path cost is, and I also want to retrieve the path for you. All right, so and this is called single source. And so if you want to know the shortest cost path from S to T, then you look it up from the table. Source node S. So build a single source shortest path table from S and look up the cost of S to T. And this allows you to go from S to T. If you change your mind, you can go from S to T2, S to T3. But if you change the source in this table, you will have to recompute a new table for the new source potentially. And this is called single source. The other kind of problems are called all pairs. Here, I want to compute for all pairs of vertices, I want to compute the shortest path distance, and I want to compute the shortest path itself. Okay. Now, obviously, this is going to be more expensive than what? Than single source. Right? It's going to be way more expensive than single source, but we will look at it next week. All right. So this week we are going to look at single source. All right. Very good. Now, one of the important things is, what about single destination? Does that even make sense? So suppose I have a destination T, and for every possible source, I want to know the shortest path from that source to the destination. So for example, suppose T is Rome, knowing that all roads lead to it, it's a natural question to know what's the length of the shortest path to Rome. All right. But interestingly enough, if you know how to solve single source, you can easily solve single destination. How is that? Well, take your graph, just reverse the direction of all the edges, compute the transpose graph or the reverse graph, and simply solve a single source shortest path problem on this transpose graph, and you're done. Right? So single destination is easy if you know how to solve single source. So we will mostly focus on solving single source shortest path problems. All right, so now I'm going to talk more about single source shortest path problems. Okay, so in a single source shortest path problem, I have as an input a weighted directed graph G with vertices V. So number of vertices is N, edges E, number of edges is M. All right, and there is a weight function. So if you have an edge from U to V, there is a weight on this edge. Okay, the weight can be positive, the weight can be negative. Sometimes you can have negative weights. What's the meaning of negative weights? Depends on the problem. Of course, if weights are measuring distances, then negative weights are not going to be meaningful. On the other hand, if weights are measuring the difference between the length of the road and 2 kilometers, let's say. So if the road is less than 2 kilometers, maybe I put in a negative value for some reason, and then let's say that's the way my problem's built. So then negative weights have a meaning there, right? All right, so very good. So and sometimes, for example, let's say a company has built a brand new road, and it's incentivizing you to take that road by giving you $10 every time you take the road, and that offer is valid until October. Okay, just to get people on this new road. All right, well, in that case, there is an incentive given to you to take the road, and therefore you might have negative weight edges in such a graph. If you're a logistics company and you want to represent this incentive, you might do so with a negative weight edge, because, well, every time you take that edge, you're going to gain some money, so that's a negative cost. All right, so these are the inputs to the problem. Now it makes sense to think carefully about the outputs, and I've already told you what the output looks like. Well, the output looks like this. So I need a table. And so for every destination, S, S1, S2, blah, 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 I need a cost, a distance, the shortest path distance to that destination. And previously I told you I need the path itself. What's the shortest path? What are the sequence of edges I need to traverse to get from S to S1? So S to somewhere, to somewhere else, to somewhere else, to somewhere else, to S1. All right. Now I need a sequence of edges to traverse. All right. How do I represent that? Well, I'm going to talk about this right now. So first property of shortest paths is shortest paths form a tree. All right. So let me do that with an example, with a concrete example, and then explain what I mean and prove the property. So first property is shortest paths form a tree-like structure. What does that mean? So let's take an example. So here is a graph. Okay, so here's your graph, and I would like to have a source vertex of 1, and I would like to know the shortest path from the vertex 1 to every other vertex in the graph. All right, so the result is going to be a table. So source is 1, and what are the destinations? The destinations are, okay, so I build a table for various destinations. So destination could be 1, the source itself, 2, 3, 4, 5, and 6. All right. So what's the cost of going from 1 to 1? That's the easiest part, 0. And the path is empty. So I'm going to write epsilon for empty. All right. So that's going to be the simplest thing. What about 1 to 2? Well, this is easy. You can work it out. The shortest path from 1 to 2 cost is 1, and the path is go from 1 to 2 directly. What about from 1 to 3? Well, if you look at it, there's many ways of getting from 1 to 3. So I could go from 1 to 2, 2 to 3. The cost of that is 3. I could go from 1 to 4, 4 to 3. Cost of that is 4.5. 1 to 2, 2 to 4, 4 to 3, and there's multiple ways, but if you see this, the shortest path is going to go from 1 to 2. For destination 3, the shortest path cost is 3, and it's going to go from 1 to 2, 2 to 3. For destination 4, the shortest path is going to go from the cost is going to be what? 1.5. Okay, and it's going to go from 1 to 4. Okay, for destination 5, it's going to go from what's going to be the cost? Okay, the cost is going to be 4. Okay, and it's going to go from 1 to 2, 2 to 3, 3 to 5, and for destination 6, the cost is going to be 3, and it's going to go from 1 to 4, 4 to 6. All right. Okay, so now one thing to notice is that the path is going to be difficult to store. So what can we do instead of storing this path? So one thing to do is we can always record the parent pi. So the parent is going to be the last node before the destination node. So for example, if you're going from, so the parent for 5 is going to be 3, and the parent for 6 is going to be 4. Okay, and this is always the last but one node before you reach the destination node, as I have shown by circling. All right, now if I just store this last but one node, it's enough. And remember, we've already seen this in BFS and DFS. It's the concept of the parent pointer pi, right? And by storing the last but one node, it's easy to see. So if t hat is the last but one node, then if I need to get from s to t hat, right? So if it's the last but one, if I need to get from s to t hat, then if I know how to get from s to t hat, then I know how to get from s to t. Okay, and that's the important part. So this is an important aspect of shortest path. I don't need to store the entire path. I just need to store the last but one node, and I can recursively recover the path. Is that okay? All right, so this is an important part. Okay, and we already saw some of this in breadth first search. All right, now this gives us a property of shortest path. If I know commit to reaching t hat and reaching t through t hat, then if I get the shortest path from s to t, it must contain the shortest path from s to t hat, right? The shortest path from s to t must involve shortest path involves shortest path from S to T hat. All right, and this is important. Okay, and this is a form of something that you have seen before, and this is nothing but a statement of the optimal substructure property stated in the reverse direction. Okay, and that's important to know. So why is this the case? Let's take some other path, yellow path from S to T hat, and let's say if that were shorter than the red path from S to T hat. Well, by concatenating the yellow path and the red edge from T hat to T, I could have gotten to T in a shorter manner. Okay, and so this is just a form of the optimal substructure property. And that's in the reverse manner. So this is the optimal substructure in the reverse direction. There is another way of stating the optimal substructure. Suppose I start from S and I commit to going to a node S hat. Okay, then if I want to get the shortest path from S to T, then this segment must also be the shortest path from S to T hat, and that's important to note. So here this is the optimal substructure in the reverse sense. If I know that the last node before T hat T is T hat, then I need to get to the shortest path from S to T hat. Likewise, if the first edge from S is to S hat, then the segment from S hat to T must be the shortest path. Okay, so this is an instance of optimal substructure. And so, like you guess, shortest path algorithms are going to be a form of dynamic programming on graphs. Okay, and this cost table that you see here is going to be like your memo table. Okay, and you don't need to store the paths, you just need to know how the parents so that you can look up. So the parents are giving us the option for T hat that's giving us the shortest path overall from S to T. All right, so so once we know this, how do we look up the answer? Well, if you know the parent, and suppose you want to look up the path from 5, well, the parent of 5 is 3. So I know that the last edge on the path is 3 to 5. What's the parent of 3? Is 2. So I know that the edge to get to 3 must be to 2. What's the parent of 2? 1. So, but 1 is the source. So to get to 5, I need to go 1 to 2 to 3 to 5. Okay, so this is important. All shortest path algorithms are going to build a cost table and a parent table. All right, and this is going to be important, and hopefully this is clear why we need to build both. Okay, finally we will talk about the effect of cycles. So far we have not really talked about cycles. What do cycles end up doing to the shortest path problem? So here's an example of a graph. Okay, so I'm going to draw a graph. All right, and the edge weights are 2, 3, 1, 4. Okay, so does this cycle matter? Well, the problem with a cycle is it gives you infinitely many paths from 1 to 4. So you can take from 1 to 2, 2 to 3. You can take from 1 to 2, 2 to 5, 5 to 4, 4 to 2, 2 to 3. And this takes a cycle once. Now you can cycle twice. So you have infinitely many possibilities in the graph, right? But the nice thing is, because the weight of the cycle is positive or is greater than or equal to 0, okay, even if it were a 0 weight cycle, this would be true. The cycle doesn't matter. Taking the cycle only makes the paths costlier. Good. Unfortunately, if your graph has negative weights, this is no longer true. So let's take the same example, but let's make negative weights now. Now the weight of the cycle here is -1. So this is a negative weight cycle. So going around this cycle, so the shortest path distance from 1 to 2, 2 to 3 is -infinity. Why is that? Because I can keep going around the cycle and I can make the weights of the path smaller and smaller and smaller. So if a graph has a negative weight cycle, then shortest path distances from any source to any destination is taken to be either you can take it to be undefined or negative infinity. And I will explain why we go for such a drastic interpretation, negative infinity. All right. Now here is the idea. So suppose I have a graph. Okay, let's go back to this original graph, which is already a nice graph. And let me add a new edge from a new node 1 to 5. 1 to 5. And let's give it a weight 2. So you might say, well, hey, 1 to 2 is well defined. It's not well defined because the negative cycle comes into effect. 1 to 3 is not well defined. 1 to 4 is not well defined. 1 to 5 is not well defined. But there is a shortest path from 1 to 5, which is 2, right? That is one interpretation. However, remember that this negative weight cycle has this following interpretation too. So if an edge doesn't exist in the graph, let's say 5 to 1 doesn't exist, you can say it exists with cost infinity. This is one of the interpretations you can give. Okay, it's one interpretation. And this we will use it again and again in certain problems. So you assume that there is a plus infinity weight edge from 5 to 1, from 4 to 3. So under this interpretation, you see, if you have a negative weight cycle, that's going to mess up the distance to 5 because now you are being forced to add minus infinity to plus infinity. And the answers are undefined. In the worst case, so it's not ideal to talk about shortest paths when you have negative weight edges. Okay, and I call it the the foreign taxi problem. This is very common if you have taken taxis in foreign capitals where you're completely unaware of what's going on, right? And the taxi driver can sometimes take you through a really circuitous path for a long time to your destination, charging you up a lot of money. And this has happened to me in a couple of foreign capitals where I did not know the place well enough. All right, I won't name names, but this has happened to me, and I call it the foreign taxi problem. So even though you may not be on the path to your destination, you may still end up being charged a lot of money. And negative weight cycles have that kind of a flavor. Even though this negative weight cycle does not impact 5, you may interpret an infinite weight edge from 5 to 1, a plus infinity weight edge, and now you are being forced to add minus infinity and plus infinity, which either gives you undefined result or gives you a really bad answer. In any case, this is not ideal. So we generally don't answer this question if your graph has a negative weight cycle. Okay, so that is more of what by an introduction to shortest paths. In the next lecture, I'm going to talk about the first algorithm, which is the dynamic programming algorithm. And it's called the Bellman-Ford algorithm. It's a simple algorithm. It's going to set up shortest paths as a dynamic programming problem and solve it. and hopefully it will be an introduction to dynamic programming on graphs for you. All right, see you in the next lecture. Bye. Okay, so in this lecture, we're going to talk about the Bellman-Ford algorithm for shortest paths. All right, so given a graph G with edge weights W, all right, now the idea here is to solve single source shortest paths problems from given source vertex S. So S is the source vertex, V and E are the vertices and edges of the graph. It's a directed graph with weight W. All right, now what is the main idea behind Bellman-Ford algorithm? So in Bellman-Ford algorithm, we are going to keep repeating a particular operation, and this particular operation has a name called the edge relax operation, and it's going to just keep getting repeated blindly a particular number of times in a particular sequence, and magically you get the shortest path. All right, but let me first talk about what the algorithm maintains. So this algorithm is first going to maintain a table. What is this table? We are all familiar with this table. So this is the table where you have destinations, you have your current cost estimate. So it's not going to be the actual cost, it becomes the actual cost at the very end, and the current parent pi. So initially it's nil for everyone. The destination, if the destination is same as the source, the initial estimate is 0. Otherwise, the initial estimate is infinity. So initially, what do? We estimate distance and estimate parent. Well, the initial estimate of the parent pi is it's nil. I do not know. And the distance is infinity. Infinity is going to signify that the node is probably not reachable. So this is my starting table. All right. And the main operation is called the relax operation. So what's the relax operation? So suppose I have an edge from U to V. Okay, and let's say the edge weight is 2. And suppose my current estimate, I have an estimated distance of, let's say, 7. So the estimated distance from the source to U is distance is 7. And let's say the estimate for V is 11. Okay, so these are the current estimates of the distance. Okay, now what relax does is it says, by the way, the cost estimate, let me call it D of V is the cost estimate. So it's this, and pi of V is the parent. It's this. All right. So I'm going to give it names D of V and phi of V. So D of U is, let's say, 7. D of V is, let's say, 11. All right. And the weight of the edge UV, is 2. Now notice that D of U plus W of UV is what? Is 7 plus 2, which is 9, is strictly less than D of V. What does it mean? It means that if I estimate that reaching U is going to cost me 7, and if I have an edge of length 2 from U to V, then I should be able to update this estimate from 11 to 9. Why is that? Well, if I can already reach from S to U of length 7, then I could tack on this edge u to v and reach v by length 9. So this gives me a way to update estimates, right? So if d u plus w uv is less than d of v, then what? D of v, let me update it to d of u plus w of uv. And by the way, let me remember that this is obtained by coming through u. All right. So this operation has a name. It's called relax along the edge uv. Okay, so this is called relax. Let me give you one more example of relax. So let's say u v, let's say the edge length is still 2. Let's say the estimate for u is 11. Let's say the estimate for v is also 11. So which means there is a path somehow that's getting to u with length 11. There is a path that's getting to v with length 11. Obviously, these are not going to be, I cannot get to u from v. So here, if I did relax of uv, I apply the same code. Is d of u plus w uv less than d of v? Well, d of u plus w uv is what? Is 11 plus 2, which is 13. And 13 is not less than, it's not less than 11. And therefore, relax does nothing here. Okay, so relax is very, very important. So what's the key property of relax? What's the key property of relax? Well, the key property of relax if d of u is equal to shortest path from source to u, right? If it's equal to the shortest path from source to u, what relax does, if it successfully changes from u to v, so if this is the shortest path from source to u, then this is going to be length of some valid shortest path from source to v. All right. It's not necessarily the shortest path, but the idea here is if I already have some path of length d of u up to u, and wuv is going to be the edge from u to v, then d of v is the length of a valid path, not necessarily shortest path, from u to v. Okay, so this is very, very important, number one. And number two is if all distance estimates are equal to shortest path estimates. What does that mean? So let us say we found our final shortest path. Let's say we have successfully discovered all shortest paths, which is the desired result at end of algorithm. Okay, what do we know? So if we have successfully discovered all shortest paths, then if you take any edge uv, okay, if this is the weight, if this is d of u, this is d of v, then we know that d of u plus w uv must be greater than or equal to d of v, which means that, what does it mean? The amount of distance it takes to reach u plus the weight of uv must be greater than or equal to the shortest path distance to v. All right. So therefore, there cannot be any further opportunity relax an edge in the graph. All right, so this is super important. So what does it mean to relax an edge successfully? Well, whenever this happens, then we are successfully relaxing through UV. Okay, and when is that happening? That's happening only when d of u plus wuv is less than d of v. Now the interesting thing is, if all distances are finally equal to their final shortest path estimates, that is, we have successfully discovered all shortest paths, then there cannot be any further opportunity to relax an edge in the graph. All right, this is super important. So what we are going to do is we are going to come up with a scheme to check whether the final shortest path distances are correct. All right, so let me give you an illustration of the scheme, okay, and then dive into Bellman-Ford algorithm. So let me start with a graph. So let me illustrate what I mean. All right, so here is a graph G. All right, here is a graph G. I've given you vertices, I've given you edges, and the source is 1, the vertex 1. Okay, this is the source. And I claim that D here represents all the shortest path distances. Is it correct? Is it really going to represent all shortest path distances? Well, how do I check? Well, there's two things to check. Number one, the distance of the source must always be 0. Otherwise, you are trivially wrong. Is that true? Yes, it is true. Check. The second thing I check is no edge can successfully relax. I already explained what it means for an edge to successfully relax. An edge successfully relaxes if I have an edge UV such that d of u plus w of uv must be strictly less than d of v. Then if this is the case, then there is some ways to go. Okay, is there an edge that can successfully relax? So let us take a look at some edges. Let's take a look at edge 1 to 2. Let's take a look at this edge. Can I relax along this edge? So d of 1 is 0 and d of 2 is 1. Okay, can I, so is 0 plus 1 strictly less than 1? No. So 1 to 2 is fine. I cannot relax from 1 to 2. What about from 2 to 3? Well, d of 2 is 1, d of 3 is 1.4. So if I am checking 2 to 3, this looks okay. So let me go ahead and check every single edge, 1 to 4. Well, 4 is 0.5 and 1 is 0, so this looks okay. What about, let me go directly and cut to the chase, what about from 5 to 3? Well, 5 is currently, oops, excuse me, switched all the way to the beginning. All right, so let me go back. Here we are. So 5 is currently at, where is it at? 1, and 3 is currently at 4. So now you see the problem. So if you have 5 at 1, 3 at 4, then this suggests that I can update this to 1.2. So this is a problem. All right. So I can immediately conclude that there is still an opportunity left from 5 to 2. So therefore, these are not the shortest path. On the other hand, if I made a change and I said this is 1.2, then you will find out that everything is back to normal once again. And in fact, you can conclude that these are the final shortest path distances. All right. So this is a very, very important criterion, which says that if you want to check whether the given set of distances are final, just make sure that there is no opportunity left to relax. All right, then the given set of distances are actually final. All right, and of course you check that this distance for the source is 0. Okay, now let me give you the main algorithm, which is Bellman-Ford algorithm. What does Bellman-Ford algorithm do? Okay, so Bellman-Ford algorithm, first of all, starts with a table. What's this table? We already saw this. So for each destination, I have a distance and I have a pi. So initially the distance from the source to source is 0 and the parent is of course undefined. From anything else, the distance estimate is kept to infinity and the parent is also kept to nil. Okay, so this is the first idea. So initialize a table. That's the first step of Bellman-Ford. That's the very first step of Bellman-Ford. The very second step is to do a loop. So I do a loop for I equals 1 to n minus 1. So n is the number of vertices. So I go from 1 to n minus 1. And what is the inner loop? So the inner loop is for each edge E in E. So for every edge in the graph, relax. Well, you should relax as well. Relax E. That's it. And this is the main loop of Bellman-Ford. There's going to be a step 3, which I might as well mention now, which is going to be some work for negative weight cycles, which I am not considering for now, which we will have to consider later. We'll have to do a little bit more work for negative weight cycles, but let me talk about that later. All right, this is Bellman-Ford. That's all it is. Okay, it starts with initializing a table. It starts by then doing this outer loop for n minus 1 steps, going for each edge and relaxing the edge. That's all. It just takes the edges in some order and relaxes along those edges. And finally, we need to do a little bit of work for negative weight cycles. So this is Bellman-Ford. What's the complexity of this algorithm? Very, very simple. So this outer loop runs for n minus 1 steps. This inner loop runs for m steps. And the relax operation is, let's call it theta of 1. It's just a comparison. You're doing this comparison here. Let me go back all the way up to where the relax operation was. Where was it? Right here. So you're doing a compare and a couple of assignments. So this is theta 1. Okay, so that's it. So the Bellman-Ford is basically 3 basic steps. Initialize a table, run this nested for loop, and then do a little bit of work for negative weight cycles. I'll put a question mark, come back to it towards the end. The running time is theta, the number of vertices times the number of edges. Okay, so n times m, theta. All right, let me give you an example and let us talk about some properties and let's talk about this negative weight cycle business. Okay, let's start with this example. Okay, so the example has 4 vertices and I have listed all the edges and I'm going to iterate at every step. At every iteration, I'm going to iterate through the edges in this order. Okay, and I'm going to relax. And how many times do I have to do this? I'll have to do this as many times as the number of vertices in the graph minus 1, which is 3 times. So I need 3 iterations. And each iteration is going to go through all the edges once and do a relax on all the edges. Now let me write down my initial estimates. And I'm going to write it in green. So the estimate for 1 is 0. All others are infinity. I'm not going to track the parents. We can do that on the side and we can work it out later. All right, let me go through my iteration. So in my first iteration, I relax according to edge 1 to 2. When I do that, the weight of 2 becomes 1.5. I relax according to 1 to 3. When I do that, weight of 3 reduces to 0.25. I relax according to 2 to 4. 2 to 4, 2 is at 1.5. So when I do that, weight of 4 becomes 2. Relax according to 3 to 2. 3 to 2. Then the weight of 3 is 0.25. The distance of 3 is 0.25. Weight is 0.5. So 2 becomes 0.75. Then I do 3 to 4. 3 to 4. 3 is at 0.25. Edge weight is 2. So this has no effect. 4 to 3. 2 is at 4. 4 is at 2. And the edge's weight is -1. So it has no effect. All right. So this gives you the first round. So after the first round, the weights are shown in green. And now we do a second round again. In the second round, again I do 1 to 2. When I do 1 to 2, so 1 is at 0, edge weight is 1.5, 2 is at 0.75, no effect. Again I do 1 to 3, and you will see there is no effect. I do 2 to 4, 2 is at 0.75, 4 is at 2, so now there is an effect, and the weight of 4 gets updated to 1.25. Okay, 3 to 2, 3 is at 0.25, and the edge weight is 2, no effect. 3 to 4, no effect. 4 to 3, no effect. All right, then the second round gets done. Then for the third round, again I do 1 to 2, 1 to 3, no effect. 2 to 4, 2 to 4, no effect. 3 to 2, no effect. 3 to 4, no effect. 4 to 3, no effect. So the final distance estimate shown in green, so the distance estimates to various destinations, and we could have tracked the parent as well. 0, nil, 2 is 0.75, and the parent is 3, 3 is 0.25, and the parent is 1, and 4 is 1.25, and the parent is 2. All right, so this is it. This would be the final answer, and you can see that there is no further opportunity to relax, and therefore these have to be the shortest paths. All right, and by the way, the distance of the source is 0. All right, so that is the main idea behind the Bellman-Ford algorithm. So you do n-1 iterations, and in each iteration you relax the edges in some order. Okay, now let me take one more example to prove to you that the order in which I relax the edges matters a lot for Bellman-Ford. Let me take another example. So in this example, I just have a graph which is a single straight line path, and I relax the edges in this order, starting from 5 to 6, 4 to 5, 3 to 4, 2 to 3. My initial distance estimates, I'll show them in blue. Now I do 5 rounds of relaxation because n, the number of vertices, is 6, so I do 5 rounds of Bellman-Ford relaxation. So when I do the first round of relaxation, I start with 5 to 6. 5 is at infinity, 6 is at infinity, no effect. 4 to 5, no effect. 3 to 4, no effect. 2 to 3, no effect. 1 to 2 has an effect, and this effect is to change the distance estimate for 2 to 1. Okay, so that's after round number 1. Now I do round number 2. Again I do 5 to 6, no effect. 4 to 5, no effect. 3 to 4, no effect. 2 to 3 has an effect. It changes the distance estimate to 2, and then 1 to 2, no effect, because 2 is already at distance 1. Then I do a third round. The third round, 5 to 6, no effect. 4 to 5, no effect. 3 to 4 has an effect. And you can see what's happening here. Okay, 2 to 3 no effect, 1 to 2 no effect. Then in the fourth round, I will change the distance estimate to 5, and in the last round I will change the distance estimate to 6, and then you will find that this is done. There is no further opportunity. So n minus 1 iterations are needed in the worst case. I've already given you an example where n minus 1 iterations are needed, and the example is a graph which is just a straight line with n vertices, and the iteration order is going from the edges in the reverse order. So this is the first edge I iterate, second edge, third edge, fourth edge, fifth edge, and so on. All right. So if I iterate the edges in the reverse order in each iteration of Bellman-Ford, you can see that n minus 1 iterations are needed for all the shortest path distances to be finalized. All right. So what are the properties of Bellman-Ford algorithm? So now let us study the properties. So properties. Okay, so the most important property of Bellman-Ford is let d star of v, I'm putting a star here, be the shortest path distance from the source to v. So the first property is that it's going to be a monotone. What does that mean? At any point in the algorithm, d of v must be greater than or equal to d star of v. Okay, so at any point in the algorithm, the distance estimate to every node must be greater than or equal to the shortest path distance. So it can never go below the shortest path distance and come back up. So this is called the monotonicity property. Okay, number 2, if dv is not infinity, if the shortest path distance is not infinity, then there exists a path from S to V. Okay, so there exists a path from S to V whose path weight equals dV. So it's not any number. If at any point I say dV has a finite number which is not infinity, then let's say the number is 10, well then there better be a path from S to V of length 10. It doesn't have to be the shortest path necessarily, but if at any point in the algorithm you give it an estimate of 10, that estimate must correspond to some path in the algorithm. Okay, so that's another property. This is property 1, this is property 2. Property 3, after I iterations of Bellman-Ford, okay, if you take d of v must be less than or equal to the shortest path of length I, shortest path of I edges or fewer. This is going to be the most important thing. After I iterations, the distance estimate d of v must be at most less than or equal to, must be less than or equal to the shortest path of I edges or fewer. Let me prove these properties. So first property is the monotonicity property. The second property is there exists a path from S to V whose weight equals dV. Okay, and the third property. So first of all, let me convince you that if I can prove 2, then that implies 1. Why is that? Well, if at any point d of v is infinity, then it's obviously greater than or equal to d star of v. That's easy to see. Infinity is greater than or equal to anything by assumption. So if d of v is not equal to infinity, well, by property 2, d of v must correspond to some path. Well, but then the shortest path must be of length less than or equal to that length of that path. So d of v at any point must be greater than or equal to the shortest path, because the shortest path after all is the shortest, right? It's the shortest weight path. So if I can prove 2, then 1 is immediately implied. All right. So I will just focus on proving 2 and 3. How do I prove 2 and 3? I prove 2 and 3 by induction on number of iterations starting from I equals 0. So I equals 0 means before the algorithm starts. So base case is I equals 0. What is I equals 0? Well, the distance to S is 0 and the distance to any other node V is infinity if V is not equal to S. All right. Now let me argue that this satisfies both the properties. Well, if d of v is not equal to infinity, there exists a path from S to V whose path weight equals dv. Well, the only node whose weight is not infinity, whose distance estimate is not infinity to begin with, is the node S itself. And therefore, there is a path from S to S whose weight equals 0, which is correct. Okay, so property 2 holds. What about property 3? After 0 iterations, d of v must be less than equal to shortest path of 0 edges or fewer. So what is the only node that has a path of length 0 edges from S? That's S itself. And that path has weight 0. Any other node has no path of length 0. So this works. Okay, so this works trivially for I equals 0. Induction hypothesis. Remember, I'm proving both properties by induction, so I will run through both proofs simultaneously. So let me work for property 2. If property holds at end of iteration I, it holds through iteration I plus 1. Okay, through end of iteration. All right, so let me look at the first property, which is if a distance from a node is not infinity, is d of v is not infinity, then there is some path from S to V whose weight equals d of v. All right, so what is the idea here? So if d of v is not infinity, okay, and let's suppose it's not infinity, then d of v must have been updated by some u. And so first of all, if d of v is not infinity, then according to the algorithm, pi of v cannot be nil. So if a node's distance estimate is not infinity, it better have a parent. Well, then if you must have relaxed along this parent node in the previous iteration. So using the induction hypothesis, in the previous iteration, d of u could not have been infinity. So therefore, there was a path from S to U whose distance was d of u. And when I relaxed along this edge uv, d of v became the weight of the edge uv plus d of u. So this d of v represents the weight of the path from S to U, which exists by induction hypothesis, and this edge from u to v. So property 2, which is that d of v must always reflect the length of a path whose weight equals d of v, is true. Okay, so property 2 is maintained. What about property 3? Well, let us say at the ith iteration, all paths with I edges or less have been taken into account. So if I know that, then if I relax from u to v, okay, then this takes care of all paths of length I plus 1 or less. Okay, so therefore property 3 simply says that d of v must be at least the length of the shortest paths of I edges or fewer. And you see it's true at the beginning, and whenever I relax, if u the d of u is shortest among all paths with less than equal to I edges, and when I relax among d of u, and if this is pi of v is u, then d of v is shortest among all paths with less than equal to I plus 1 edges. Okay, and the more detailed proof is in the book, so I'm just giving you a hand wavy. Even though you can't see my hands wave, you can at least see a sketch of the proof. Okay, so these are the two very key properties, that d of v always represents the length of some path if it's not infinity, and after I iterations, d of v must be less than or equal to shortest path of I edges or fewer. All right, so therefore, if a graph does not have negative weight cycles, I can prove the following. So if a graph does not have negative weight cycles, then the shortest path must have, what's the length of a shortest path? Well, a shortest path can have at most n minus 1 edges. Okay, at most n minus 1 edges. So if a graph does not have negative weight cycles, then any shortest path must have less than equal to n minus 1 edges. Okay, it cannot have more than n minus 1 edges. Why is that? If a path has k edges, then it must involve k plus 1 vertices. In the worst case, a shortest path without negative weight cycles, because if you have negative weight cycles, then you can go around the cycles forever, and this doesn't hold. You can have at most n edges on the path, n vertices on a path. So n vertices on a path. Then how many edges can you have? You can have n minus 1 edges. So the shortest path cannot have more than n minus 1 edges. So by property 2, after n minus 1 iterations, d of v must be less than equal to shortest path involving less than or equal to n minus 1 edges, n minus 1 or fewer edges. But this is nothing but the shortest path, so this is nothing but d star of v. So after n minus 1 iterations, we know d of v is less than equal to d star of v. But property 1 says d of v is always greater than equal to d star of v. So after n minus 1 iterations, assuming no negative weight cycles, the shortest path distance v becomes equal to d star of v. Okay, and therefore no negative weight cycles implies that Bellman-Ford algorithm works. All right, and that was the proof. Okay, this I went through the proof rather quickly, but I hope that you take a little bit of time to understand this proof. It's spelled out in the book. Now we just need to complete one last thing. We need to handle cycles. What about negative weight cycles? So here is the idea. So I initialize Bellman-Ford. Second step is for I equals n1 to n minus 1. For each edge in the graph, relax. Now the third step is I wanted to check if negative weight cycles exist, in which case my answer is I should evaluate my answer, right? I should reevaluate my answer. Well, here's how I do it. Check if any edge can lead to further relaxation. That's it. So walk through the edges one more time and check that if any of the edges can lead to a further relaxation. If it can, then you have a negative weight cycle. If yes, then you have a negative weight cycle. If no, we found all shortest paths and no negative weight cycles. This is super important. Let me illustrate this with an example. Okay, let's take a graph with a negative weight cycle. Let's take a graph with just 4 nodes, and then let's do 1 to 2, 2 to 3. All right, I made a graph with negative weight cycles, and let's iterate through the edges in this order. Okay, and let me write down the initial distance estimates. I'm going to use 1 as the source. Okay, how many iterations to Bellman-Ford? 3 iterations. Okay, so let's do 3 iterations. So first iteration, 1 to 2. 1 to 2 brings down the weight of 2 to 1. 2 to 3. 2 to 3 brings it to 2. 3 to 4 brings the weight of 4 to 0. And 4 to 2 brings the weight of 2 down to negative 1. Okay, so that's one round of Bellman-Ford. I have to do 3 rounds. So let me do the second round. In the second round, 1 to 2 has no effect because 2 is minus 1, 0 plus 1 is 1. 2 to 3 now brings down the weight of 3 to 0. 3 to 4 brings down the weight of 4 to minus 2. And 4 to 2 brings down the weight of 2 to minus 4. Alright, that's the second iteration. Then we do a third iteration. Third iteration, 1 to 2 has no effect. 2 to 3 brings down the weight of 3 to minus 3. The weight of 4 is brought down to minus 5. And the weight of 2 is brought down to minus 6. So that's the end of 3 iterations. And you have the following set of weights. Okay, and now what you do is check for negative weight cycles. See if any edge in the graph can relax the weights further. Can that happen? Well, 1 to 2 cannot. What about 2 to 3? Well, 2 to 3 unfortunately can, because 3 is at minus 3, 2 to 3 will relax it to minus 5. So immediately I conclude that there is a negative weight cycle. And in fact, I can go even further. I can conclude that it involves 2 to 3. And so this is the last step. And how do I do this? Well, to check that, I just do for each edge in the graph, check if the distance of the source of the edge plus the weight of UV is, let's say E is the edge UV, is less than the distance of V. If yes, then you get negative weight cycle. and you have to declare it, and you have to invalidate all your distance estimates, because with negative weight cycles, shortest paths, remember, are either set to minus infinity or taken as undefined. Okay, this has been a really long lecture, but hopefully I have conveyed to you the idea behind Bellman-Ford algorithm. I have conveyed to you the reason very briefly about why Bellman-Ford algorithm works. Why is it actually giving you the shortest path estimates in the absence of negative weight cycles? And how do you check if a graph has negative weight cycles? Well, finish Bellman-Ford and see if you can further relax. Hopefully this is all good, and we can talk about further improvements to Bellman-Ford later on. The book has many further improvements, but this is the basic Bellman-Ford algorithm. Okay. In the next lecture, we will talk about a more efficient algorithm which only works if the graph has non-negative weights. All right, and that's called the Dijkstra's algorithm. We'll talk about that next time. See you then. Bye. All right. In this lecture, we are going to look at some special cases, including the shortest path algorithm for directed acyclic graphs, also known as DAGs. Okay, so there's going to be a special way to run Bellman-Ford on DAGs, and I will also remind you how to handle shortest path when all edge weights are 1 or equal, generally equal to 1. So every edge has the same length, which is 1. How do you do shortest path in that case? Let me recall, and the answer to that you should remember is to do a breadth first search. Okay, but let's take care of that later. So first, let me talk about directed acyclic graphs. All right, so what's a directed acyclic graph? It's a graph that does not have a cycle. All right, so here is an example of a 5-node graph. Okay, that's a DAG, that's a directed acyclic graph. And let's add some edge weights. All right, so in this directed acyclic graph, there's nothing special. You could run Bellman-Ford. Okay, and how many iterations does it take? It has 1, 2, 3, 4, 5, 6, 7 edges. So 7 edges, 5 vertices. So it's going to be roughly 7 times 4, 28 relax operations, and there is no need to check negative weight cycles, which is the last step in Bellman-Ford, if you remember. So there is no need in this graph to check negative weight cycles. So, but this is theta v times the size of the number of vertices times the number of edges. But I contend that this is actually much more expensive. In fact, for a directed acyclic graph, you can run Bellman-Ford in the following manner. So suppose you have, let's say, a source vertex, destination vertex. So initially you start from the source being 0 and everything else being infinity. All right. Now there is a special way to do Bellman-Ford. What is the special way to do Bellman-Ford? Well, the idea is you just need to do one round of Bellman-Ford, just one iteration, and the entire algorithm will run in time theta v plus e. That's it. How do we do that? Well, the idea here is you do Bellman-Ford in a clever manner. So the first step you do is you topologically sort this graph. So if you want to sort it topologically, you can sort it in either order, ascending order or descending order. So let me sort it in the ascending order. So here it will be if
there is an edge from A to B, then A comes before in the topological sort and B comes after. So in this graph, the topological sort is going to be 1, 2, 3, 4, 5 in that order, because every edge goes from a lower ranked edge in the topological sort to a higher ranked edge in the topological sort. Hopefully that's clear. Okay, so once we do topological sort, here's what you can do. Take the first vertex in the topological sort and relax all the outgoing edges according to that vertex. So I will take 1 and relax everything according to 1. But 1 is already at infinity, so if I relax everything according to 1, it doesn't change. Alright, then I take the edge 2 and I relax everything according to 2. So if 2 has weight 0, so I look at all the outgoing edges of 2, which are 2, 3 and 2, 4, and I relax. So 2, 3 has weight 1. So you can update. Okay, so you can update the weight for edge 3 to be 1, and you can update the weight for edge 4 to be 2. Alright, and now consider the next vertex in topological sort, which would be 3. And again, update all the outgoing edges. Outgoing edge is just 3 to 4, so I just relax according to 3 to 4. Next is 4, whose only outgoing edge is 4 to 5. I relax according to 4 to 5, and as a result, I update the weight to 2. Alright, so there is a very, very simple algorithm and it works. Okay, so the idea is, number 1, topologically sort all the vertices in the graph so that each edge goes from lower ranked to higher ranked vertex in the sort. So sort it so that in your list of vertices, every edge goes from a lower rank to a higher ranked vertex. Okay, so once you're sorted, iterate through each vertex in topological order. So go through the vertices in topological order for each outgoing edge of V sub I, relax according to that edge E. That's it, done. And total time taken is dominated by the time taken for a topological sort, which is a DFS. So this takes a DFS, a depth first search, and this is also V plus E. You're going through every vertex in the outer loop, and through the inner loop you're going through every edge once. So it's theta V plus E, number of vertices plus the number of edges. This is a huge savings over standard Bellman-Ford. Okay, and this comes about because I can come up with a clever ordering of edges. I can come up with a clever ordering of edges so that I always relax from a lower rank to a higher rank, and therefore the shortest path information for whenever I am relaxing from a lower ranked edge to an higher ranked edge, shortest path for the lower ranked vertex is already found. Shortest path distance is final, so therefore this works very well. Okay, so this is how you would do it for a directed acyclic graph. Okay, last but not, let me remind you of something that we've already learned. If you want to find a shortest path where every edge has weight 1, or generally every edge has equal weight, let's say, okay, equal positive weight, okay, equal positive weight edges, then how do we do it? Remember that breadth first search does the trick.
Okay, and that's an important observation. You can do it with breadth first search. Why is that? Because remember, breadth first search accesses the vertices in terms of their depth from the starting node. So if the starting node is S, all nodes at distance 1 are first enumerated, then all nodes at distance 2, then distance 3 and distance 4. Okay, so when you do this, breadth first search has this nice property that it is going to find the shortest path where the size of a path is measured in terms of number of edges. Okay, so this is yet another special case where you should not be doing Bellman-Ford, because breadth first search runs in theta v plus e rather than theta v times e. Again, huge savings. All right, so next we are look at a very special case, okay, which occurs very commonly, which is when all edge weights are greater than or equal to 0, or another way, no negative weight edges. The graph has no negative weight edges, okay, and this is really common if edges are representing quantities like time, distance and so on, which are naturally always greater than or equal to 0. Okay, so if there is a reason in your problem, like in Google Maps, the edge weight is greater than or equal to 0. If there is a good reason that the edge weights have to be greater than or equal to 0, then there is a special and very well-known algorithm for doing this problem, and that's called the Dijkstra algorithm, invented by the famous scientist Edsger Dijkstra, okay, who came up with so many new concepts and new innovations, and one of them he's well known for is called Dijkstra's algorithm. All right, and this we are going to study in the next lecture. Very, very important algorithm, and we are going to study in the next lecture. The bottom line is Dijkstra's algorithm is going to be a greedy algorithm for solving the problem. All right. Okay, and it's only applicable if all edge weights are greater than. We will see this algorithm in the next lecture. See you then. Bye. Okay, in this lecture, we are going to study Dijkstra algorithm. Okay, as I mentioned earlier, Dijkstra's algorithm is a shortest path algorithm for graphs all of whose edge weights are non-negative. You can have cycles, but all the edge weights of the graph are going to be non-negative. So negative edges are not allowed in the graph. So no negative edges. Okay, and this is very, very natural in some situations. What are these situations? Well, the situation is going to be, well, it's going to be natural when edges are physical quantities like distances, time, Q size, QUE, UE, Q size, and so on, which can only take non-negative values. Okay, and given that, it's going to be important. And finally, the algorithm is a greedy algorithm, and it's going to share a lot of commonalities with Prim's algorithm. All right. Okay, so let us understand how Dijkstra's algorithm works. Okay, so basically, here is what Dijkstra's algorithm does. Think of it as exactly, there is many ways of thinking of it. One way of thinking of it is think of it as an algorithm that's very much like Bellman-Ford. Okay, but
what we are doing is every edge is relaxed exactly once. Okay, so whereas in Bellman-Ford what we would do is we would come up with an order of edges E1, EM, and then relax n minus 1 times, where n is the number of vertices. Okay, so this is original Bellman-Ford. Okay, whereas this is original Bellman-Ford. In Dijkstra, I'm going to choose or compute a clever ordering of edges. Okay, so I'm going to compute a clever ordering of edges somehow. And just relax edges according to order, and if I do so, I just need to do one relaxation for every edge, and that's it. Alright, now how do we do this? So here is the idea. So just like Bellman-Ford, Dijkstra is going to maintain for every node, it's going to maintain what? So it's going to maintain for every destination the current distance estimate and a parent. And it's going to start with the source, initialize it to 0, parent of course for the source is not defined. Everyone else is going to start with infinity and undefined parent. Okay, so here is the idea. At every step, choose a previously unvisited node. Okay, choose a previously unvisited node, number 1, whose D value is smallest. Okay, so at every step, choose a previously unvisited node. So originally everything is unvisited. Okay, and idea is choose a previously unvisited node whose D value is the smallest. Do that at every step. Okay, number 1 and number 2. Okay, and number 2, relax. So let us call this a node V. Okay, relax all outgoing edges of V, mark V as visited, and do this until all nodes are visited. That's it. Okay, so what is the algorithm? Algorithm is until all nodes are visited, do this. Okay, what is this? Well, choose a previously unvisited node whose D value is the smallest. Okay, so this is it. Relax all outgoing edges of V, mark V as visited. Okay, so these are the 3 steps of the algorithm. So let us do this on an example. Okay, keeping this algorithm here, let's do this on an example. Okay, so here's an example with 7 vertices, and a bunch of edges that I've shown with edge weights. Okay, and just like Bellman-Ford, I'm going to initialize a table of for every vertex. I'm going to record the D value, the parent pi. So far it's going to be 0 for the source, infinity for everyone else, the parent's going to be nil, and I'm going to track whether the node has been visited or not, false or true. Okay, so first nothing has been visited, and let's keep 1 as the source as usual. Alright, with that said, how does the algorithm start? Here it is. Until all the nodes are visited, at every step, choose a previously unvisited node, so visited must be false. with D value being the smallest. Which node is that? So in the very first step, I'm going to choose the node 1, whose D value is 0, which is the smallest. So I'm going to choose the node 1. Relax all outgoing edges of V. So relax all outgoing edges of 1. When I do that, I relax 1 to 2, I relax 2 to 3. Okay, I relax 1 to 2, I relax 1 to 4. Okay, now what happens after I relax? Well, the value of the node 2 is going to become, and the value of the node 4 and their parents are going to get updated. What are the values? The value of the node 2 is going to become, the distance estimate is going to become 1, the value of the parent is going to be 1, the distance estimate for 4 is 2, the value of its parent is 1. Okay, and mark the vertex V as visited. So mark the vertex V as visited. Alright, so then that's done. What's the next step? Well, again, let's keep doing until all nodes are visited. Are all nodes visited? Not yet. So the next step, choose a previously unvisited node V whose D value is the smallest. Which is the node with the smallest D value so far? Well, the answer is the node 2. It has the smallest D value among all the nodes which are as yet unvisited. All right. Now, choosing 2, relax all its outgoing edges. So relax 2 to 3, 2 to 5. So what do we get when we relax 2 to 3? Well, the weight of vertex 3 is going to become, okay, so weight of vertex 3 is going to become 1, its parent is going to become 2. 2 to 5, the weight of vertex, weight of vertex 3 is going to become 2 and its parent is 2. Weight of vertex 5 is going to become 1.5. And its parent is going to become 2. All right, good so far. All right, so now that this is done, I'm going to say 2 is true. All right, what's the next one? Well, the next one is going to be choose the smallest that has not yet been visited, and that is vertex 5, which has a weight of 1.5. All right, so we choose vertex 5 and we relax the outgoing edge for vertex 5, which is going to be 5 to 4. So when I relax 5 to 4, the weight for 4 gets updated. Okay, so the weight for 4 gets updated. And what's the weight for 4? Gets updated to 1.7 and its parent gets updated to 5. Okay, that's good. All right, so the weight for 4 gets updated, its parent gets updated. All right, good. And then 5 is now visited. True. All right, so good so far. Okay, what's the next one? Well, the next one is 4, whose weight is 1.7. Well, so the outgoing edges for 4 get relaxed, which are going to be 4 to 3 and 4 to 6. So when I do 4 to 3, its value gets, 3's value gets to 1.7 plus 1, so 2.7, but it's already 2, so I'm not going to touch it. How about 6's value? 6's value is going to become 1.8. And its parent is going to become 4. Okay, now 4 is done. All right, what's the next one? That's going to be 6, which is the smallest so far, okay, among all the unvisited nodes. So now I'm going to relax 6 to 2. Okay, so when I relax 6 to 2, 2 is already been visited, so there is not much I do. I'm not going to bother. All right, what's next? Next is going to be look at all the nodes that are not so far visited. Okay, and that just leaves us 3 and 7. So 3 is going to be the next one that's chosen, and I'm going to relax its outgoing edge.
So I'm going to relax according to 3 to 6. 3 to 6 is going to try and update the weight for 6 to 2.5, but 6 has already been taken care of with 1.8, so nothing more needs to be done. Last but not least, I'm going to take 7 and relax all its outgoing edge, but when I try to relax the edge 7 to 4, there is no effect, so this is also done. And then all nodes are visited. And therefore done. Okay. In doing so, notice that I visit every node once. I visit every edge exactly once and relax along it. Okay, so this is going to be quite efficient compared to Bellman-Ford, right? So every node is being visited once and plus every edge is being visited once, right? When I visit a node, I relax according to all its outgoing edges. But there is a key step. What do I need to do? At every step, I need to find a previously unvisited node V whose D value is the smallest. So I need to go through all the nodes and choose the one whose D value is the smallest. How do I do that? Is there a data structure that we have learned so far? A data structure that is efficient for maintaining minimum key. Have we learned such a data structure? Can you think of it? Yes, we have. And the idea here is we can use a heap data structure. Right? If we use a heap data structure, according to the key, which is the D value of the node, then at every step, what you can do is among all the unvisited nodes, you can always find the smallest key value. Okay, so that is basically it. So we can now write the pseudocode algorithm. Pseudocode. Here is the idea. Okay, so what's the idea? Let V be the set of vertices and E be the set of edges. Let's have n vertices and m edges. Okay. First step is initialize. For all vertices V, how do we initialize? If V is equal to the source vertex, then V dot D equals 0, V dot pi equals nil. Else, if it's not the source vertex, then V dot D is infinity, V dot pi is still nil. Okay, so that's the initialize. So this is the same as Bellman-Ford. All right, hopefully that's clear. Then the next step is to construct a heap. What does it mean to construct a heap? Well, let's make an array of all the vertices, okay, and heapify it using V dot D as key for vertex V. So V dot D is the key or the priority that I'm going to use. Okay, next step. All right, now comes the main loop. While Q is not empty, okay, what do? Let me take a vertex U, which is going to be the minimum vertex in the Q. Let me extract the minimum vertex. Okay, and then what? Once I extract the minimum vertex in the Q, let me iterate through all its outgoing edges. And how do I do that? I have an adjacency list, so I can
take all the outgoing edges, v1 through vk. For all outgoing edges uv, what? Do the relax operation, but with a small caveat that I'm going to note for you. If u dot d plus the weight of uv is strictly less than v dot d, then what? V dot d must be equal to this quantity. Furthermore, v dot pi must be equal to u. Furthermore, remember that v dot d just decreased, so bubble up in the queue, bubble up v, because its key decreased, so you have to do this bubble up. And that's it. That is Dijkstra's algorithm in a nutshell. Okay, so this is the pseudocode for Dijkstra's algorithm. Alright, what's the running time? Well, the initialization step runs as much time as the number of vertices. Heapify for n vertex is theta n. Outer loop runs n times. It goes through once for each vertex. What's the complexity of extract min? Well, theta of 1 to find the minimum element and theta of log n to do a delete. Okay. How many times does the inner loop run? Well, it's running as many times as the number of outgoing edges, but then for every vertex it's running as many times as the number of outgoing edges for that vertex. So sum of the number of outgoing for all vertex v, okay, sum of the number of outgoing edges for all vertex v is simply the number of edges in the graph m. So jointly, the outer loop and the inner loop jointly, if you take each time the outer loop runs and for that each time the inner loop runs, the total number of times this code gets executed is m times. And that's not surprising, as we noticed before, every edge is relaxed exactly once. But there is a hidden complexity here, and this is theta log n. So now if you add everything up, the total running time is theta n plus theta n log n coming from this step, which is running n times, plus theta m log n for this step. Okay, that is theta m plus n log n. Much faster than Bellman-Ford because all the edge weights are positive. So now we are left with the question, why does Dijkstra work? Why does the algorithm for Dijkstra work? And I will treat that question in the very next lecture. See you then. Bye. Alright, so in this video, we're going to look at why does Dijkstra's algorithm actually work. So we are going to give a sketch of a proof that the algorithm works. And what does work mean? Work means that when it finishes, it finds the shortest path from the given source to all the destinations in the graph. Okay, so to recap Dijkstra's algorithm, we have the initialization phase where the source's d value is set to 0. And remember, the value of v dot d is distance estimate, okay, from S, the source, okay, and pi is the parent, all right. So while there are unprocessed nodes remaining, what do? We choose the unprocessed node with the least value of u dot d, okay, with the least value. And then for all outgoing edges, of u, what do? We relax the outgoing edge and u is processed. We keep moving. Alright, so there are two things about Dijkstra's algorithm. So Dijkstra's algorithm, think of Dijkstra's algorithm as building up a set P of vertices that have been processed. Okay,
for which you have taken the vertex out of the priority queue and processed all its outgoing edges. All right. So if P is that, okay, then the graph at any point can be divided into P and V minus P. All right. This is everything that's been processed and everything that has not been processed. All right. Initially, P is the empty set. When algorithm terminates, okay, when algorithm terminates, P equals the vertex set V, all vertices in the graph. Okay, so this is the termination condition. All right, so there is going to be a bunch of vertices in P, okay, and there's going to be some vertices in V minus P. Okay, so the main claim is for every vertex in P that's been processed, V dot D equals shortest path distance from S to V. This is the main thing. So what does it mean? For everything in the set P, we have already found shortest path. All right. Everything in V minus P is we are yet to find shortest path. Okay. So this is the main theorem. For every vertex V in P, the shortest path V dot D is the shortest path distance from S to V. All right. And in fact, this proves correctness because when the algorithm terminates, P becomes equal to the vertex set. So therefore, when algorithm terminates, since P equals V, this ensures correctness. Because for every vertex, the shortest path distance is recorded in V dot D when the algorithm terminates. All right, let's prove this. Okay, so let's prove this. For every vertex V in P, V dot D is the shortest path distance from S to V. All right, so proof is by induction. Induction on what? Induction on the number of times the while loop runs. Okay, starting with the very first time. Okay, so the very first time we have U, the vertex that's chosen must be equal to S, the source vertex. Okay, and because U equals S, we know that U dot D equals S dot D equals 0. And this is in fact equals shortest path distance from S to itself. Okay, so that's important, number one. All right, now let's do the actual induction. Okay, so do the actual induction. Consider at any point of this algorithm, we have the set of nodes already processed. We have the set of nodes already processed. And let's assume that their shortest path distances. So for each of them, let's call them W, W dot D, indeed equals the shortest path distance. So by induction hypothesis, W dot D equals shortest path distance from S to W for all W in P. Now, what is the idea in Dijkstra's algorithm? In Dijkstra's algorithm, I am going to choose a node. Okay, I am going to choose a node V. Okay, I am going to choose a node V such that V dot D is the least, or we call it U, so let's keep calling it U. So I'm going to choose a node U such that U dot D is the least in V minus P. In the rest of the unprocessed thing, U dot D is the least. Okay, number one. What do I know about U? The one thing I know about U is, so far, the only edges that have been relaxed are the edges that are leaving
any process node. So the only time you relax an edge is when you are bringing the source node into the process node. You are relaxing all the outgoing edges. So number one fact that we know is u dot pi must always be in the process set. So the parent must always be in the process set. All right, that is number one. And number two is u dot d is going to be greater than or equal to in each case. So u dot d is going to be greater than or equal to the shortest path distance from S to u. This is always the case. U dot d is always going to be greater than or equal to. Our job is to prove that it's the other way around, that it's always going to be less than or equal to the shortest path distance. All right. But let's assume that we are wrong. We are wrong that the actual shortest path to u is not going to be the current through the current u dot pi. The actual shortest path is going to be through a different route. Okay. And whatever this route is, it has to start from inside the set P and it has to leave the set P at some point. Okay. Let us call the first time it leaves the set P as the vertex that you encounter. Let's give it a name. Let's call it W. All right. So let me gather some facts about W. Number one is I will claim that W dot D. So if this is, let's say W was involved in the shortest path. So the shortest path itself went through W and then went to U. All right. First of all, I know that W dot D must be greater than or equal to U dot D. And why is this? Because W dot D is going to be greater than or equal to U dot D because U is chosen to be the least value of D in V minus P. So if that is indeed the case, then W of D cannot be smaller than U dot D. It must be greater than or equal to U dot D. That is the first fact. The second fact, which is kind of strange, is W dot D is also the shortest path distance from S to W. Why is this? Well, the reason is I assumed in my theorem that in my contradiction that, well, the shortest path to U goes from S to W and from W to U. Okay. In that case, what happens is W dot D, the edge, the parent of W dot D has already been relaxed. So which means that for whatever W dot pi is, this is in P. And by induction hypothesis, it already has its final shortest path value. Okay, so whatever the parent of W is, W dot pi is already good. And I've already relaxed the edge from the parent to W. So which means that W's shortest path is already fixed, except we don't know it yet. All right. And the second point is, okay, the segment going from W to U, this segment of the path must have shortest path value greater than or equal to 0. Why is that? Because all edges are non-negative. Okay, so if I add the distance from S to W, which is equal to W dot D, plus distance from W to U, okay, so which is greater than or equal to 0. So therefore what? Therefore, you have, along this path, you have the shortest path value is W dot D plus a positive value. The positive value comes from this remaining segment from W to U. So all in all, U dot D must be less than or equal to W dot D plus the distance from W to U. So therefore, the current path through the parent of U has a shorter length than the presumed shortest path through W. All right. And this is a contradiction. This is a clear contradiction. Therefore, U dot D is indeed the shortest path distance from S to, and this completes the induction and the proof of Dijkstra. And the proof relies non-trivially on the fact that all edge weights are greater than or equal to 0. Otherwise, it's possible, if the edge weights were negative, even though w dot d is greater, it's possible that this path from w to u might cause a reduction in the value, and thus this doesn't really work for arbitrary graphs with negative weight edges. It only works for graphs with positive weight edges. Okay, so that completes the analysis of Dijkstra's algorithm. All right, hopefully reading through the proof, it makes more sense right now. Okay, very good. I will talk, in the very next video, we'll talk about the all pair shortest path algorithm. All right, which is going to be, instead of single source, we are going to look at shortest paths from every node to every other node in the graph. All right, see you then. Bye. Okay, so now in this lecture, we are going to look at the all pairs shortest path problem. So what is the all pairs shortest path problem? So far, we've looked at a graph with a given source vertex. So for example, here is a graph. Okay, let's put some edge weights on it. Okay, and we gave you a source vertex. We said, okay, let 1 be the source vertex. So we found single source shortest paths. And we studied algorithms for this, Bellman-Ford and Dijkstra's. Okay, so we studied 2 algorithms for this. Bellman-Ford can handle negative weight cycles, negative weights in general. Even can detect negative weight cycles. Dijkstra only non-negative weights, positive or 0 weights. Good. All right. So now let's look at the other kinds of algorithms, which are all pairs shortest path. In all pairs shortest path, the idea here is I don't give you a single source. I want to know what is the shortest path from 1 to 3. What's the shortest path from 3 to 2? What's the shortest path from 2 to 5? So if I'm given n nodes, there are n squared possible pairs of source and destination. And I want to know the shortest path distances as well as be able to retrieve the shortest path for any given source and destination. So I might ask you for 1 and 5, or I might ask you for 4 and 3. Okay, so this is called the all pairs shortest path. Now the question is, how do I represent the distances in the first place? And very simple, for all pair shortest path problem, we represent the distance as a matrix. So we write down 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we write down the shortest path distance from 1 to 1, from 1 to 2, from 1 to 3. What's the shortest path distance from 1 to 3? I believe that should be 2. From 1 to 4, from 1 to 4 the shortest path distance is 1. What about from 1 to 5? From 1 to 5 the shortest path distance is 1. Alright, and similarly for from 2 to 1 the shortest path distance is, I believe, 0. 2 to 2 the shortest path distance is 0. 2 to 3 shortest path distance is 0. 2 to 4, so on and so forth. So you fill out a matrix of shortest paths, distances. All right, and in fact, not only do you fill out a matrix of shortest path distances, so let's call this matrix the D matrix, the distance matrix. You also come up with a different matrix called the next matrix, or let's call it the N matrix, which is going to tell you for any I to any j, so for any I to any j, I'll put in the ID of the node that comes next in the shortest path. So this is the next matrix, the node that comes next in the shortest path from I to j, let's call it I hat, so I will say I hat. So this is the identity of node that comes next. And if I had both the D matrix and the next matrix, I can retrieve the shortest path. If I needed to retrieve the shortest path from A to B, I will first look at the A bth entry, and let's call that A1. Then I will look at the A1 bth entry, and then I'll get A2. So then I can reconstruct the shortest path by repeatedly looking at what's next until I get to B, and then I stop. All right, so that I hope it's clear how having a D matrix and the next matrix gives me the distance from any given source to any given destination, and the next matrix encodes the node that comes next along a path. All right, now we need to think about how do we compute the D and the next matrices. What's an efficient way to compute it? All right, and there are many algorithms to do so, and the simplest scheme we can do, for example, is we can, if the graph has all non-negative weight edges, what do? We can run Dijkstra from every source node. So walk through every node as the source node of the graph and run Dijkstra, and thus you can record the D and next from the information that Dijkstra provides you. Okay. Now this is not bad, and what the running time would be is the size of the number of vertices of the graph times V plus E log V. Okay, so this is going to be if the graph is dense, which means that the number of edges is theta n squared, then this is roughly going to give me n cube log n if the graph is dense. If the graph is sparse, which means the number of edges is theta n, then this gives me something like n squared log n. Okay, so this is not bad, but it can only be done if the graph has all non-negative weight edges. All right. Now what happens if that's not true? Well, then you can run Bellman-Ford, which takes V times E for each run, and you have to do it for every vertex in the graph, so you get theta V times E. So if graph is dense, in a dense graph, the number of edges is roughly the square of the number of nodes. So then you get very bad complexity, n to the 4. Okay, if the number of edges is sparse, and so if it's a sparse graph, this is called a sparse graph. If the number of edges is a proportional constant on the number of vertices, this takes theta n cube. All right, so these are the runtime complexities if you are using known solutions that you should know. Okay, now I'll present you a new algorithm, and this is the Floyd-Warshall algorithm. And this new algorithm, it's a dynamic programming algorithm. Okay, so it's going to be a dynamic programming algorithm, and what it is going to do is it's going to do some kind of an iteration, a dynamic programming iteration. Okay. Okay, so the basic idea in Floyd-Warshall algorithm is I'm going to compute the distance matrices incrementally. So I'm going to compute a series of matrices D sub 0, D sub 1, D sub j, D sub j plus 1, all the way to D sub n, and where D sub n is going to be the final distance matrix. All right. Now, how do I manage this? All right. So let me start by explaining what does D sub k, the matrix D sub k, mean. Well, D sub k is going to be a matrix. It's going to be like an approximation of the final distance matrix. So it's going to approximate the final distance matrix. But in what way? Well, the ijth entry of this matrix and let me call that d sub k of I comma j equals the shortest path from node I to node j, such that with the extra constraint that all intermediate nodes do not include the source and the destination. They are not intermediate, but everything else that comes in between is intermediate. All intermediate nodes must have ID less than equal to k. And by the way, I should mention that the vertices are now numbered from 1 to n. Okay, so each vertex has a number from 1 to n. And so the number, the ID of the intermediate vertices in d sub kij is less than equal to k. So d sub kij is the shortest such path which only involves vertices from 1 to k in the middle. Alright, the middle vertices are only from 1 to k. And this is important because now when you look at it, d sub n is going to be all possible paths. Because now when I allow the intermediates to be less than equal to n, I have lifted all constraints. So d sub n lifts all constraints. What about d sub 0? So d sub 0 means that the intermediate vertices, if any, have to be less than equal to 0. But there is nothing less than equal to 0. The vertices are from 1 to n. So therefore, d sub 0 of ij is going to be very simple. It's going to be either what? It's going to be the direct edge weight from ij, if there exists an edge from ij, or let me call it infinity. Alright, so this is it. So either d sub 0 of ij is w of ij if ij is in E. It's going to be infinity if I and j are different. And by the way, I might as well set it to 0 if I equals j. Okay, and this is kind of trivial. If I equals j, I might as well just set it to 0. Alright, so this is d sub 0. So I know how to do d sub 0. I'm convinced that d sub n will be equal to d because in d sub n all the intermediate restrictions naturally get removed. So now comes the clever part of this algorithm. If I know d sub k minus 1, how do I calculate d sub k? Now think of two vertices I and j. Now I know the shortest path from I to j, the shortest path distance involving vertices of id less than equal to k minus 1 in the middle. If I need to find out the shortest path involving vertices less than equal to k, there are two types of shortest paths. Shortest paths that already involve less than equal to k minus 1. So that's one type of shortest path. Another type of shortest path or shortest path that involve the vertex k. But if it involves the vertex k can appear just once in the path. So there is only one occurrence of vertex k, and the remaining must be the shortest path from I to k, but this can only involve nodes of less than equal to k minus 1. Likewise, these vertices can only involve nodes less than equal to k minus 1. So this is d sub k minus 1 of kj. And whichever one is the winner between these two options, option A, option B, is going to take over the shortest path, allowing d sub k. So the equation is d sub k of ij equals the minimum between what? D sub k minus 1 of ij and d sub k minus 1 of ik plus d sub k minus 1 of kj. Alright, and that's going to be it. So that gives me the algorithm. So what's this algorithm? This algorithm goes like this. For k equals 1 to n, initialize d sub 0. What is d sub 0? Take the adjacency matrix, which already has the weight for ij. If an edge doesn't exist, make the weight infinity, and take all the diagonal elements and put a 0. So D sub 0 is initialized to the adjacency matrix with edge weights. Caveats are infinity if I not equal to j and ij edge doesn't exist. Okay, there is no edge from I to j. Okay, and 0 if I equals j. So make up this matrix, let's call it D sub 0 and initialize it. Alright. Now the rest of this algorithm is basically going to be 3 nested for loops. And what are these for loops? These for loops are going to be as follows. Alright. For I equals 1 to n. For, the outer loop, let me put k in the outer loop. So for k equals 1 to n. For I equals 1 to n. For j equals 1 to n, okay, d sub k of ij equals minimum of d sub k minus 1 of ij, comma, d sub k minus 1 of ik plus d sub k minus 1 kj. And that's it. Okay, and then return d sub n of ij. Okay, so this is taking care of the distance matrix, and this is simply computing this formula, this update formula here, and you see why it works. So you have the reasoning of why it works. Now the only thing is, how do I retrieve the shortest path? How do I retrieve the shortest path? Well, here is the idea. Now what you can do to retrieve the shortest path is, I told you there is a next matrix, right? So let me, along with each of these d sub i's, let me make up a matrix called next sub I, right? So what is the idea? So next sub 0 of ij is going to be what? It's going to be j if ij has an edge in the graph. Okay, so if there is a direct edge from I to j, if I start from I and I take this direct edge, the next guy is just j. That's easy. Otherwise, just make it undefined. Okay. Oh, by the way, if I equals j, make it I. Otherwise, make it undefined for now. Okay, because there is no path, let's make it undefined. All right. So now that I have next sub 0, if I know next sub k minus 1, how do I compute next of k? Well, I know how to compute from dk minus 1. I know how to compute dk, and next k minus 1 just goes with dk, right? So here's the idea. If I have from I to j the shortest path less than equal to k minus 1, well, next k minus 1 gives me the identity of what's next after I, right? And if I consider option A, if I consider option B, like I mentioned before, then I go from I to k and I go from k to j, and this has to be less than equal to k minus 1, and this has to be less than equal to k minus 1, and the next here is given by next of k minus 1 ik, right? So if I need to find out next of k of ij, right, then let me look at d of k ij. Well, it's the minimum between two options, option A and option B. Option A is d of k minus 1 of ij, and option B was what? Option B was d of k minus 1 ik plus d of k minus 1 kj. Okay, so this is A, this is B. Let me find out which of the options is winning. So if option A wins, then set next of k ij to next of k minus 1 ij. Nothing changes. If option A is smaller, if B is smaller, then simply set it to next of k minus 1, like the first node that's encountered along this path, ik, if B is smaller. That's it. So this update goes hand in hand with update to the D matrix. That's it. Okay, very good, very good. All right, so this is Floyd-Warshall algorithm. What's the running time? Well, the running time is very simple. You have 3 nested for loops, each running n, so it's theta n cube. That's the running time, and it gives you the full shortest path. Okay. How about an example? Well, it's too tedious to work it out by hand, so the easiest thing to do is to actually give you an example by actually running it on IPython notebook. So code it up, and I'm happy to do that for you, but the book has a nice worked out example as well. Alright, so this is the main algorithm for all pair shortest path. Now there is a couple of things that I will have to mention. Okay, so one thing is, this is one way of doing, if you think about this, this is nothing but a dynamic programming memoization algorithm. Okay, and the idea behind the way you memoize or way you carry out the dynamic programming is you restrict the set of intermediate nodes to be of id less than equal to k rather than, and then build it up from there. Okay, now there is a different way of doing it, and this new type of algorithm, that's called the matrix multiplication algorithm. Okay, let me briefly mention it because this is somewhat useful to know, though it's going to have a complexity that's going to be suboptimal. It's going to take slightly longer running time than Floyd-Warshall, so we rarely use it, but it's still useful, and it will definitely be useful in solving some problems. What's the idea here? The idea here is I'm again going to start with a matrix D0, D sub k, build it up to D sub n, except the interpretation is different. What is the interpretation? So the interpretation of D sub k ij as the shortest path from I to j involving k or fewer edges. Okay, k or fewer edges, and in fact you just need to go up to dn minus 1. Okay, so interestingly, in the previous Floyd-Warshall, the interpretation was the IDs of the intermediate nodes were less than equal to k. Here, the interpretation is d of k ij involves k or fewer edges. Now, how do I go from d of k to d of k plus 1? So if I have d of k ij, right, how do I go from that to d of k plus 1 ij? So if I want to go from I to j, but now I'm allowing less than equal to k plus 1 edges, you have multiple options. So first option is option A, which is just instead of taking k plus 1 edges, just take k or fewer edges. Okay, so that's option A, and this is already given by dkij. Option B1 through bk, bl or bn is as follows. So let me choose a path of size k plus 1, but before I do that, let me take a path of less than equal to k edges from I to some L, some intermediate L, and then from L to j. Let me choose an edge. So the cost of this path is dkil plus weight of Lj, okay, and whichever is the smallest. So according to this, the equation becomes dk plus 1 ij is the minimum between what? dk ij. So either choose a path of length k plus 1 or dkil plus let me simply say the weight of the edge from L to J, noting that the weight can be infinity if Lj edge does not exist. And this is going to be the minimum of this plus this, and it's going to be the minimum of all this, and this is L ranging from 1 to n, all possible intermediates. Okay. Now interestingly enough, if you look at this, this has the flavor of matrix multiplication. So dk plus 1 ij is min of dk ij and a matrix multiplication of a special matrix multiplication of dk with w, where suppose I multiply two matrices A and B, okay, the ijth entry of this multiplied matrix is nothing but summation over aik times bkj, k going from 1 to n. Here, let me call it L to match it up nicely. So this is traditional matrix multiplication. This is multiplication, addition. Now if you look at it, if this is the same thing except this multiplication here is actually plus and this addition is actually a min. So if you replace this addition by a min and this multiplication by a plus, that's what's happening here. So therefore, this is special multiplication, matrix multiplication in what is called the min plus ring. What's the min plus ring? The min plus ring is basically a ring where you, instead of taking your multiplicative operator, you take it as the plus as the multiplicative operator and min as the additive operator. Okay, so this is called the min plus semi-ring. Okay, and interestingly enough, this multiplication algorithm is exactly the same as regular matrix multiplication algorithm. All right, so this is number one. So what do? We do d sub 1 is going to be exactly the same starting point as the previous one. D sub 0, adjacency matrix modified with 0 weight on diagonal and infinite weight if edge doesn't exist. Same starting point, and now you simply do d sub for here we call it d sub 1 because this is one or fewer edges already. Okay, so this is the only difference I will make. I'll call this d sub 1, and then d sub k plus 1 is d sub k multiplied specially by d sub 1. All right. Interestingly enough, if I do this, then I have to do n matrix multiplications to get to d sub n. Okay, but there is a faster way to get to d sub n. Instead of getting d sub 1, d sub 2, d sub 3 and so on, d sub n, you can go like repeated squaring. What is repeated squaring? In repeated squaring, you say d sub 1, you start from d sub 1, d sub 2 is d sub 1 times d sub 1, d sub 4 is d sub 2 times d sub 2, d sub 8 is d sub 4 times d sub 4. And so what you do, is you do repeated squarings, and in repeated squarings what you can do is you can get within log n multiplications. You can compute d sub 1, d sub 2, d sub 4 and d sub 2 to the power k, where n is a k-bit number. And then what you do is, if n is, let's say, 1 0 1 1 0 1 0 0 1 1 1, now what you do is you simply add d sub 1, d sub 2, so you simply multiply d sub 8, d sub 32. So take all the 1 bits in the binary representation of 1 and just multiply them together. So this trick is very, very common. It's called repeated squaring trick for computing d to the power n, where d is a matrix. Alright, now with this trick, the algorithm works in theta n cube log n. So this is the complexity of matrix multiplication, and this is how many you need using the repeated squaring trick. Still, it is outperformed by Floyd-Warshall which is done in theta n cube. Alright, there is just one last point, and this last point is transitive closure of a graph. Transitive closure of a graph is basically, suppose I have a graph, okay, and I have edges in this graph. What I want to do is I want to compute a new graph called the transitive closure, where if there is an edge in the transitive closure from ij, means that there is a path from I to j in original graph. Oh, so as an example, suppose I took a graph 1, 2, 3, 4, 5. The transitive closure graph is going to be, let me show it in red, it's going to have the same set of vertices, but it's going to have a whole lot more edges. There's going to be an edge from 1 to 2 because there is an edge in the original graph, 2 to 3. Now there's going to be an edge from 1 to 3 because there is a path in the graph from 1 to 2, 2 to 3, 1 to 4, 4 to 5, 1 to 5, 5 to 3, 5 to 2, 5 to 4. So you can see there's going to be a whole bunch of edges in this graph, okay? 3 to 2, 3 to 4. So there's going to be a whole bunch of edges in this graph, where if there is a path in the original graph, for example, there is a path from 4 to 5, 5 to 1, 1 to 2, 1 to 3, so there's going to be edge from 4 to 3. So things like that, okay? So for any, if there is a path from I to j in the original graph, there's going to be an edge in the transitive closure. Now, how do I compute the transitive closure? Well, here's a simple idea. Start with simply give all the edges weight 1, okay? And do all pair shortest path. So all pair shortest path is going to end up with a matrix D, which is going to have the weights, and it's going to have infinity if there is no edge. Okay, so if there is no edge, if the shortest path distance, if there's no shortest path, it's going to have infinity. Otherwise, it's going to have the shortest path. And so on. So now, take this and construct the adjacency matrix for transitive closure. Interestingly enough, this is an easy idea, but you can make it even better because you really don't need to know the shortest path distances. You just need to know if there is a path or if there isn't a path. So there is actually an easier idea where instead of storing the shortest path distances, just store false if there is infinity and just store true if there is a path. And now you can use Boolean operations of and or to compute the transitive closure. How you exactly do that, I will leave it as an exercise, but you can already see how all pairs shortest path can do some interesting things that you can't normally do otherwise. All right. Hopefully this was all clear. Hopefully you saw how dynamic programming gives you all pairs shortest path, and this should conclude our discussion on shortest paths. Thank you.